Welcome to the Ultimate Go Programming Live Lessons second edition. Yes, this is the second time we're here, and if you've seen the first edition, there's a lot more going on here. My name is Bill Kennedy. I am a trainer in the Go space. I've been training companies for over 4 years, hundreds of companies and thousands of developers. And this class is really about somebody who wants to learn this language inside and out. I assume that you're already a software developer. I'm not going to be teaching you basic syntax. I'm going to be teaching what you need to know, the history, the mechanics, and the semantics of this language so you can learn how to read code and leverage Go's tooling like never before. So in this video, we've got lots of lessons, and I really need you to start from lesson 1. Please don't skip around. I build layers of foundation that are going to be very important for you from beginning to end. So we're going to start with like design guidelines. I've got to get your mind in place for what Go is, where Go is trying to take you, so you can appreciate everything I'm going to show you moving forward. Now, we are going to talk about language syntax, and a lot of the language syntax we talk about will revolve around, again, the history of the language, the mechanics, how things work, the semantics, how things behave. This is so important. So we're not going to really be talking about syntax like you think. Like, I'm not going to teach if statements and for statements. We're going to teach the semantics about these things that are unique or very important in Go. Our data structures, our arrays, our slices, and our maps, our core data structures in Go. I'm not going to just teach you how to use them. I'm going to teach you why they're there, why Go only has these data structures and the mechanical sympathies and the data-oriented design aspects behind it. Now, we always got to learn decoupling, right? We're going to learn how to work in the concrete. Our performance comes from the concrete. It's our data structures, our language syntaxes, but decoupling is key. We've got to be able to minimize those cascading changes throughout a code base. So we're going to learn the mechanics behind decoupling, the cost of decoupling, and a lot of the semantics there as well. Then we're going to get into design, right? So we've done that, we've learned that. Now we get into design. We learn how to leverage the beauty of composition in Go. We start to design our software from the concrete up through the use of composition. Error handling is everything. We're going to learn how important integrity is in Go, and that error handling piece is going to teach us how to write APIs that respect the people who are using our APIs, right? We're going to respect and give people enough context to make informed decisions. Now, I see a lot of companies lacking on the idea of package-oriented design. How do we structure projects in Go? How do we design packages? We're going to talk about that from a design standpoint. I'm going to try to give you as much guidelines as I can around packaging. Then we're going to move into the concurrency, which is where you're probably going to want to try to start. I'm going to try to hold you off again throughout the class. Start from the beginning. Get to the concurrency sections when they come up, because we're going to be using a lot of what we've learned as we move in there. So I'm going to teach you Go routines and how to manage Go routines and how to deal with synchronization and orchestration, especially when we get into data races. We'll talk a lot about synchronization in our data race lessons, and then channels we come back and start talking about orchestration. So all of this concurrency stuff, including special patterns that are going to help you really summarize all of this stuff and show you the real power of Go. And once we get through all the concurrency stuff, I'll show you how testing works in Go. Unit tests, subtests, mocking. I'll show you all of that stuff. I'll show you how cool benchmarking is in Go with some basic benchmarking there and validating what you're doing in terms of benchmarking. And then we're going to have a ton of fun learning how to do profiling and tracing. And every single lesson that I've just mentioned sits on top of the other. So really take the time from beginning to end to walk through this material. There's a lot here, a lot here. I normally teach this material over 3 days, and you get the opportunity to sit there in your home, wherever you are, and take your time to learn this stuff. It's going to be very valuable for you if you're really looking to be a high-level, performance-oriented Go developer. All right, that's everything, so let's get going. Welcome to Lesson 1, Design Guidelines. Please take the time to listen to what I have to say here. I'm going to be setting up the stage for the history of where Go comes from. I'm going to talk about a lot of quotes. I'm going to give you a lot of quotes from very important people in our industry from now to 40 years ago. You're going to understand why Go is the way it is and what we're going to do in this class and why I'm teaching it the way I teach it. So the design guidelines here are very, very important for you to be able to set your mind, okay, set yourself up to have a very successful time going through this video. All right, I want to make sure that you fully understand what this material is and where it's coming from. And this is why I truly hope you start these lessons right here with Prepare Your Mind. Follow these lessons in this first section because it's really going to help prepare you for not just the material we're going to teach, but how I'm teaching it and why I'm teaching it the way it is. Now, somewhere along the lines, we came up with this idea that programs and projects with large amounts of code were really, really cool and they were awesome. But I want you to understand that this is not really where we want to go today. We're going to learn that lines of code really can affect how healthy a project is, how healthy a team is. And I want to start moving away from being impressed with projects with large amounts of code. If you look at the Linux operating system as an open source project, there's about 24 million lines of code in that project today. That is immense. It's massive. It's going to take a massive team to be able to deal with that. And I personally don't want to be on projects like that. Now here's another thing that I want us to focus on and understand that Go is trying to solve. That we were taught to create these large abstractions in our code base to deal with change. In fact, we've been taught to put abstractions on top of abstractions. This is something that we also need to get rid of because all this is doing is adding more code to our project, which is going to be causing more pain. And I think one of the most beautiful things about Go is that we're going to learn how we can create these very thin layers of decoupling and still achieve our ability to deal with change without all these extra generic layers of abstraction. Now here's another one that a lot of people lose, and it's not fair. The languages you may have been using could have been using a VM like Java and C#, where there's a virtual machine there taking care of what we will call mechanical sympathy. We're going to learn mechanical sympathy in this class. But what's important here is this, is that if performance matters, and it does, that's why we're here using Go, then it's the hardware that matters because it is the hardware that executes instructions. Your performance is going to come from the hardware, nothing else. So we either need to be sympathetic with the hardware or not. The hardware is the platform at the end of the day if performance matters. And we all know that it does. And the last thing here, and again, I think it's lost because of the languages that we've been working with, is that engineering is about understanding cost. Every decision you make comes with a cost. There's a benefit for that decision and a cost. And if the benefit is not outweighing the cost, you shouldn't be taking the decision. You should be making that decision. And so part of this class, a big part of this class is understanding that engineering is about understanding the costs you are taking. And when you don't, you're not coding, you're not engineering, you're hacking. And we can't have that today at all. Now, another thing that's very important, these are things that I believe Go is trying to solve. These are problems that Go has seen, and we're trying to solve them with Go. And this other one is that the idea is that you cannot throw more hardware at the problem. Now, not many of us have data centers anymore. We're using the cloud. And so I could apply that to the idea that you can't throw more cloud computing at the problem anymore. It's expensive stuff. And so one of the big things about Go is we're trying to write software that minimizes the use of resources, minimizes the use of that hardware, minimizes the use of cloud. Why? We can keep those costs down. We're on shared machines. And again, all these things are going to tie back in together into the language as we continue to learn it. And we already know this. You can't throw more developers at a problem. At least historically, it hasn't been the case. How many times you've been on a team and a manager, somebody in management comes and says, well, you know, if I throw another developer on this project, could we get it done faster? And I'm always like, look, this isn't accounting. It's not like I can throw an accountant on here and we're going to move faster. This is software development. And there are things that cause us to have pain as a team grows. I think Go is solving a lot of these problems also around package-oriented design. We're going to talk about these things. And there are ways to structure and package projects together where we could put more projects on developers on a team and potentially get more work done. But we have to know and think about this up front, and the language has kind of done that. So throughout this class, throughout the 15 hours that we're going to be together here, I need you to always be a champion for quality, efficiency, and simplicity. I'm going to try to teach you how to do that. It's critically important that you always have a point of view and self-reflect about who you are as a developer. But I don't want you to hold back on your point of view. I want you to analyze and self-reflect. What is my philosophy here? What is driving the engineering decisions that I'm making? Am I improving as a developer usually means that you're improving your point of view, that it's changing. It's okay to change your mind on something. That's growth, and we want to have that all the time. So as we continue to focus on this class, I want you to open up your mind. Look, technology is changing quickly. We feel it and see it every day, but our minds change slowly. We resist to change. And it's always easy to adopt new technology, but it's hard to adopt a new way of thinking. And one of the things I got to do in this class is kind of break you down and build you back up. There are things that I'm going to be asking you not to do that you've been doing historically or have been taught to do. Go has different costs for things, and that means that you've got to make different decisions. And it's not that what you were doing before was wrong. It's just that it's not necessarily the best or the right thing to do when we are coding in Go. And these are things that I'm going to try to teach you over the time that we're going to spend together in this class. Now, as we continue to talk about this, I want to focus on this idea of legacy software. If you ever met me in a bar and I've been drinking a little whiskey and you happen to tell me that you're a software developer, well, one of the very first things I'm going to ask you is, what is the legacy you're leaving behind? This is a critical question that you should be asking yourself. Now, I got some really great historical quotes here. I think history is critically important. Mechanics after that, and semantics, behavior. We're going to talk about all of these things throughout the class. But I love this quote from Peter. There are two kinds of software projects, those that fail and those that turn into legacy horrors. This is great. Every time I say it, I crack up a little bit. But it's so true, right? What is a project that fails? A project that fails is a project that never makes it into production. But a project that gets into production and is no longer able to be maintained, that's a legacy horror. And if you really think about it, we've got 40 years of software in this country, around the world, that is really a legacy nightmare. It is. I can't tell you how many times I walk down the street and just wait for the lights to turn off. I'm always saying that I don't want Hollywood anymore to write movies about earthquakes and asteroids. I want a movie about legacy software systematically failing all over the planet and no one being able to do anything about it because there aren't any unit tests to deal with it. And I've got clients today that are writing legacy code out of the box, mainly because one, they don't know how to do it any other way, and two, they create these incredibly short-term milestones for themselves that just really can't be met. And at the end of the day, all they're doing is hacking. Look, Chuck Moore said it best. Legacy software is an unappreciated but serious problem, and it's going to be the downfall of our civilization. I really believe that. But we today have opportunities to learn how to write software that isn't legacy out of the box. Go is at the forefront of this. We just got to learn how to rethink how we do software development, restructure our software development, and keep this in the front of our minds at all times. But I think one of my favorite quotes throughout this entire class and all the material comes from Sarah May. If you don't know Sarah May, you need to look her up. She is a powerhouse, a thought leader in our industry. And though she spends most of her time coding in Ruby, I don't care. What she talks about and the things that she tells us applies to almost any engineering that we're doing in software development. And she said this, and I love this quote: "We think awful code is written by awful devs, but in reality it's written by reasonable devs in awful circumstances." And I want us to understand that because all of us at some point are going to be asked to look at a piece of code that we haven't written. When we look at that code, we might come up with the conclusion that I don't know what kind of drugs this developer was on, but they should have been sharing them because this is out of control. But I want us to step back and think and say, whoa. Let's not trash the developer who wrote this piece of code. Let's come back and ask ourselves, what was the condition or the situation they were in when they had to write this piece of software? And now we're here to maintain it, and maybe we can even improve it. And so I want us to all have empathy for everything that we're doing, because every environment is different, every situation is different, and we're going to be asked also to maintain code that exists. But as you continue to write new code, I want you to think about that person that has to maintain that code after you. That's going to help us move away from these legacy issues. Sarah May, brilliant quote. Now, if we really are going to focus around not creating legacy code out of the box, for me, the number one thing we have to keep in mind are mental models of a code base. Mental models are everything. And it's going to be part of your daily refactoring of the code. Mental models, number one. Now, Tom Love, who's the inventor of Objective-C, said this. And Tom Love works for the Department of Defense on very, very, very large projects. But he said that, let's imagine a project's going to end up with 1 million lines of code or more. The probability of that project being successful, at least in the United States, is about 50%. This is a nasty thought that once projects get over 1 million lines of code, they're probably going to fail. This is scary. But why is Tom saying this? He's saying it because he identified that a ream of copy paper is about 10,000 lines of code. Now put that in your head. I mean, you can all imagine what a ream of copy paper looks like. I'm sure we've all touched a ream at one point of time in our lives. That's 10,000 lines of code. What Tom is saying is that a developer, the average developer, really can't maintain a mental model of code beyond that 10,000. When we talk about maintaining a mental model, I don't mean memorizing every line of code. What we mean is that you know where everything in that code is. If I ask you where this function is, if I ask you where certain things are, you can find it quickly. You know how the flows work. You know how variables are named. You understand the code base intimately enough where if there is a problem, you could probably go to the code, identify where to start looking, and start reading that code very, very quickly. That's the mental model. This is what we're looking for. And Go is going to allow us to do this because we're going to be able to write less code. But this is really what happens. If the average developer can only handle 10,000 lines of code, then once a project goes beyond 10,000 lines of code, you need a new developer on that project. And when we start talking about code bases with 1 million lines of code, I mean, we're talking about 100 developers on that project if we really want to maintain our mental models and the health of the project. And I don't know about you, but historically I've only ever worked on teams of about 3 or 4 people. And I could tell you it is difficult to keep 3 or 4 people rowing the boat in the same direction every day. Imagine trying to do that with 100 people. And this is why these projects fail. As the larger the code base gets, it's not even so much a technical issue anymore beyond the fact that we have to manage more people who have to maintain these mental models. We probably don't have even one person that knows the full mental model of that code base. It really becomes both a technical and a management issue. And so we really want to focus on lines of code and reduce it. And to identify the health of our teams, we really need to understand, is there that 10,000 to 1 developer balance? Now, cognitive load is really, really important. And Brian Kernighan said this best. The hardest bugs are those where your mental model of the situation is just wrong because you can't see the problem at all. And everybody knows that debugging a program is twice as hard as writing it. So if you're clever when you write it, how are you going to debug it? People find this really interesting, but historically, I've been writing software for 30 years. Historically, I never allowed developers on my team to use a debugger without asking for permission. And this is primarily because when there is a problem in production, all you have is your mental model of the code base and the logs that you're writing. And if these are not helping you find bugs, you're done, you're lost. You're not going to hook your debugger up into your production environment. And I'm not saying that debuggers are necessarily bad. They are a tool, but they shouldn't be your first tool to finding the bugs. They're great if you've got a brand new code base and you want to understand how it flows. But I have a 20-minute rule, and that 20-minute rule would say leverage your mental models, leverage your logging to find that bug, and if you can't after that, we'll turn it on. But we've got a refactoring problem in front of us at this point because we've lost it. All right, so I don't want us becoming attached to debuggers. I want us to focus on our mental models and really also making sure that we create logs that have more signal to noise. Because I love this quote, debuggers don't remove bugs. They really don't. They just show them in slow motion. At the end of the day, we've got to refactor that code cleanly so those bugs disappear. But at the same time, if more bugs start to show, I don't need to waste time on the debugger. Our mental models are logging. It all helps. Productivity versus performance. This is a big one. As an industry, if I ask people for a long time, is performance your highest priority, they would say yes. But the reality is that productivity has been our highest priority. It has been in just the languages we've been designing, the languages we've been using. People want to be productive and get things done. And we've kind of looked at performance as secondary, though if you ask anybody, they're too afraid to tell you that, because then you don't look like you're technical or your chops are in place. We put people on a pedestal who can get on stage and talk about how they can shave a few milliseconds or microseconds off of an algorithm. And I really kind of want to move away from that. Productivity really is and should be our highest priority, but we do need performance. It does matter. And what I find interesting about our industry is that for the last 30 years, we have kind of been on the same path that Nicholas Wirth has said back in 1987. He said that the hope is that the progress in the hardware is going to cure our software ills. In other words, he's saying that we as software developers have always said, we don't have to worry about performance. The hardware will come in and save us. And we've continued to kind of have this mantra for the last 30 years. Back in 1987, after I graduated high school, I was on a plane to Italy, and I sat next to a software developer, and that software developer told me, this is 1987, that all of us right now watching this video would be BASIC developers. We'd all be coding in BASIC today because the hardware would be so fast, we wouldn't need anything else. The reality is that has not happened. I mean, Henry back in 2015 wrote, the most amazing achievement of the computer software industry is this continuing cancellation of the steady and staggering gains made by the computer hardware industry. We're still talking about this stuff 30 years ago. Remember, I told you before, the hardware is the platform. If performance matters, then we have to be sympathetic with the hardware, mechanical sympathies. And look, the hardware folks really haven't changed hardware in the last 15 plus years. They really haven't. We've had these multi-core processors, multiple hardware threads per core, and the reason why they're not doing it is because we haven't been able to take full advantage of what's there now. We're starting to see now Intel talk about their 24, 36 core processors. And that's great and it sounds amazing, but if we don't engineer for this hardware, if we don't understand how it works, those processors are actually going to slow us down, not speed us up. So we're going to spend some time in this class talking about how caching works and some of the mechanical sympathies the language drives through us and allows us so we can get to these levels of performance and we want, and hopefully take advantage of the hardware that's there so the hardware industry stops playing games and starts giving us more. But that's on us, it's not on them. But I think our core part of this class is going to be this next quote from Brian Kernighan. And it starts him talking about C. He was asked a question about the C programming language, but I think you can replace C with Go, and it absolutely mirrors it exactly. Go is the best balance I've seen between power and expressiveness. You can do almost anything you want to do by programming fairly straightforwardly and have a good mental model of what's going to happen on the machine, and you can predict reasonably well and how quickly it's going to run and understand what's going on. This is Go in a nutshell. I'm going to teach you how to read code in this language, so that holds true not just for me, but for you. And it's possible because Go's model is not a virtual machine. It is a real machine. It is the real machine. And once you're coding against the real machine, then you can do all of these things if you just know a little bit about the mechanics and the semantics of the language. When I say mechanics, I'm talking about how things work. When I say semantics, I'm talking about how things behave. And I'm going to teach you throughout this class how to be able to do that, and that's going to drive you being able to make some better engineering choices. Correctness versus performance. So this is a big one for me because we've also been trained as developers to kind of like focus on performance again as a priority, and we tend to write code with the idea that this is going to be faster than that. The reality is that unless you've done it 1,000 times and you already know, you're guessing. And usually code that's focused on performance is clever code. I want to reverse the tables on this. I don't want to optimize for performance. I want to optimize for correctness when we're writing code. I want to use our debuggers and our profiles, not really our debuggers, apologize, our profiles, our ability to benchmark, our ability to trace, to identify where we may have a performance problem, and then fix the performance issues like that, still trying to maintain levels of correct or readable code. Look, the performance of your software is going to come from 4 places. Or I should say the lack of performance is going to come from 4 places. First is latency. And it's going to be latency on networking and I/O, disk I/O, those types of things. That's going to be a real killer of performance. And those are things you probably want to focus on first. Your next potential performance drain is going to be on memory allocations. We're going to talk about that in this class. And memory allocations can cause performance problems. And we'll see that when we start talking about the garbage collector. And the garbage collector is doing an amazing job, but we don't want to walk away from it. But when we talk about performance in Go, it's not about is it the fastest, it's about is it fast enough. But garbage collection and memory allocations, that will be your number 2. Number 3 is going to be how you access data, how efficiently you access data. We're going to talk about that in this class as well. And then number 4 would be like algorithm efficiencies. Can we streamline an algorithm to take less steps than more? And we tend to, if we're optimizing performance, focus on that piece. And the reality is the hardware is going to be so fast if we solve the first 3 problems that we can have a little algorithm inefficiency and still get more than we need in terms of performance. And now we're optimizing for correctness. And this is really where we want to go. And there's some great quotes by some amazing people in this area. Wes Dyer, make it correct, make it clear, make it concise, make it fast. I want us to listen to this history. These are people who've already learned these lessons. I don't want to make the same mistakes. All right, JBD, who works over at Google, and again, you got to look her up. She's also a tremendous thought leader in this space. You know, engineering is about not about finding the perfect solution. It's about understanding the trade-offs. We talked about this. Engineering is about understanding the costs you're taking for the benefits that you need. It also is about optimizing for correctness, knowing what we're doing in terms of our code. And correctness of the implementation is the most important concern. Listen what Al is saying here. But there's no royal road. Listen to Al again. What he's going to say is that it takes several things. Invariance, that's the engineering costs. Testing and code reviews. And testing and code reviews really require our ability to read and understand code. Without our ability to read and understand code, we're really going to be lost. There's a great quote that says that we are one of the few industries where we ask people how to write code before we teach them how to read. And this is really mind-boggling when you start to think about it, because everything that we're going to talk about correctness is going to stem from our ability to read code first. And this class is all about our ability to read code, to optimize for correctness, to be productive. That's what we're trying to do. That is what Go is trying to do. And if we continue to look at quotes even from Brian, right, the basic ideas here of good style, of correctness, are fundamental to writing clear and simple code. And we've known this, he's known this for over 35 years. I'm not telling you anything new. These are not my ideas. These are not my philosophies. I'm trying to bring to you industry leaders who are telling us over and over again, correctness over performance when it comes to the code. And to do that, we've got to be very good at reading code. But I love what Jason Fried said here. Maybe, again, next to Sarah May, one of my favorite quotes here in the material. Problems can usually be solved with mundane solutions. That means there's no glamorous work. You don't get to show off. Okay, you build something, it works, you move on. Okay? And this is really important. This is one of those quotes I want you to put in front of you at all times. Because if you are a back-end developer, like I am, and what you're looking to become if you're not already, then the idea is that your software should be working 24/7 without issues. The reality is nobody should know your name if you're doing your job well. If somebody knows your name, probably means your software is failing or causing problems. You want people to know your name? Become a front-end dev. Front-end devs get the oohs and the ahs, but I promise you this, you're going to spend 2 weeks working on a screen, killing yourself to get things in a certain location, certain words, and the first thing somebody's going to do when they look at it is point something out that they don't like. Oh, that used to drive me crazy. I'm a back-end dev, okay? I build systems to the point where nobody knows I even exist. That's a good day in the office. Code reviews. All right, since we're going to be focusing on reading code in this class, we've got to have a measuring stick. We've got to have priorities in reading code. And I do these things in my head while I'm coding. We do these in code reviews. And this is also, from my perspective, Go's priority when we're reading and writing code. Number one is integrity. And if integrity isn't your number one, I'm telling you right now, you can't work for me. Integrity is everything. Integrity is about being serious about reliability. And it's really important. In fact, I love asking this question. This is my cell phone. You've got one, I have one, everybody you know has one. We can't live without these things. So here's an interesting question. If this cell phone stops working for the next hour, your phone, my phone, everybody's phone in the United States, it stops working for the next hour, how many people lose their lives? I know it's a serious question, but the reality is that if this phone stops working for the next hour, the answer to that question is not zero. Somebody's going to lose their lives. Our lives are so embedded in technology today that if things can go bad and people are going to lose their lives, this is a very serious situation. This is why integrity has to be number one. Do you realize that we are one of the very few industries where people's lives are at risk and we're not licensed to do our job? I mean, how long do you think it's going to last that we as software developers are not going to need a license to do our jobs? Because at the end of the day, everyone's life is at risk. Now, you might say, Bill, come on, man, I'm in the gaming industry, or I'm in some industry where people are having fun. No, the reality is that even with the mental illness crisis in this country, your software, your bug, your problem may be the one that puts somebody over the edge. Over the edge. And so I need you to constantly put into your mind that regardless of the industry and regardless of the software, right? People's lives, their happiness, everything is being dependent on the technology that you're building. And we got to take integrity seriously. Now, integrity comes in two places. There's a micro level and a macro level. At the micro level, I want you to understand that every line of code you write, every line of code either does one of three things. It allocates memory, it reads that memory, and it writes to that memory. What's really interesting is all our code is doing is reading and writing to memory. What's really interesting is all we are doing in our code is reading and writing to memory. And yet, all of those reads and writes cause everything around us to happen. Lights are on, you're watching this video, phones are ringing. It's all reads and writes. What's even crazier is we're really just reading and writing integers at the end of the day, too. Really mind-blowing stuff. So at a micro level, integrity comes from the fact that those reads and writes are always accurate, consistent, and efficient. And when they're not, then we have an integrity issue. We've got corruption. Software now has to shut down because if it doesn't, we're going to cause more damage than good. But there's also integrity at a macro level. I want you to understand that really what we do every day is solve data transformation problems. Data-oriented design is going to be a big part of this class. We work with data. And data-oriented design says that if you don't understand the data, you do not understand the problem that you're working on because the problem is the data. And our functions and our methods and these encapsulations that we write are all about the data transformations that we have to perform. And so if your data transformations are not accurate, consistent, and efficient, you also have integrity issues. And we have to apply this idea of data-oriented design. Go is very focused on data-oriented design. I'm going to show you this in the language. As opposed to object-oriented design, data-oriented design is going to be very big here. And it's, again, all about our data transformations being accurate, consistent, and efficient. You know, one of the things I like to do is I have a friend who's in the data science world. And I always say to him, you know, man, you guys are a trip over there. You know, you guys came up with two funny words, machine learning and AI. And suddenly you guys created this whole kind of software industry around just data science. I'm like, dude, we've been doing data science, machine learning, and AI for 30 years. Man, we've been building predictive algorithms just because we didn't formalize the models and all that stuff doesn't mean we haven't been doing it. Everybody is. What I want you to have in your head is that you are a data scientist. If you are a software developer, you are a data scientist because you're working with data, you're transforming data, and it's what you do on a daily basis. If you don't understand the data, you don't understand the problem. If you don't understand the problem, how can you write a single line of code to solve it? Now, integrity is going to really come in two places from a macro level, and things that we're going to focus on in this class as well. And I already told you before that lines of code is critical. The amount of lines of code in your project will determine the health of your team and the health of your project. I said before that the average developer cannot handle more than 10,000 lines of code, cannot maintain a mental model of more than 10,000 lines of code. Once projects get larger than that, we really need more developers. And we keep focusing on this idea that we need to write less code. And there was a study done where they identified that for every 1,000 lines of code that's written, the average developer will produce 15 to 50 bugs. Now, I want to put ourselves in the worst developer category, which basically means that for every 20 lines of code you write and I write, we've added a bug to the software whether we like it or not. Start putting that in your head. So when you start thinking about, let me add setters, and let me add getters, and let me add abstractions on top of abstractions, really what you're saying is, let me throw more code at this project, and therefore let me throw more bugs at this project. We need to take this idea in the reverse. Less is always more. And what's interesting is when we have more code than we need, right, then we've got more places for bugs to hide. It also means you've got more incomplete tests because you've got to write that many more tests to deal with that many more lines of code. And eventually a code base will collapse on itself, and instead of you maintaining your frameworks and your patterns, you start to just hack. And that's when legacy becomes a real threat to the project. Now, another big part of integrity, outside of just writing less code, is also dealing with error handling. And error handling is a big, big part of integrity. Here's the reality. Anybody could write a piece of software that works when life is good. A 6-year-old can Google today and find code that works when life is good. Engineering is not about when life is good. Engineering is about when life is bad and things are happening. And your software has to be able to maintain stability and not add to the crisis, but try to recover from it. Error handling is what we do every day. The majority of the code you write is focused on failure, not the good case. And if that's not happening today, I need you to reevaluate what's going on. I love the way Go deals with error handling. It was how I've been dealing with error handling for 30 years. Even when I had exception handling in languages like C++ and C#, I used it really just to deal with the unhandled stuff. I would do very much what we're doing in Go today and return errors out or codes out and handle the errors right then and there. And I love the way error handling is done in Go. We're going to talk about these things when we get to the error handling section during design. But there was a study done on some very critical software. In fact, Redis is on this list. And how many lives today are dependent on Redis? I mean, there's a tremendous amount. And they identified that out of these projects that they were looking at and the critical failures that caused this software to either go down or have corruption. 92% of those problems could have been avoided. 92% if the error handling was better, was more focused. 92%. See, error handling is really, really critical if integrity is important. So we're going to focus on that during design as well. We're going to be constantly focused on less code and error handling as we get into design. The next step here on our code reviews is readability. Readability is number 2. It doesn't trump integrity. Nothing trumps integrity. You're doing a code review and you find an integrity issue, that has to be fixed. But readability is number 2. We talked about optimizing for correctness, which is about readability. Now, readability means that we're going to structure our software in a way that's comprehensible. And there's 2 aspects of readability that I want to focus on. The first one is the average developer. The average developer on your team should be able to understand the full mental model of the code base that we're working on. Should be able to read every line of code, have a full knowledge of the mental models, and should be able to fix almost any bug, or in fact every bug, that comes across the code base. Now, what I love doing is asking you to think about this. I want you to think about you, and I want you to think about your team. Have that in your head right now. Now ask yourself, am I the average developer on my team? Do I comprehend the entire code base we're working on? Do I have a strong mental model of what's going on? Can I solve every single bug or problem that comes across this code base? If the answer is no, then you're not the average developer. Now, I want you to think yourself for a second. Am I less than average or am I more than average? Now, the more than average developers really have a burden on themselves because you have to have responsibility to not write code that is clever. If you're less than average, you have the responsibility to come back up. Now, I want you to evaluate everybody on your team. Who is average? Who is less than average? Who is more than average? Are those less than average people working hard to come up to speed? And are you helping them? Or are you a hindrance? As the average developer, you have responsibility to bring them up. Are you or who else on your team is more than average? Is that person writing really clever code? Have you taken the responsibility to tell them that their code is too clever? And are they taking responsibility to not do that? Look, you put me on a crypto team, I am less than average. I've got to come up. You put me on a team building business applications, web APIs, I'm going to be above average. I've got to make sure my code comes down. And if you're hiring somebody and you don't know whether they're average, less, or more, you're really going to cause problems on your team dynamic. If you're hiring people who are less than average, do you have the time to bring them up to speed? The answer is probably no. But if you do take the time, think about how an amazing developer they're going to be for your team. If you're hiring people who are more or above average, do you have time to teach them how to be less clever? Are they willing to be less clever? That's going to cause more problems than probably the developers that are less than average. I need you to do these evaluations for yourself, for your team, and when you're hiring. This is really important stuff. But that's subjective, right? And it's based on the team and it's based on the software you're building. And you always want to make sure that that team dynamic is everybody knows who they are, what their responsibilities are, and that the code base is clean and healthy with those mental models. But that's subjective. Let's talk about the piece that's not subjective. What readability also means is not hiding the cost of the code you're writing, not hiding the cost. Now, this one is hard for me to explain, so what I'm going to use is a piece of code that's written in C++ to show you what I mean about not hiding cost. And even if you've never seen C++ before, I promise you, you'll be able to read this code. So let's take a look at this code that's written in C++. What you see here on line 7 is a type named foo. Now, what's special about foo is that it has these features that you find in object-oriented programming languages like C++. On line 8, there's a constructor. On line 9, there's the copy constructor, the move constructor, the destructor. And if you're an object-oriented programming language developer, you know what these do, right? Constructors get called when a value is constructed, destructed. If you're making a copy, if you're moving something. We call these features because we're able to kind of tuck away code when these things happen in our code base. And you could also see on line 13, I've operator overloaded the assignment, which means anytime we use the assignment operator against a value of type foo, this code is going to get called. We call these features. Now look on line 16. On line 16, what we have is a function named f1. And f1 creates an object of type foo, makes a copy of it on the return, and brings that copy back out. The caller gets a copy, its own copy of the foo object being created on line 17. Brilliant. I've shown you 18 lines of code. I haven't hidden any of it from you. And this is what I want to ask. Look on line 23 and 27. This is super interesting. On line 23, we're calling the f1 function, which creates an object of type foo and returns a copy of it back out and assigns it to a local variable, foo1. On line 27, we call f1 again, the same function we call again, reassigning to our foo1 variable. So here's the question. Who can look at this code right now, and I've shown you all of it, but let's just focus on the two lines there, 23 and 27. How many objects of type foo get created by the time this program runs and completes? Does the copy constructor get called and when? Does the move constructor get called and when? And does the assignment operator ever get called and when? Here's the reality, is that you have no idea by looking on line 23 and 27 what the full scope of behavior is on that call. And by the way, if you don't ask me what version of C++ we're using, the behavior changes. The semantics change also depending on what version of the language you're using. This is a nightmare. the fact that I cannot look on line 23 and get an understanding of how that code's going to behave, how it's going to perform on the machine, and what my costs are is a nightmare. This is why Go doesn't have constructors and destructors and these features, operator overloading features, because they hide costs. They don't help us. Now here's the reality. When I run this code on the latest version of C++, you're going to see that the first call to foo optimizes the copy away. On line 23, the optimization by the compiler says we don't need to make a copy. We're creating this object for the first time. We'll assign it. But on the next call, line 27, even though calling F1 again and reassigning it, now constructors, assignment overloads, copy constructors, 2 objects are made. Oh my God, the cost difference on line 23 to 27 is great. We cannot write code like this. These features hide cost. Go doesn't have it because Go doesn't want you to hide cost. And when I see code that's hiding the cost or the impact it's going to be having on the machine, guess what? We have to fix it. We have to walk away from it. So Go doesn't have those features. And it's very, very important that we remember that we are focusing on the real machine. That way we get to be able to write code that doesn't hide the cost. And we give that developer at every moment in time the ability to understand the costs they're taking and the impact it's going to have. And I love this quote from Peter Bargon. And he's another gentleman who's a big part of the Go community, a thought leader, somebody you should be looking up, somebody you should be watching talks from. Making things easy to do is a false economy. Focus on making things easy to understand, and the rest will follow. Now, simplicity comes after readability. Integrity, readability, and simplicity. Simplicity is interesting because what simplicity says is that we want to hide complexity. Remember, readability is about hiding, not hiding cost. Simplicity is about hiding complexity. And our encapsulations, right, our functions and our methods, which are trying to reduce the boilerplate code, it's trying to simplify things. If those encapsulations cause our ability to no longer understand the impact our code is having, we can't have it. Simplicity is not something you do day one. It is something that you refactor into. And one of the biggest things that I can tell you about simplicity is what Dijkstra said. You know, it's a great virtue. It requires hard work to achieve, education to appreciate it, but complexity sells. But we've got to get away from that idea that complexity sells. And we've got to refactor into simplicity as we go. Go is an amazing language as it comes to simplicity engineering. I'm going to try to point those things out to you as we go. But there's 2 more big parts of simplicity here, quotes, that I want to say again. Again, we're trying to hide complexity, but we're going to focus on this in the class really well. And Dijkstra said it again. The purpose of abstraction is not to be vague, but to create a new semantic level where one can be absolutely precise. We're going to talk about at some point precise APIs and how powerful they are in a language like Go, where we have a compiler and have the ability to find and identify bugs at compile time as opposed to production. And I'm going to be asking you to kind of throw away some of the API design that you've been taught around object-oriented programming here and really focus on the cost that that has over the benefits of this idea of precise API design. And Joe Beda, who's a company called Heptio, great company, said this, and I love this also around simplicity. Computing is all about abstractions. Those below are just details, and those above are limiting, complicated, crazy town. So anytime I look at a function or a method and I'm seeing that this is an abstraction, right, we're seeing encapsulation, I want to make sure that these encapsulations are not just testable. I want to make sure that they're providing a new semantic, precise level of understanding that is not hiding cost, okay, but hiding complexity. Welcome to Lesson 2, Language Syntax. This is where we begin to start learning how to read code in Go with the understanding that every decision you make comes with a cost. Nothing is free. What benefit are you taking for the cost that you're taking? And this is where we start to begin to look at the cost of things. We're going to learn how pointers work and memory works, which is so critical. If you really want to understand the cost of things, We're going to learn how important it is to really understand how things work in terms of memory. We're going to get through all of that and language syntax that's important for our ability to be able to predict reasonably well how code is going to run on the machine. Variables. All right, so in this section, we're going to talk about variables. But trust me, this material assumes that you're already a software developer. You know what variables are. I'm not teaching you variables from the very beginning. There are just things here that I need to talk about to help us develop a base knowledge of material as we continue to grow in complexity and our ability to read and write code and Go. So I really hope you stick out this section. I'm not teaching you what a variable is, but there are some very important things here. So we're going to scroll down now into this area where we have the code review. And we'll be using the Go playground for a lot of this. Now, one of the things that I want to talk to you about is type. Type is everything. Type is life. And I promise you one day, if I get a little too drunk, I'm going to go to a tattoo parlor and I'm going to write type life right here on my knuckles. That's how important it is. Actually, if that ever happens, you can just laugh at me for the rest of your life. But type is everything. Type is life. Without type, we can't really have integrity, and we can't really start to understand the cost of the decisions we're making in our code. I mean, start with this right here. Our basic unit of memory that we're going to be working with in our programming model is a byte. And a byte is 8 bits. And I've just drawn a byte right now here on the board with a particular bit pattern. Now, what I'd like to ask you is, what is the value of this byte? What is this byte, or what is the value I've just stored inside this box? The reality is you cannot answer this question unless I give you the type information, unless you know what this bit pattern represents. Now, if I tell you that this represents an integer, now you can tell me, well, Bill, that represents the number 10. Brilliant. But if I said, no, it doesn't really represent an integer, it represents a color. Now you've got to say, Bill, what is number 10 on your color chart? And I might say to you, oh, yeah, no, that's red. So you could see that this bit pattern can represent an infinite number of things. It's all based on what the type information is. Now, type provides us two pieces of information. Size, how much memory, how many bytes of memory we need to read or write at any given time, and its representation, what it represents. And Go is not being novel in many, many cases. You really already know the syntax of this language. I don't have to really teach too much syntax. And just like other programming languages, Go has the built-in types, your numerics, your string, and your bool. And what you're seeing on lines 15 through 18 in the code is just that, those built-in types being used. And if you look at the name of the type, start at 17. I love looking on 17. The name of the type, float64, tells us two things. Look, I want you to look at some of this early material differently than you ever have before. Right? I'm not necessarily teaching anything new. I want to give you a different perspective on what's happening here. So again, we can have this foundational material and understanding as things get more complex. When you look at the name float64, it's really interesting because it tells us both parts of the type information. Float64. 64 tells us that it's an 8-byte, 64-bit value that's giving us the cost in terms of memory footprint. And float tells us it's an IEEE 754 binary decimal. You see how the name in this case is giving us both pieces of type information. We know a bool is 1 byte. We only need 1 bit for that byte, on or off, true or false. And then when you get to int, it's really interesting. There is precision-based integers, int 8, int 16, int 32, int 64. But if I saw you using a precision-based integer and it wasn't obvious to me why, that would raise a flag to me during a code review. Now, when I say raising a flag, it doesn't mean it's wrong. It's just not obvious to me why you're making a particular choice, and I would want to talk about it. And there are times where you need a precision-based integer. If we're using the atomic instructions, if you're doing something that has to be the same size across multiple platforms. But most of the time, we're just going to use int, which can seem confusing because all this type name is giving us is half of the type information. All it's telling us is that whatever number of bytes we're going to allocate, they only represent an integer value. So then the question comes, if we don't understand size, we don't understand cost. So how much memory is allocated for an integer? Well, this is all going to be based on the architecture that we're building for. Now, most of you, if you type go space version into your command line, you're going to see that you're using AMD 64 as your architecture. Some of you might be on an ARM processor, but for the most part, you're probably all using AMD 64, which tells us that we're on a 64-bit architecture. Now, if we stick with AMD 64 for a second, what that's going to mean from a Go perspective is that since we're going to work on a 64-bit architecture, that means that our pointer size or the address size is going to be 64 bits or 8 bytes. And the way Go kind of works is this. We look at what the address size is going to be for the architecture that we're on, AMD 64, 64-bit, 8 bytes. Then we say, OK, our generic word size, when you hear me use the term word throughout the class, we're talking about a value that can change size depending on the architecture. So our word size is going to match the architecture. That's 64 bits or 8 bytes. And then Go says, if your address and your word size is 64 bits or 8 bytes, let's just make the integer follow. That will be 64 bits or 8 bytes. All three are always going to be the same. Now, this gets interesting because you're seeing code on the playground. The playground is a single-threaded environment. When we get to the concurrency stuff, we won't really be able to use it. But what's also interesting is the playground is an AMD 64 P32 architecture. P32, it's a native client architecture. What that means is that addresses are 32 bits on this architecture. For all intents and purposes, it's a 32-bit architecture because our address scheme is 4 bytes or 32 bits, which now means what? Addresses are 4 bytes, 32 bits. Word size is 4 bytes, 32 bits. Therefore, our integer is 4 bytes or 32 bits. So we see that our integer can change size depending on architecture. And there's mechanical sympathies for this. The hardware or the architecture is basically saying that 4-byte integers is going to be more efficient than 8-byte integers on our 64-bit. We're saying 8-byte integers are more efficient, right? So we're trying to gain mechanical sympathies for the platform that we're building on when it comes to the address, the word size, and the integer. And that's why we want to use int and not a precision-based integer unless it's something very specific like we have to, and it's very obvious. We want to do that. Now, there's another concept here. And I would call it one of Go's warts. There is a wart in Go. And it's that there's too many ways to declare variables and to create values in Go. And we'll talk about this early on in the class. But what you're noticing here is I'm using the keyword var to declare these variables. Now, there's a concept called zero value. Zero value is very, very important. And it's an integrity play in Go. And I want us to understand that, again, the cost of integrity is performance. So this little performance hit will never show up in a profile. I mean, the machine's very, very fast today, but we want it. And what zero value says is all memory that we allocate gets initialized at least to its zero value state. In other words, anytime we allocate a byte of memory, if we don't pre-initialize it with some value, then we're going to run electrons through the machine and make sure that we set it all to 0. This is going to help with a huge number of bugs that we've had in the past where a program starts up, it allocates a variable, it doesn't initialize it, the bit pattern is reasonable enough, and the program starts running. And it's running, but it's also in a corrupted state. So zero value is an integrity play, and it's very, very important. And one of the things we're going to do in this code base, and one of the things I follow, is that if I'm going to declare a variable, create some value like this, declare a variable, and it's going to be set to its zero value state, I'm going to use var. Var is that kind of readability marker that we're declaring and initializing to 0 value. And var gives us 0 value 100% of the time in this language. And I'll show you some examples later on where if you're not using var, you're not getting 0 value. Now there's one more type here, and it's called string. And strings are really kind of made up data types for any language, and there's different ways to implement strings. Go has what I would call a unique way. I had never seen it before up until Go. Now, when we look at on line 16 and we see this var b string, what we're seeing is a string being declared and created, setting it to its 0 value, which is what we call an empty string. And so an empty string in Go is going to look something like this. B is going to be a 2-word data structure. Strings are 2 words. Notice I'm using the term word because the size of a string will change depending on the architecture. On the playground, the word is going to be 2 64-byte words. So that's 8 bytes. On our 64-bit, it will be 16 to 8-byte words. There it is. Where the first word is a pointer, we're going to talk about pointers. And the next word is the number of bytes. Since this is an empty string, we don't have any pointer to a backing array yet, and there are no bytes. So a word is a 2-word data value, 8 to 16 bytes depending upon architecture. Again, I want to talk about cost, engineering cost, so we can predict reasonably well how things are going to run, how things are going to happen in memory. So type is important. The size of things can be important. We really want to understand the cost of the things that we're taking. Now, you're probably not going to always want to create, construct, and initialize to 0 value. There are going to be times where you want to pre-initialize something. And this is where the short variable declaration operator comes from. That is the colon equal that you see here on line 27. A lot of people think that the syntax from the language comes from C. But actually, the Pascal programming language had a large influence also in the syntax of this language. This is one of those places where Pascal comes from. Now, this operator is really a productivity operator. It's allowing us to declare and initialize at the same time. I don't want to use the concept that Go has duck typing. It doesn't. It's really struct-based typing. But in this particular case, I want us to always look at the short variable declaration operator as a productivity operator. So AA is 10, BB is string, CC is a float, and DD is bool. And it's based on the fact that the compiler knows what type of value is sitting on the other side of that short variable declaration. And if we go back to hello for a second, what hello would look like from a string now is an array of 5 bytes, right? HELLO. Our pointer would point to that, and we would say we have 5 bytes right there. We're going to go deeper into this stuff as the class goes on, but I really believe in visuals and being able to visualize code. And early on in my career, I used to keep a piece of paper at my desk with a pen, and I would draw these things out. So what you see me draw on the board is really my mental models, my visual mental models of code and how things go. And you're going to see a lot of that throughout this class. And I really think it helps, and it's something that might help you as well. So we've got the short variable declaration operator when it's something that's going to not be 0 value. Now, you might see code like this, and I could see this. There, I'm using the short variable declaration operator to assign or declare an integer and set it to its 0 value. There's nothing necessarily wrong with this. A big part of what we're going to learn about writing code and mental models is consistency. If you want to do this, then be consistent. I wouldn't. I would use var for 0 value because I think the readability marker of var is just way too strong to walk away. And if I was doing a code review, I'd ask us to switch that to var. But it's not for any other reason for readability and consistency and readability. So I don't want to do that. You won't see that in this code base, but that's up to you. As long as everybody on your team is doing it the same way, then it's going to be OK. Now there's one more concept here that I want to talk about, and it's called conversion. Go doesn't have casting. It has conversion. And what conversion means really is that we may be taking a cost, a memory cost, as we convert values from one type to the other. If you've never heard of casting before, what casting has done traditionally, and it's really a part of helping with performance, is saying this following thing. Let's say that we allocated a 1-byte integer. There it is. There's my 1-byte integer. Let's say for some silly, crazy reason, I decide that I really want A not to represent a 1-byte integer, but a 4-byte integer. Casting would allow me to do something like this, where I could tell the compiler, look, you know and I know that A is an int h, or 1-byte integer, but casting lets us pretend that what that memory really is a 4-byte integer. And the compiler, trusting us, will just say, OK. And suddenly now, if I'm casting A from 1 bytes to 4 bytes, I have the ability to read and write memory across those 4 bytes from this particular location. I could be potentially corrupting a lot of memory here. Now this is a silly example because really where casting traditionally comes in is kind of 2 places. One, if you're dealing with data coming over the wire and you've got large number of bytes, you probably would blindly copy those bytes somewhere in memory, and then you would cast or overlay a structure on top of it, right? And that's going to be very, very, very fast. You're just going to say, hey, those bytes over there, those 20 bytes starting at that address location, they really represent this structure. And then that's going to let you, because without type, you can't read and write to memory. It's going to let us do that. But if you're off by 1 byte, then we've got real problems. So casting comes with the idea that if you're off, or say in that 1 byte as you overlay that struct, now you're reading and writing the bytes you didn't. And that's a real problem with casting. So Go says, look, integrity is number 1. We care about integrity as our highest priority. So you could use the unsafe package to do some casting, but we'd rather have is conversion. What Go would say here is we don't want to even set up this scenario. So if you really want A to be 4 bytes, then we're going to convert A into a new value that will be 4 bytes, and maybe, and in this particular case, even have to give it a new variable name. In this case, in the example, we used AAA. But the idea of conversion over casting, again, is an integrity play. There could be a cost of new memory, but we always rather be safe than sorry. So this is what I want to share with you in the variable sections. You already know what a variable is. But to sum up here, okay, type is everything. Type is life. It gives us 2 pieces of information. Size of the memory that we're going to be allocating and reading and writing, and what that memory represents. And without the type information, we will have chaos. It gives us the levels of integrity we need. All right? We have the idea of 0 value in Go, and I want to use the keyword var for that. All memory is initialized at least to its 0 value state. We're going to use the short variable declaration operator when we're initializing something to its other than its 0 value state. There's exceptions to everything, and part of engineering is knowing when to take that exception. But these are the guidelines we're going to be following, and we have conversion over casting. Again, it's an integrity play to keep our software, again, and our data and our memory safe. Okay, next we've got to learn about struct types, or really user-defined types. The language would be useless if you couldn't define your own data definitions, right? Your data types. And Go, again, is not being novel here. Lots of languages do that. So there's some important things here I want to share with you. Not necessarily teach you what a user-defined type is, but kind of how they exist in Go. And there's a great quote here by Martin Thompson, who really coined the phrase mechanical sympathy. Look him up if you don't know him. Implicit conversion of types is a Halloween special of coding, and whoever thought of them deserves their own special hell. We'll come back to this implicit conversion here, and Martin Thompson. I really love the quote. All right, let's do a little code review here, and let's start with some basics here around our user-defined types. So there it is in Go. On line 10, I'm defining a named type called example. It's a struct type, a composite type. It's made up of 3 other existing types, bool, int, 16, and float, 32. There it is. Nothing really special going on. And you see on line 20 that I'm creating a value of type example named E1, setting it to its 0 value. You won't hear me use the word object in Go. We create values in Go. You'll continue to hear me say that. Listen to the language and the words I'm using. I'm going to be very consistent with them, and it's going to help us throughout the class. So again, on line 20, we are constructing or creating a value of type example named E1 set to its 0 value. But let's go back here and talk about the type declaration, because I want to focus a lot on if performance matters and these things matter, with the idea that we optimize for correctness first. And at the same time, there's some interesting things about structs that I want to share. And if we're really going to understand cost, I told you we have to understand allocations. And so then the first question I'm going to ask you is, how much memory is allocated for the E1 variable on line 20? I mean, anytime we construct a value of type example, how much memory has to be allocated? Now, your first guess might be, well, Bill, it's a composite type. So, I could just do the following. I could say, OK, the first field is a flag. So, Bill, that's a Boolean, right? And that Boolean would just then be 1 byte. And then, Bill, I've got a counter, which is an int 16. So, my counter, Bill, that's an int 16. So that's 2 bytes. Drawing a little line for the 2 bytes. And then, Bill, we've got pi here. And that's a 4-byte value, Bill. And what was that? A float 32, Bill. So, if I add these 3 things up, I'm going to get a total of 7 bytes. So Bill, it seems to me that every time I construct a value of type example, it's going to be 7. Now, I don't think it's a bad guess. It's probably, and it's very realistic. The problem is that that's going to be wrong. And the reason that's going to be wrong is because we have the concept of alignments. And they come from the hardware. And alignments are there to make reading and writing memory as efficient as possible. As we move across the hardware in this class, we're going to see that there are these different boundaries, memory boundaries, that the hardware is dealing with. And one of these boundaries is the hardware's ability to pull data in and out into the hardware. And so what we end up with is these machine word boundaries, right? And I just want you to get a general sense of what's happening here with alignments and why they're in place, and then why this really isn't a 7-byte value, but we're going to find out that it's an 8-byte value. So if we take memory on these word boundaries, here we go, on these word boundaries, then the idea is this. The hardware has the ability, let's say within one instruction, to read and write this word boundary, and then read and write this word boundary. So the idea is that if we would allow a 2-byte value, let's say we had a 2-byte value, and we allowed that 2-byte value to be placed in memory across this boundary like this. Let's say that's our value. We've just now allowed it to align in memory in such a way that it crosses over these 2 boundaries. Then it means it would take the hardware 1 and 2 operations to read it in, and then 1 and 2 operations to write it out. I mean, not efficient, and really sets us up for some other nasty things later on. We don't want to do that. The hardware doesn't want to do that, and we don't want to do that. So the idea around alignments is there's no reason to allow this value to cross over these word boundaries here when it can easily fit inside of a single word boundary. So the idea of alignments is to say, let's make sure that all values, wherever they are, fall within these word boundaries. So if I have a 2-byte value, then they always fall inside the boundary. Now, what that means is that we're going to end up with this other concept of padding inside of our structs. So let's go back to our struct for a second and start to understand what alignments and padding do. So the way this is going to work is the following. If you have a 1-byte value like a bool, well, that will fit inside of a word boundary no matter where you put it. It could never cross over because byte is our basic unit of memory, read and writes, and that will fit inside of any word boundary cleanly. But when you get to a 2-byte value like counter, now, as I showed before, we can cross over these boundaries. So what we need to do is make sure that any 2-byte value always aligns within a single word boundary. How do you do that? Well, you make sure that that value always falls within a 2-byte address scheme. In other words, if we look at the last digit of any address, it always falls on a multiple of 2 in terms of its address. It falls within, so address 0, address 2, address 4, address 6, address 8, you get it. And if we have a 4-byte value, then it has to fall on a 4-byte alignment. Address 0, address 4, address 8, you get it? And if it's an 8-byte value, like our int64, then it's got to fall within that full boundary, address 0, address 8. And so what we're doing is looking at the size of a value to determine what its alignment is, and then making sure that it falls properly in memory within those boundaries. So if I go back and we look at our example, and we draw that back up, what we originally said was, OK, here's our flag, right? That's our 1-byte. And then here was that counter, and that was 2 bytes. And then here was pi, right? And that was the 4 bytes. But we said this really isn't a 7-byte, 1, 2, 3, 4, 5, 6, 7. It's really 8. So let's start mapping this out by address. If the flag byte starts at address 0, which is quite possible, then let's go back to counter. Counter is a 2-byte value, which means it has to fall on a 2-byte alignment, which means its address has to be within a 2 bytes. So 0, 2, 4, 6, 8, which means that counter must start on address 2 if it's going to be properly aligned. It has to always fall within a multiple of 2. Well, that's interesting because if flag is 1 byte and falls on address 0, Well, what happened to the byte at address 1? That's our padding. This byte exists, and it unfortunately has to be skipped over. It's part of the value itself, but it's not used. The fact that we've got bool int16, and the fact that the alignment of int16 has to be on address 2, means that this byte here at address 1 gets skipped over. This becomes padding. Now you can see where you've got 1, 2, 3, 4, 5, 6, 7, 8. There it is. It's an 8-byte value. All right, now there's a couple things here before we make this a little bit more complex, okay? I always want to focus on optimizing for correctness, which means I don't care about padding right now unless it is a problem. And the only way padding could be a problem initially is maybe we've got so much padding in the struct that it's allocating much more memory than we want it to, and therefore maybe we've got a larger footprint in memory. But now we're talking about micro-optimizations based on a memory profile. How is that possible? Well, think about this for a second. What if I did this instead? Not int16, but int32. Now what do we have? Now what we have is not 1 byte of padding here, but now we have 3 bytes of padding here, because this now has to start on address 4. int32, 4-byte value, 4-byte alignments. Now you got 3 bytes of padding here. Hey, what if this is int64? Well, if that's int64, then what? Now this has to start not on 4, this has to start on 8, which now means we've got 7 bytes of padding here. You could see how something like this could add up very, very quickly. I mean, again, we're talking about micro-optimizations and nothing we would do during coding. But imagine we had a struct where size was important, and though the field names would have to be different, we did something like this. Now you've got 7 bytes of padding, and 7 bytes of padding, and 7. We've got an extra 21 bytes of padding or memory for a value of type example that we really don't necessarily need. Again, I want to optimize for correctness. So if this is a better way to look and read the struct, I'll take the 21 bytes until a memory profile is telling us we shouldn't. Now, if we truly want to micro-optimize the padding away, what we need to do is order fields from largest to smallest. When you order fields from largest to smallest, what that will do, I'm just playing around here just to give you that kind of visual clue. What that will do is reduce padding all the way down, if there needs to be any, to the bottom of the struct, because alignments are always going to find evenness throughout the struct. Because there's another part of this alignment equation, and that is a struct must also properly align based on its largest field. So this struct right now, its largest field is an 8-byte value. So there's also an 8-byte alignment that has to happen on the struct. There's going to be padding at the bottom of this structure right here. If I got rid of int64 and it was just int32, now the entire struct has to fall on a multiple of 4. Now it has to be a 4-byte padding. And so you've got that stuff too. But I promise you that if I see a struct that's laid out where the field from its largest size to its smallest size, that's going to raise a flag for me. I'm going to ask you, why are you pre-optimizing this struct right now? Do you have a memory profile? Do you have something that's telling you that we're using up too much memory? If the answer is no, I'm going to ask you to reorder the fields based on correctness. What is a better way to read it? Let's group things together that belong together. Instead of going right into this idea of optimizing for performance. And you might say, well, Bill, why doesn't the language do this for you? Because the language isn't going to go behind your back and make changes, because then we would lose our ability to understand the impact that we're having. You get to control your memory layouts. You get to make them as precise as you need them to be. And it's not the language's job to go behind the back and try to pre-optimize things for you either. There are some languages that might do that. Go isn't going to do that. So the idea, again, around understanding the size of a struct means we have to understand alignments and padding. And now we know that based on the size of a field, and this would be anywhere in memory. You don't really feel it until we get to the struct types. But our int16s have to fall on a 2-byte alignment. Our float32 has to fall on a 4-byte alignment. Our bools can kind of be put anywhere, and that can cause places for padding. So we really got an 8-byte value here. So on line 20, when we construct our E1 variable, value of type example, That's 8 bytes of memory cost. Now we know what that is. And I want to show you on line 27. What line 27 is showing you is how we do construction when we don't want 0 value. And this is going to be a very common syntax in Go. We're going to call this a literal construction. So here you're seeing literal construction of the name type example. We're initializing field, counter, and pi. You see the syntax with the colon. You also see a comma at the end of every line. Go is very much about convention over configuration. It's very opinionated here. Go funct is going to play a big role in your life here. And so these are opinions that you have. Whether you like it or not, this is the way it's going to be. You can see the use of the short variable declaration operator during this construction as well. And Go is not being novel. We're going to use the dot operator, value dot field, value dot field. Now you might see this in a lot of code in Go. You might see the use of literal construction to create a value set to its 0 value. There is nothing wrong with this. I don't do it again because I rather use var to show 0 value construction like I showed you there on line 20. Line 27 is also doing 0 value construction in this case, but what I tried to tell you before is just because literal construction here, literal empty construction here as it relates to struct is creating 0 value, that's not necessarily the case all the time. So I'd rather use var. But there's nothing wrong with that if that's what you want to do. Just be consistent. But in this code that we're going to go through, we're going to use a literal construction most of the time when we want to initialize to something other than 0 value. Okay? The only time you might see empty literal construction from me is when we're not assigning it to a variable. You might see it on a return. That will be absolutely fine. You might see it on a function call. That will be the exception to empty literal construction. But anytime we're assigning it to a variable, I'm not going to do that at all. Okay, so that's our basic kind of struct, our layout, our user-defined struct. But let's take a look at something that I think is a little bit more interesting. Go also has the concept of an anonymous struct. We'll call these literals in the language. And anytime you see a compiler message about a literal value or literal type, what we're really talking about is an unnamed type. So there are things in this language that are named, and there are things that are unnamed. And what you see on line 14 is us declaring a variable named eat1 based on the literal struct type. I can't give it a name because there isn't any. And we're using var, so again, it's set to its 0 value. You know, readability is about consistency, and you can start seeing how we're leveraging var to have a very consistent look and feel around 0 value. And you can see on line 21, I'm displaying the value of E1, which will all be set to its 0 value. And here what you're seeing is I'm doing literal construction. Actually, this is again type declaration. So we're declaring on the fly a struct. It's a literal struct. It has no name. And right below it, you now see the literal construction because we're not going to set it to 0 value. You'll see a lot of this in Go. These literal types can come in really handy for things like when you're doing, let's say, unmarshalling on a web API. A piece of JSON might come in. You have to do some unmarshalling. You need some type information, but it's not necessarily good to name it because it only needs to be used in this one place. And we don't want to name something we're only using in one place. That would be pollution. We get the ability to define these structs literally where they're needed and use them right then and there. It also really enhances readability. Since it's a struct, it is leveraged the same way. Okay, let's focus on this E2 struct here because or the E2 variable, because I want to talk about this as well. Let me take this struct declaration that we have, and let's do something very interesting. Let's go ahead and define 2 types. I'm going to have type Bill, and let's create a type named Alice. Now, I'm going to hit the format button so we can do this. I want you to notice something about Bill and Alice. They are really technically identical. They're identical and compatible. They have the same memory layout, the same field names, and ideally if I have a value of type Bill or Alice, I should be able to assign them to each other without any integrity issues, right? There are none. The memory layouts are identical. All right, so let's do the following then. I'm going to come back here, and I'm going to create a variable of type Bill and a variable of type Alice, both set to their 0 value. and then I'm going to go ahead and assign Alice to Bill. Now the compiler will complain if I don't use these variables, and it's the compiler again focusing, or the language again focusing on readability. Don't declare a variable if you're not going to use it. It doesn't help with readability. So I'm just going to display it. But here's the question. We know Bill and Alice are identical. We know they are compatible. I do this assignment, and it shouldn't be a problem. I know it. The compiler knows it. But look at what the compiler says. It says, sorry, Bill, but you can't use A as type Alice as type Bill in the assignment. I'm sorry, but we're not going to do this assignment. Now, there are lots of other languages that would have done this assignment. And when languages do this assignment, we call it an implicit conversion. We're going back to what Martin Thompson said about implicit conversion being like a Halloween special. Implicit conversion has caused a tremendous amount of pain for software over the decades. And no, it's not going to cause us pain necessarily with our struct types. Where traditionally it's caused pain is when B is an int, a signed int, and A is an unsigned int. And the compiler allows these signed and unsigned variables to be assigned to each other. We know now there's going to be a loss of precision, and therefore there's going to be data corruption. And so, though there are languages historically that have done implicit conversion when there is data that is identical and compatible, it's caused more problems than good. And Go says, look, when we're working with this concrete data, if the data is like this, Bill and Alice, right, we're based on these name types, I'm sorry, but I'm not going to do implicit conversion because historically it's caused more problems than good. But what if we really need to do this assignment? This is where conversion comes in. I love the idea of conversion in Go because what it does is it shows your intention. It's a way of telling the compiler, look, it is my intention that A does get assigned to B. And now there can't be any mistake. The compiler can't say, well, I thought you wanted to do this. No, 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 no. Now the compiler's saying, if you really want to do this, then you explicitly, not implicitly, explicitly tell me through the conversion syntax, show me that this was your intent. And there it is. We see conversion syntax. And now if I do this, yes, we're going to be able to compile through. This is a beautiful, beautiful piece of the language holding us and our code to integrity and holding us to responsibility when we're doing these types of assignments. But I've got an interesting question for you. We've got an E2 variable here based on a struct that also is identical and compatible with Bill and Alice. What if I go ahead and I put E2 here? What will the compiler do? Will the compiler allow this or still ask for conversion? Well, what you're going to notice is the compiler doesn't ask for conversion here. And now the big difference between A and E2 is that A was a name type, E2 is a literal type. When the type is named, there's going to be no implicit conversion. You're going to have to show your intent through conversion. But when the value like this isn't named, it's a literal type, now we have this flexibility on assignment. Now, again, it's kind of silly to do it with struct types. Ideally, you'll see this type of assignment with literal values when we deal with functions. A function in Go is a value. It's a literal value. It's not a named type. And we pass functions to functions all over Go, especially when we start talking about web APIs and middlewares and things like that. And so it makes it where it's not really cumbersome. So I love the balance that the language is giving us here. If we're dealing with values of a name type, there is no implicit conversion. You've got to use your conversion syntax. You've got to show your intent. When we're dealing with that literal type value, then we're going to get a little bit more flexibility. Well, it's not really implicit there so much as we know that these things are compatible. We allow it to happen, and everything is safe when we maintain these safe levels of integrity throughout our code. So remember that Go is not being novel here. The keyword struct is our core way of defining user-defined data in the language. We don't have the keyword class like you might have seen in other languages. We have struct. Struct defines that data. There's no implicit conversion when we start talking about this concrete data. Name types, we've got literal types, and the conversion syntax comes in handy here when we're talking about doing that explicit conversion, okay? And then we also talked about the idea that I don't want to optimize for performance here. We always want to optimize for correctness. If I go back to the first example, you can see I want the fields to be laid out correctly. In other words, readability first, grouping things together. But I want you to be able to understand the cost of things. And understanding how much memory is going to be allocated for a particular type helps you with understanding cost. And therefore, we talked about alignments. We talked about padding. And we talked about that only unless you have a benchmark that's showing you're using up too much memory, would I want to optimize that struct to minimize padding. I cannot stress this enough because I've had too many clients come in after this lesson and restructure everything to reduce padding to the bottom. Please don't do that. I'm teaching you this so we can look at cost in terms of allocation, not so we can restructure everything. Pointers. This is one of the most important sections we're going to have in the class. It's really going to help us learn how we can look at the impact that our code is having on the machine. Remember I said that performance or the lack of performance is going to come from four places. Sorry. One is latency around networking, disk I/O, that type of I/O. We're not going to really talk about that in this class. The second one was around allocations in memory and garbage collection. This is where we're going to learn how all of that stuff works. The third thing, again, was how we access data and eventually algorithm efficiency. But this is our beginnings of being able to understand the impact that our code is having on the machine as it relates to memory. So let's start with the idea that everything in Go is pass by value. And when I say pass by value, what I mean is WYSIWYG. What you see is what you get. And I want to give you an initial example of what we mean by pass by value and this idea of that the WYSIWYG allows us to truly understand the impact that our program is having. Now, before I could really dive into this code, there's a couple of things I want to share with you up front. We're going to talk in a much deeper detail when we get to the concurrency sections. But it's going to help us to understand the impacts here on this code and the things that we're going to be doing moving forward. So let's start with this. When your Go program starts up, it's going to be given a P or a logical processor for every core that's identified on the host machine. From a playground perspective, we're single-threaded. That is one core, or one P. And that P is given a real live operating system thread that we call M. I promise I'm going to be going much deeper into this stuff when we get to the concurrency sections. Don't skip ahead. Stay with me right here. And that M is going to still be scheduled by the operating system scheduler on a particular core. And we get one more thing from the runtime, and that is our Go routine. So there it is, our G. And if you've ever heard of coroutines before, Go routines or coroutines, it's just Go. We changed the C to a G. But that's it. Now, what's important here right now is the idea of a path of execution. Threads are a path of execution at the operating system level. All of the code you're writing at some point gets into machine code, and the operating system's job is to choose a path of execution, a thread, to execute those instructions one after the other, right? Starting from main, ba, 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 ba. That's the job of the thread. And the operating system schedules threads. But what's important here is the data structures now. Now, there's three areas of memory that we may talk about throughout the class. There's the data segment. There's stacks, and there are heaps. Now, the data segment's usually reserved for your global variables, your read-only values. I don't care about that so much today. What we're going to focus on is stacks and heaps. And the stack is a data structure that every thread is given. Now, at the operating system level, your stack is a contiguous block of memory. And usually it's allocated to be 1 meg. 1 meg of memory for every stack, and therefore for every thread. So if you had 10,000 threads, you can add that up. That's 10,000 megs of memory immediately being used out of the box. And this concept of a stack is coming to us all the way through the hardware. The hardware wants this stuff. It really helps simplify our programming models down there. And it's really going to help us, too, in our programming models, as we're going to see, again, to understand cost and what's happening. So since an M, or an operating system thread, is a path of execution, and it has a stack, and it needs that stack in order to do its job, our G, which is our path of execution at Go's level, G's are very much like M's. We can almost at this point say that they're the same, but this is above the operating system. A G has a stack of memory too, except in Go today, that stack is 2K in size, 2K. It was 4K for a long time. Today it's 2K. Notice how much smaller, and I mean significantly smaller, the stack is for a Go routine as it relates to an operating system. And that's important because we want to be able to have a lot of Go routines in our program, lots of paths of execution running. And remember, Go is focused both on integrity and minimizing the use of resources throughout the running program. And this is one of those areas where we're seeing that. So when our Go program starts up, we get a G. Our G is our path of execution. Its job is to execute every single instruction that we've written. The M is it's going to host itself on top of the M to actually get that happening at the hardware level. And what we have is this 2K stack. And this is what's important here. This is what we're going to be talking about. So by the time the Go routine that was created for this Go program wants to execute main, it's already executed a bunch of code from the runtime. Eventually it says, hey, I want to execute the main function now. We're ready. And this is what is going to happen. As the Go routine executes code and starts jumping between functions, this stack becomes critical to make all that happen. And eventually the Go routine says, I want to execute main. And anytime a Go routine makes a function call, what it's going to do is take some memory off the stack. We call this a frame of memory. So it's going to slice a frame of memory off the stack so it can now execute the code that you see here inside of main. And what I want you to understand right now is that in order to execute this data transformation, we have to be able to read and write memory. Remember, every line of code we write is either reading memory or writing memory, obviously also allocating at some point. It's doing those three things. And what's important here is that the Go routine only has direct access to memory. Let's think about this for a second. The Go routine only has direct access to memory for the frame that it is operating on. So it wants to execute main. This is now our active frame. Here it is. The Go routine is now executing within this context. And this is, for our purposes right now, the only memory the Go routine can read and write to directly. This is it. Now, what does that mean to us? What it means is if this data transformation has to be executed by the Go routine, and it can only operate within the scope of memory within this frame, that means all of the data that the Go routine needs to perform this data transformation has to be in here, this frame. And if we look on line 10, what we see is a variable declaration of count assigned to the value of 10. We basically are now going to be allocating our 4 bytes of memory right here inside this frame. It has to be inside this frame because if it's not, the Go routine can't access it. Understand that this frame is serving a really important purpose. It's creating a sandbox, a layer of isolation. It's giving us a sense of immutability that the Go routine can only mutate or cause problems here and nowhere else in our code. This is very, very powerful constructs that we're going to want to leverage, and it starts to allow us to talk about things like semantics. You're going to hear me use the word mechanics and semantics. When I talk about mechanics, I'm talking about how things work. When I talk about semantics, I'm talking about how things behave. And the semantics are going to let us understand what the behavior is, the impact we're going to have. The mechanics are going to allow us to visualize and see how all that works. We need both. The semantics, though, are very, very important and powerful. And what we're looking at so far here is that we've created a value of type int. Its value is 10. It has been allocated or created within the frame here because this is the only place the Go routine can operate in terms of memory. Now on line 13, we're doing two things. I want to bring everything back to English. And on line 13, what you're going to see is that I'm asking us to display the value of count. Anytime I use the variable's name, I want us to think value of. What's in the box? And over here, you can see I'm using the ampersand operator. Ampersand operator isn't unique to Go. Many programming languages have used it, and it usually means the same thing. Address of, where is the box? Hey, if you got a box in memory, it's got to be somewhere. Now, we're going to be using hexadecimal numbers for this, and we only have to worry about looking at the last 4. So I could pretend that this is an address F1BC. Again, we're using hexadecimal numbers because it's just more efficient when you have these very large numbers, which are addresses. OK, so value of what's in the box. That's the variable and only the variable. Ampersand variable. Address of where is the box. It's got to be located somewhere in memory. It's going to be a memory address. There it is. Now, I want you to look on line 16. On line 16, we're about to make another function call. I want you to think about this for a second. Every time you make a function call, what we're really doing is crossing over a program boundary. Program boundaries are important to identify because in this case, this program boundary, this function call, means that we're going to be moving out of this sandbox or frame, and we're going to be moving into a new one. Every time we call a function, what's going to happen is we're going to slice a new frame off the stack. This is now going to be the active frame. Our Go routine is now going to be operating within this sandbox, this level of isolation, which once again means that if we're going to execute this code inside of increment, if we're going to perform this new data transformation, then the data the Go routine needs to perform this transformation better be inside of this frame because this is the only place we can operate in. And this is where the idea of parameters come from. We have been using parameters our whole programming lives. We've learned about API design. We've done all of these things. But I want to show you the mechanics behind it, because without the mechanics of parameters, we wouldn't be able to encapsulate it all. So these parameters are really serving a mechanical purpose on top of our design purpose. And that is to get data inside of this new frame so the Go routine can operate this new data transformation in a level of isolation with a level of immutability. And so what we're doing on line 16 is passing the value of count across this programming boundary. And because everything in Go is passed by value, what that means is that we're going to make a copy of the data as it goes across the boundary. Now you're going to hear me start using three different terms. You're going to hear me use the word data. And data is what we're working with, concrete data. If you don't understand the data, you don't understand the problem. But there's two types of data that we operate with. It is the value itself, like this integer value 10, or it's the value's address. Yes, addresses are data, and I want you to always understand that. And in this case, what we're passing across the program boundary is the value itself, which means we're making a copy of the value, the 4 bytes. We're going to throw it over this program boundary, which means that those 4 bytes have to end up now inside this frame as well. This is where your parameters come from. And so this parameter we're declaring inside of int. What that is there for is to capture or hold that value we're throwing over the program boundary so the Go routine can operate this data transformation. So this becomes inc. And pass by value means we make copies and we store copies. There it is. Now the Go routine can operate within this function right here, which it is. And on line 27, what you see is a read, modify, write operation, line 27, inc++, which means that we are now mutating memory, but we're mutating it right here. What's really important is that this frame is allowing the Go routine to mutate memory without any cause of side effects throughout the program. The memory mutation is happening in isolation within our sandbox with a level of immutability in the sense that we don't affect anything else outside of this execution context. This is a very, very important and powerful mechanism. And what we're really seeing here is what is called value semantics. We're going to focus a lot in this class on the value and pointer semantics behavior that the language gives you. If you want to write code in Go that is optimized for correctness, that you can read and understand the impact of things, then your value and your pointer semantics are everything. And what we're looking at here is an example of value semantics. There's a value here in main for count. Now we operate a different transformation around that data, and that means that every data transformation, every piece of code that's operating on it gets its own copy of the value. This is value semantics. It's very, very important. And value semantics has the benefit of, again, this idea of isolation and mutability. It's going to also potentially, in many cases, give us some performance. We're going to talk about that. But I told you engineering is not about just hacking code. It's about knowing the cost of things. Everything has a cost. Nothing is free. And so the question now is, what is the cost of value semantics? One of the costs of value semantics is that we have multiple copies of the data throughout the program. There is no efficiency with the value semantics, and sometimes it can be very complicated to get a piece of data that's changed and to get that updated everywhere it needs to be. So our value semantics are very powerful semantics because it's going to reduce things like side effects. We'll talk about that. It's giving us isolation. It's giving us these levels of immutability that are so important towards integrity. But sometimes the inefficiency of value semantics might cause more complexity in the code. It might even cause some performance problems, and performance does matter. And one of the things we've got to learn is how to balance our value and our pointer semantics. So right now, all we're looking at here is the value semantics. When the increment function returns, and we're back up in main, now what's going to happen is this go routine is no longer operating in this active frame. This is now our active frame. The go routine is now operating here. And if I were to run this program, what we're going to see is that mutation that we made got isolated here, did not carry up or forward. Now this piece of code is still operating on its own copy. This was operating on its own copy. We got the benefit of this mutation not affecting anything else. This is value semantics, and this is a big part, again, of the beauty of the pass by value. What we see is what you get. So we just looked at our value semantic example, but let's imagine that what we really wanted is not the go routine here operating in its own sandbox and its own copy. Let's say what that next data transformation, what it really needed to do was manipulate the memory here, which was going to be in the frame above us. Now what we need is pointer semantics. And pointer semantics serve one purpose, and that is to share a piece of data across a program boundary. Sharing. If you don't need to share something, then you don't need a pointer. You don't need the pointer semantics. And this is where the pointers are really going to come in. Let's take a look at the mechanics around sharing and then continue to talk about the benefits and the cost of pointer semantics. And we'll try to continue to bring all this stuff together as we go. So let's go back to our original program. Let's come back here again. We're going to clear our stack right here. Here we are. And we've got our stack. And we're operating in main. And main has its variable count. And we can get the value of count. We can get the address of count. But this time on line 17, we've done something different. I'm not passing the value of count across my program boundary. I want you to notice that what we're passing is the address of count. Now you might think that this is what's called a pass by reference. Lots of people say that this is a pass by reference. It really isn't. Remember, pass by value means WYSIWYG. What you see is what you get. Pass by value means that we're making copies of data as we cross over program boundaries. This is a pass by value. It just so happens that the data we are copying and passing is not a value, it's an address. And I need to stress again that addresses are data. So since we're going to make a copy of count's address and pass that across the program boundary, we need to store an address. Guess what? This is what pointer variables are for. Pointer variables are not special. They aren't. They serve one purpose, and that is to store addresses, our address data. Now, if you look at the declaration of the parameters for increment, you can see now that we've added this operator called star. And the star operator is allowing now us to declare the pointer variable. I want you to understand that pointers are literal types. Remember what I said before in the other section? We have name types, we have literal types, unnamed types. And pointers are literal types. You can take any existing type, like name type int, put the star in front of it, and you've just now identified the literal pointer type for that. And what that means is changing everything. Int is no longer representing an integer. Int is now representing the ability to store an address. All right? That's what we're going to be doing. And that address is going to point to something. In this case, what we've done is we've taken the address of count and we've passed that across the program boundary, which means that is what we're going to be storing in this box, that address, which now means that we're able to point to a piece of data outside of our frame. Pointers are for sharing. Pointers are confusing because of that star. The star dictates that this is now a pointer variable. It's always 4 to 8 bytes of memory, depending upon the architecture, the size of an address, and that is what we're storing. But this is very important. You might think, well, Bill, if the star is what's dictating the variable's type, which it is, why can't we just say star? I mean, it's the star that's dictating this is a 4 or 8 byte value. It's the star that's dictating this is a pointer variable and what's going to be stored. You're right, except for one thing. It's not enough to just store the address. The whole reason for storing the address is because we want to manipulate, read and or write the memory that that address is locating us to. In this case, this count. And I told you before, you cannot read and write to memory unless you understand the memory's type. You must understand the size and the representation of this memory. Type is life. So we can't just say star. We've got to say star int. What I'm saying is I want an address. Absolutely no pause. I need an address. But guess what? Can't just be any address. It has to be an address to an integer, because I want to read and write integers. And we're going to get that type safetiness. The compiler won't let me pass any address, only addresses to values that are based on the integer type. There we are. And then what you see on line 28 is the use of the star operator. Again, this can be confusing. Remember, the star is being used during type declaration. Now it's being used to say one thing. Remember, we're going to put everything in English. Use a variable by itself, its value of what's in the box. You take ampersand variable, address of where is the box. And if you have a pointer variable, then the star says the value that the pointer points to. And what we call this is an indirect memory read or write. What you see on line 27 is an indirect memory read and write, a read, modify, write operation through pointer indirection. Remember I told you that the Go routine only has the ability to directly read and write to memory within its frame. Now when we made this call, this is no longer the active frame. This is now the active frame. The Go routine is operating within this sandbox right here. And now what we're able to do is say this. The Go routine still performs the direct memory read. Even though this is now still the active frame, right? Remember again, this is our active frame right here. Our Go routine is operating within this sandbox right here. And in order for this Go routine to be able to access anything outside of its sandbox, it still must perform a read of the address. Remember that the Go routine only has direct memory access to the frame. If you want the Go routine to be able to access memory outside of the frame, you must share the address of that memory location to it so it can be done in a safe way. And so now on line 28, what we have here is an indirect memory read, modify, write over here. And now what we're able to do is modify that memory outside of our frame. The pointer gives us this capability. However, there's a huge cost to pointers. Remember now, we've just walked away from our mutation isolation, our immutability. What we've done is set ourselves up for what we call side effects in our code. When we start mutating memory, we have to be very, very careful. But if we're mutating memory within the scope of value semantics, we're good, we're clean. We can't cause problems anywhere else except for ourselves. But when we start mutating memory around pointer semantics, we have to be very careful. Because at some point, we are going to return from this function. We're going to move out of this program boundary. And we're going to move back into this program boundary. Again, this being the active frame, this is where we're operating on. And when we come back, we may not have realized that the Go routine or some other Go routine in a multi-threaded piece of software has gone behind the scenes and has mutated this data. It's not necessarily clean anymore. It's dirty. And if we're not aware of that, this can cause huge side effects. And in multi-threaded software, it could cause data races. Functional programming languages try to reduce the side effects by not giving you pointer semantics at all. Everything is value semantic. But remember, the cost of value semantic is inefficiency with the data. There are times where it's just more efficient, simpler to have one piece of data and that's it, and share it across your program. We're going to continue to talk throughout the class when to use value and when to use pointer semantics, I promise you. Right now we're still very focused on mechanics and some base semantics, but this class is going to, over the course of time as we continue to go forward, try to teach you when to use one semantic over the other. There's just still more that I have to teach you. And so as I run this program here, you will see now that on the return, we've mutated the memory in the frame above us. And now when we come back up, we now see that mutation. This is technically a side effect. We have mutated memory outside of our isolated space, our safe space, and have mutated something out here. This is going to require a lot more care. And you can see here that now that we're here, it's all done. Now there's one more thing I want to talk to you about as it relates to what we've seen here. I keep drawing for you the active frame. One thing that's very important is I want you to come to the realization that any memory below the active frame is not valid memory. None of this memory is valid. If you notice that we've been working the stack down, now that is a silly implementation detail. They could have done it any other way, just historically this is how it's done. But I want you to understand that as we make function calls, we are going deeper into the stack. As we return, we're coming back up the stack. There are stack and frame pointers that allow us to identify where the active frame is. And in this case, what I want us to understand is that anything below the active frame, this memory is no longer valid. It's no longer in play. The active frame and memory above is always got a level of integrity because we can continue to go up, but going down causes problems. Remember, we have the concept of zero value, and zero value is a very powerful concept in Go. Think about it. I'm back up in main right now, right? We've done this mutation. But what happens when main makes another function call? When main makes the next function call, it's going to need another frame. And when it takes that frame, it's going to clean it up. This is why I want to stress that memory below the active frame no longer has integrity because it's going to be reused. So we want to keep that idea as well as we continue to learn about our value and our pointer semantics and these stacks. All right, so we just looked at the base mechanics for value and pointer semantics. These are going to be very important going forth. Again, I want to make sure that we can read code in Go and understand the cost and the impact that code is having. Memory is going to be a big part of that. Now, there's a big thing here around these semantics and value semantics and the pointer semantics, and it's the cognitive load around understanding how to manage memory. One of the most beautiful things about Go is it takes that burden off of us, where we don't necessarily have to worry about things, because we make a mistake with where things are located and how we access it. It can cause very, very big problems for us. So our value and our pointer semantics are going to be big for us in order to be able to read and understand how things behave. And again, let's talk about that again. Value semantics have the benefit of being able to mutate memory in isolation within our own sandboxes. But it has the cost of inefficiency. We're going to have lots of copy of the data as we cross over these program boundaries. Pointer semantics, however, fix the efficiency issue. We're just going to have one piece of data. We're going to share it. Everybody, if we mutate it, everybody's going to see it. But it comes with the cost of side effects and a lot more work for us to make sure that we're not corrupting data or that things aren't being changed behind the scenes without a piece of code or a Go routine later on knowing it. This is complex stuff. I'm just not going to hide it for you. But if we balance our value and our pointer semantics properly, leveraging the aspects of the language helping the cognitive load over memory management, it's going to be a lot better for us. So I want to show you another example here of these semantics and how the language is really here helping some of our cognitive load. And this is also going to be important in our ability to understand the impact and the cost our code is having on the machine. So I've got a user-defined type here. It's username and email. And what I do is I have two functions, one called createUserV1 and one called createUserV2. Now, as I shared before, we don't have constructors in Go. Yay, we don't want that, right? It hides cost. But what we do have is what I call factory functions. Factory function is a function that creates a value, initializes it for use, and returns it back to the caller. This is great for readability. It doesn't hide cost. We can read it. And it lends to simplicity in terms of construction. Now, I don't want to call these functions constructors because that's baggage. I call them factory functions. And I've got two factory functions in this piece of code, version 1 and version 2 of the create user. Let's start with version 1 of the factory function. Now, the first thing I want you to do is look at the return type for the function. It returns a value of type user. Immediately, that clues us into the understanding that this factory function is using value semantics. Throughout this class, I'm going to ask you, what semantic is in play? This is critical to everything, as you will see. And when we talk about V1, value semantics are in play because the caller is going to get their own copy of the value after this function returned. Now, if we were to map out visually how this function is behaving, we would probably think that this is what's going on. We're in main. Now we call V1. There it is, version 1. And right away in this function on line 25 through 28, we have literal construction. We're constructing a value of type user using our literal construction. We end up with a variable named u and a value that has at least Bill inside of it. There it is. We're seeing construction. And right now I'm drawing it within the frame that the active Go routine. Here's our active frame at this point. Our Go routine is operating within this frame right here, and we do the construction. Now I want you to look on line 30. The ampersand operator is very powerful from a readability standpoint. Ampersand means sharing. And now when I read line 30, what I see is we are sharing the user value down the call stack to the print function. At that point, we have another frame for print, and we see here that we are sharing that value down the call stack. Now when print wants to display it, it's going to do it through an indirect pointer here. It's doing it through indirection, but it's OK because when this is the active frame, remember all of the memory associated with the active frame up is valid. This is perfectly clean to share that pointer down. Life is good. Eventually, this is going to return. This is going to be the active frame again. Our Go routine will operate on here. Life is good. And then on line 32, notice that we're doing a return u. This is the value semantic call, right? We are making a copy of u and passing it back up across our program boundary, back up the call stack, which now means that when this Go routine is now operating here, here's our active frame, here's our Go routine right here. This Go routine now is operating on its own copy of u. There it is, Bill, which is fine because, again, that memory that we were using below the active frame, we didn't need it anyway because we're operating on our own copy. This is classic value semantics, and you can see the levels of integrity we get because the Go routine is operating on its own copy. It's again operating on its own copy. We did make a copy of it, but this is now the point of truth, and we don't care about anything that's happening below. Again, we can't worry about this data here, and it doesn't matter because when main makes another call, it's going to wipe out all of this data. None of this. This is all basically ready for use again. But we're seeing our value semantics pretty strong here. Now let's look at version 2 of this piece of code. If you notice here, version 2, look at the return. It's not using value semantics anymore. Version 2 is using pointer semantics. Notice what it's saying is it's going to give the caller a copy of the address that we are constructing. This is very common stuff to do in Go. Let's draw out what this looks like on the board and get a sense of what's happening here. So I'm going to clean up my stack right here. We're going to have our main right here. We're going to have version 2. Now, this code looks identical to version 1. There's a couple subtleties, but it really kind of looks identical. Look on line 39 through 42. It looks like we're performing the same exact construction. It looks like we're constructing a value of type user, initializing it to Bill. We're sharing it down the call stack again. Again here, this is our active frame. Our Go routine is operating right here. We share it down the call stack again like we saw before. We're going to share it. The active frame was here. We come back up. But this time on the return, we're not making a copy of the value. We're making a copy of the value's address. Again, passed by value, where the data is either a value or an address. Now, it looks like, from reading the code on the surface, this is what we're going to end up with right here. Now, if this was truly the case, we would be in a tremendous amount of trouble. Think about what I've just drawn on the board. As we perform the return and share the value up the call stack, and once this becomes the active frame, this is a very, very bad scenario. If this was really happening, we'd have an integrity issue. Because when main makes the next function call, it's going to take a frame, and it's going to wipe all of that out. Oh my goodness, think about it. When we share up the call stack, what we're doing is basically putting ourselves in a situation where the pointer is pointing to a piece of data that can be corrupted. Side effects. Oh my God, this stuff gets very, very complicated. So this absolutely cannot be what is happening, and it's not. And if we didn't have the compiler coming in and dealing with this, this is something that you would have to deal with as a developer, which is why it's so complicated and we've made so many mistakes in the past. So what's happening here is the compiler is really, really powerful. The compiler is able to perform static code analysis. And in this case, what the compiler will do is perform what's called escape analysis. And this static code analysis, called escape analysis, will determine whether a value gets to be placed on the stack, which is what we want, or it escapes to the heap. Notice that our first priority is that a value stays on the stack. And this is because that memory is already there. It's very, very fast to leverage the stack. Also, stacks are self-cleaning, which means that the garbage collector doesn't even get involved until a value escapes the stack and ends up on the heap. And in Go, that is what we call an allocation. An allocation in Go, it was an escape analysis determines that a value cannot be constructed on the stack, but has to be constructed on the heap. Because to keep it on the stack, like in this particular case, would have an integrity issue. And now the garbage collector has to get involved with anything that allocates to the heap. Now you might be saying, Bill, why does the garbage collector not have to deal with stacks? How are stacks self-cleaning? Let's go back to zero value for a second. Remember, every time we make a function call, we take a frame and we clean it. Zero value helps to make sure that every single byte and every single bit is set to where it's supposed to be. There's nothing left random. You make another function call. What happens? You make another function call, we take another frame, we clean it. Take another frame, you clean it. See, stacks are self-cleaning because as you make function calls, the stack is being cleaned all the way down. But as we come back up and return, we leave that memory. It would be inefficient to clean memory on the way up because we don't really know if we need it again. We'd have to have some level of efficiency. So memory is left alone on the stack as we go up and cleaned on the way down. So the garbage collector doesn't have to get involved. The stack can give us a tremendous amount of performance because the memory is already allocated and it's self-cleaning. We really want to try our best to leverage our value semantics and to keep values on the stack because, again, one of the benefits of not only is the isolation and the immutability and the reducing of side effects, but in many cases can also give us some better performance. Because once something is allocated, the garbage collector has to get involved. And again, we've got to learn how to balance our value and our pointer semantics. So if none of this is happening with the code I just showed you, what is happening? This is one of the most beautiful things about Go. The Go syntax abstracts away the machine. It's really powerful, very, very interesting. It abstracts away the machine so you don't necessarily have to care where data is. But when performance starts to matter and debugging starts to matter, it does begin to become important to understand the escape analysis and where things are. So let's walk through this code with the understanding of what's really happening thanks to escape analysis. So I've got my stack. I've got main. We're now in V2. And suddenly what happens during construction on line 39? Well, the way escape analysis works is it doesn't care about construction. Construction in Go tells you nothing. What tells us everything is how a value is shared. Sharing tells us everything. And because of line 46, the sharing of the value up the call stack, that's going to clue us in that escape analysis is not going to construct you, user, on the stack, but it's going to go and construct this user value out on the heap. Interesting. Construction is happening immediately on the heap. Now, what gets super interesting to me is this. U represents a value of type bill, but it represents a value of type bill that's not on the stack frame, but on the heap. And what we know is that if you want to access any sort of data that doesn't exist inside your frame, remember this is the active frame, our Go routine is operating here. If you want to access anything that is not on this frame, you can only do that through a pointer. This is really amazing stuff. From a syntax perspective, U is a value on the heap. You get to keep your code simple by manipulating the U value through your value semantics. However, underneath the covers, the compiler knows, well, I've had to have that escape. So even though the syntax at the coding level is a value of type U, we'll convert that underneath to a pointer to be able to access the heap value. How cool is that? The syntax and the language is abstracting the details and that cognitive load from you. But it's important to know that what we're really working with, U, is truly a value on the heap that you get to work with as a value and not as a pointer, which historically you'd have to deal with yourself. Now, when we share U down the call stack, we're making a copy of that heap address. And when we get to the return on line 46, we're making a copy of the heap address, whatever that was. And so we no longer have an integrity issue. When we're now back up here as the active frame, all right, and this is our Go routine now, well, it doesn't matter. None of this memory, again, is in play. It's invalid, but it doesn't matter because we have a pointer to the actual value that's out there on the heap. Yay, but there's a cost to this, right? And that cost was an allocation. This value now is out on the heap, and now the garbage collector has to manage it. So there's a guideline here that I want to provide because the ampersand is a very powerful readability operator, and you don't want to walk away from it. I mean, let me ask you this question. If this is the only code that I showed you, I'm zooming into the return here. If this is the only code that I showed you, return ampersand U, what do you know already based on what I've taught you? You know that there is a cost to this line of code, because even if you don't know what U is, you now know that it's potentially on the heap. In fact, it's on the heap. It's being shared up the call stack, and therefore escape analysis is going to say allocation, which now means the garbage collector. You know the cost of this line because you can read it, ampersand U. But what if I show you this? What if I get rid of the ampersand? Now what does this line of code share with you? The answer to that question is it tells you nothing. Nothing. It doesn't necessarily tell you anymore what the cost is. You have to be able to read the rest of the code. We just walked away from some readability because I have to read all of the code to understand the cost. Why? Because I can do this. And for me, this is clever code. This time during the construction, I'm telling the compiler, I don't want U to be a value of type user. I want it to be a pointer to the value that we are constructing. This to me is a total nightmare. We are using pointer semantics during construction, even though we're creating a variable, and now we've made this code much harder to read. And we're really also mixing semantics as we go along the way. Anytime you mix semantics, we're going to have a problem. So here's a general guideline. I never want to use pointer semantics during construction. I want to use value semantics during construction if you're going to assign that value that you're constructing to a variable. So we can leverage the highest levels of readability in Go. We can show sharing down. We can show sharing up. You can do your own escape analysis. When we do this, we're walking away from readability. The only time I want you to use pointer semantics on construction is if you're going to do that on a return. OK, we're not assigning it to a variable. We're doing it on a return. Or again, you're going to do it inside of a function call. We're not assigning it to a variable. We're doing it within the scope of a function call. That's where that syntax makes sense. But if your goal is to assign a value you're constructing to a variable, please use value semantic construction. Construction doesn't tell you where something is in memory, only how you shared. So if you start the life of a variable as a pointer, you're walking away from readability, and you're walking away from this idea that construction tells you nothing. This is what we really want to do. And you want to see some really nasty code. We talk about mixing semantics. Imagine you saw code like this. And I've seen this before. This stuff really makes me cry. Look, we're using value semantics on the return, pointer semantics on line 39 on the construction, and you're going back to value semantics on line 46 because you've got to get back to it. And what's really interesting about this code is that value never escapes the heap. We're using value semantics, yet your code is using pointers. I want to just duct tape my head when I see this kind of stuff. This is not good. So we want to make sure that we're using the right semantics and semantic consistency all of the time. We don't want to construct values to variables using pointer semantics. We want to leverage the ampersand in the right place. Now what's also very powerful here is you're going to use Go build to build your binaries. And when you use the GC flags on the Go build calls, and we'll do this as well when we're on Go testing later on, but when you use these set of flags on building and testing, what you're going to get is not a binary, but what we're going to get is the escape analysis report. We're going to come back to this during profiling because I want to show you how powerful it is to have this report, because when we look at a profiler, it can only show us what is allocating. It can't tell us why. This report tells us why something is allocating. So I don't want you using it while you're coding. We're going to use this as it relates to profiling. But notice down here, what it basically tells us is that we're moving you to the heap, and it's because of the return. Again, the return is causing a share up the call stack, which means you can't leave it on this frame, because once we come back here, this is the active frame. It has to escape to the heap. We now have an allocation. We now need garbage collection involved. We just started learning here now how that escape analysis teaches us when something allocates or not. How something is shared will determine whether it allocates. Now there's another part of allocation in Go, and that is that if the compiler doesn't know the size of a value at compile time, it must immediately construct it on the heap, because those frames that I've been drawing for every function are sized at compile time. Frames are not dynamic. So if the compiler doesn't know the size of something at compile time, it cannot place it on the stack. Now the compiler knows the size of a lot of things at compile time. It knows your struct types. We already learned how to read that. Your built-in types, other types that we're going to be using. But sometimes you might have things like collections that are based on their size is based on a variable, in which case the compiler has no idea what the size of that is, and we're going to have automatic allocations immediately. So that's the other place where you might have an allocation in Go. Compiler doesn't know the size of something, automatic allocation. But we talked about these stacks in Go being very, very, very small. That the operating system stack is about 1 meg, and your Go stack is 2K. So what happens when you've got a Go routine that's making lots of function calls, and eventually it runs out of stack space? What's going to happen? We can't just terminate the Go routine like we do with a thread, and we won't. Remember, Go is about integrity first, and it's about minimizing resources second. We always want to try to reduce and minimize the amount of resources that we need. We're all on cloud computing today. Shared resources are important, and that 2K stack is a big part of that. But When we run out of stack space, what we need now is to get a new stack. This is something for me that's very unique from a programming language. I'd never seen this before. Basically, imagine that we had our stack and we had some value there, and imagine we were even sharing this value as we move down the call stack. Eventually, we run out of stack space. What Go does is it has what are called contiguous stacks. And what it's going to do is allocate a larger stack, 25% larger than the original one. And then what it's got to do is copy all these frames back over. In this case, these pointers are relative, so they're very fast to fix. But basically, that Go routine, during the function call, we're going to take a little bit of this latency hit on creating the larger stack, copying those frames over, and readjusting any of these pointers. We do this in Go. We take this hit, 1 for integrity and 2 to minimize resources. I told you nothing is free. Integrity and minimizing resources come with a cost. But this isn't something that's going to happen all of the time. 2K is usually more than enough for our stacks, because you usually don't go more than even like 10 function calls deep. You don't. And there's other optimizations the compiler can do to keep these frames very, very small. So this is a very good trade-off and balance. But this can happen. And what this is telling us is, which is again really unique for me, is that values on your stack can potentially be moving around. This is a whole new world. I mean, I'm going to show you an example of this right here, a little piece of Go. I've got a constant of size 10. And here's my main, right here. Here's main. And we're constructing a string value. There it is. It says hello. And then I'm going to share this string value down the call stack. You see that on line 14. But what I've also done is allocated an array. And arrays, we know the size of an array at compile time. It's part of built into the array. This is a 40-byte array on the playground. An integer is 4 bytes. I have 10 of them, 40 bytes. And this array is going to be placed on the stack frame. Still going to keep the stack frame small. But stack copy is a recursive function. It calls itself over and over and over again, constantly sharing the string down the call stack. Now, if I run this for 10 function calls or 10 iterations, you see that the address on every iteration of the string inside of that frame for main hasn't changed. Beautiful. Our 2K stack is large enough to run this program without any issues. But what if I change our 40-byte array to be a 4,000-byte array? Whoa. Remember, we only started with a 2K stack. That means on the first call to stack copy, we're going to get some growth. That also means that that 25% is only going to go so far. And we're going to see more growth as we run this program. Watch what happens now when I run this program. What you'll see is, honestly, this is already a new stack location. But look on index 2. On index 2, we also have a new address, 55FA0. We have another new stack. In fact, if you look on index 6, we've done it again. Why? Because this 4K array is being kept on the stack frame because it doesn't need to escape. Remember, escape analysis says we want to use the stack, and using the heap is an exception when there's integrity. Here's a classic case of there is no escape. But you can see that the stack has grown several times. So cool. We're having the ability to start with very small stacks, which means we can have lots of Go routines, and the stack grows when it needs to grow. But think about the side effect that we have here. Since a value can move in memory that's on the stack, this actually creates an interesting constraint for us in Go. What this means is no stack can have a pointer to another stack. Imagine we had all of these stacks all over the place, hundreds of thousands of Go routines with pointers to each other's stacks. That would be total chaos if one stack had to grow. Think about it. If this stack had to grow, we would have to track every pointer that points to this stack and update it as well. You want to talk about stop the world latency, that would be insane. So one of the constraints or engineering choices here in Go is, since our stacks can move, it means that the only pointers to a stack would be local pointers. Only that stack memory is for the Go routine and the Go routine only. Stack memory cannot be shared across Go routines. Again, this is where the escape analysis comes in the heap. The heap basically now is used for any value that's going to be shared across Go routine boundaries and any value that can't stay on the frame because there's an integrity issue, or any value where we don't know the size at compile time. These are our 3 constraints around allocations in Go. And again, it's because we want to really be able to have hundreds of thousands of Go routines, which means we need to be able to have hundreds of thousands of stacks. We couldn't do that if they were a meg. They have to be as small as possible. We take the small hit always for integrity and for uses of small memory usage, because that is our higher priority in Go. What we care about is not that our code is the fastest it can be. We care about, is it fast enough? Now that we've really learned how the stacks work in Go, our next step is to understand the heap a little bit more and really garbage collection. Remember I told you performance is going to be lacking from latency on network and disk I/O, and number 2 was going to be on allocations and the garbage collector. So let's learn about how the mechanics around the garbage collector, and we'll talk about some guidelines around that that we really should be following as we learn more about how memory works here and we start writing more code. So the big thing about the garbage collector right now is that we call it a tricolor mark and sweep concurrent collector. One of the big things is that it's not a compacting garbage collector. Memory on our heap does not move around, which is again interesting because memory on our stacks potentially are. Once an allocation is made on the heap, it stays there until it gets swept away. But the tricolor is a mechanism, we'll talk about how that is, and that it runs concurrently is also very, very important. And it's something that we asked the language designers for a long time. Give us a collector where our Go routines can run at the same time memory is being collected. And they were able to do that. But again, nothing is free. One of the costs of having a concurrent collector is still some stop the latencies, or some stop the world latencies. But the idea is to reduce those points of stop the world down to their very bare minimum. So let's start here with the pacing algorithm. Everything begins and ends with the pacing algorithm. So the garbage collector has an algorithm. It's the pacing algorithm. And what the pacing algorithm is trying to do is balance 3 things. And it's just amazing. I mean, I'm not a PhD in any of this stuff. There's tons of documentation here if you want to go deep. But it's trying to balance 3 things in Go. What we want is the smallest heap size, right? Again, we're talking about reducing memory. How do I get the smallest heap size where the garbage collector can run at a reasonable pace to do that, where our stop the world latency is never more than 100 microseconds per run. Now, the total garbage collection time will be longer, but we don't care about the time where we're running concurrent. We care about the stop the world time. But there's also a cost to that. In order to do that, the garbage collector is allowed to take up to 25% of your available CPU capacity. All right? Doesn't necessarily have to, but it's allowed to depending on what's going on in your app. This stuff is very, very complex, but let's go back through it again. How do we maintain the smallest heap size, run at a reasonable pace where the stop the world latency time is under 100 microseconds, okay? And we're able to even leverage less than or up to 25% of your available CPU capacity. Well, let's talk about the CPU capacity cost for a second. This is a little bit more complex than what I'm going to draw, but it gives you a general sense of where that 25% could come from. Imagine you are on a machine with 4 cores, which now means that you have 4 Ps, which now means that you've got a 4-threaded Go program, because we can put a thread on every core and we can run 4 threads in parallel. Now, let's say you were running a web service where you've had 10,000 Go routines being distributed across all of your Ps, right, your execution contexts, and they're all working. So where could the 25% come from? The garbage collector uses Go routines as well. I mean, Go is written in Go, the runtime and the compiler. So the garbage collector is going to use Go routines as well to get this work done. So one scenario could be, and we'll see it's a little more complex when we get into tracing, but one scenario could be the garbage collector says, I want this entire P to myself, which means all these other Go routines will be distributed there, and all of the garbage collection Go routines we'll now leverage this 1p. That would be 25%. A garbage collection just took 25% of your entire available CPU capacity, which means that the garbage collector Go routines are leveraging this core, and you could still run 3 Go routines in parallel at the same time while this is running. So that's a general sense of where that constraint comes from, right? And there's different types of garbage collectors, and each one has their own thing where you want the garbage collector to maybe run at a high level of performance to get done quickly. Go is about the lower latency, and we all just run together, and we do things at a very constant and consistent pace. Okay, great. So there's our 25%. Now, when the pacing algorithm wants to run, what it's looking at right now is both our size of our heap and our live heap. So let's talk about that. So imagine that you start your program, it comes up, and let's say Go decided that we're lucky enough where we only need a 4 meg heap. That's it. It's not unreasonable, 4 meg heap. The heap sizes in Go are at a meg level of granularity. Well, let's say that in your Go program that's a 4 meg heap, you've got 2 megs of memory here that is pretty persistent. Maybe this is some map, it's a caching system, things you're doing. That's memory you've allocated, it's not going anywhere. That would mean that the live heap, okay, we have a line for the live heap, is at 2 meg. Now this is what the pacing algorithm is going to be dealing with here. The size of your heap and the live heap. Again, we're trying to maintain the smallest heap possible at a reasonable pace so the stop the world latency maintains itself at 100 microseconds or less. So what's going to happen as your program's running? As your program is running, the live heap is moving close to the top of the heap. At some point, if it gets close enough, we have to bring it back down. I said close enough. We can't let the live heap get all the way to the top of the heap, because if we want to run concurrently, that means that we would blow by it. And any time the live heap has to go beyond the scope of the size of the heap, there's one configuration option in Go called GOGC. And the default for GOGC is 100, and that means we're going to have 100% growth on that heap when the live heap has to go by it. So we want to really maintain or stop that from happening to the extent we can by having consistency in our app through allocations so the pacing algorithm can maintain this balance. Again, trying to balance all 3. So hopefully it gets close to the top of the heap, and then the pacing algorithm runs and it comes back down. And it's quite possible that we might run at like a 1 millisecond or maybe 2 millisecond pace to make that happen. It's not unreasonable. But think about it. If you're running at a 2 millisecond pace, but you're always still running except for 100 microseconds of time, I mean, that's a nice little trade-off. You're still running, the stop the world's only maybe, what, 5%, 10% of the total GC time. Like, that's fair. I mean, that's fine. We get to run concurrently. So the pacing algorithm is trying to do this. Now, what's also nice is if a Go routine starts to go rogue during a garbage collection, well, the garbage collector can figure that out and stop that Go routine from running. It can context switch it off of a P, give another P time on that thread, and it can also recruit that Go routine to help with garbage collection if it's being bad. It's really cool. Okay, so that's the pacing algorithm. It's going. Now, when we start talking about this, I've thrown this chart up on our screen here. And it shows the different areas of the garbage collector and where some of that stop the world time is. And you notice that immediately during garbage collection, we have a very quick stop the world. And that's to turn the write barrier on. Now, there's really 2 points of stop the world in every garbage collection that runs. There's this one in the beginning to turn the write barrier on. And then there's one kind of at the end before the sweep where we have to do a bunch of cleanup. The write barrier one should be really, really quick. The other one, depending on how much work you're doing, could take longer. Let's talk about the write barrier. The idea of the write barrier is that these Go routines that are running essentially need to report in what they're doing. I like to think of the write barrier as a way of the Go routines to report in what they're doing to keep the schedule and the garbage collector intelligent. But in order to turn the write barrier on, what we need to do is for all of these Ps that are running Go routines, and they only run one Go routine at a time, but they're queued up. What we have to do is bring each one of these Ps to a safe point. We literally have to be able to stop every go routine and set this flag. Now, something that we're going to talk about in Go 1.10, while I'm filming this, 1.11 is now in beta. But at least from Go 1.10 and before, the only way to stop a P or to bring it to that safe point is to wait for a go routine to make a function call. Scheduling really all happens during function calls. This is because we have not a preemptive, but a cooperating schedule. We'll talk more about that later. So the cooperation all happens through function calls. And so if you have a go routine that's in a tight loop, just executing raw instructions, maybe it's calculating pi to the nth level, we could literally stall garbage collection because the other P's and scheduling, because these other P's could be brought to a safe point, and now we're waiting for this. So it's very important in Go that if you're doing any high-level CPU type of, say, mathematics, things like that, that you do have function calls happening. Now, I did see recently that they're looking at trying to create ways at a statement level to be able to bring these P's, let's say, to a safe point, which will be brilliant. But it's a very complicated thing because you've got to deal with the memory barriers. You've got to make sure that things are atomic. And it's very complicated, but they're starting to look at it. From our perspective right now, we've got to have go routines making function calls for all of this stuff to work in a healthy way. So we get all of these P's to a safe point. There's a stop the world latency. If we're lucky, maybe it's 10 microseconds tops, and we set the right barrier on. And now the garbage collector is using some P, and we're running with the rest of the P's. Now, remember something, that the heap is nothing more than a very large graph. And what we have are two things. We have our stacks, okay? And our stacks have frames. And in some cases, these frames are going to have values that point to values on the heap, like this. We're going to have other values here. And some values can point to other values. We've got all this going on. What we really have is an object graph, right? And it all starts and ends from the stacks. Now, you could have global variables that also point into the heap, but we know that not to use global variables, right? I'm just going to pretend that we don't use global variables. There's lots of problems with global variables as relates to testability, hiding the cost of information config. We really want to stay from global variables. There may be some sort of global variable also that you have that's pointing to some value, but let's just focus right here. Now, what we're going to do is, from a tricolor perspective, what we have here is that we turn all of these values, the stacks and these objects, they all start out as white. We're going to paint them white. This is a very high-level view of how this stuff works. I've got articles in there if you want to learn more. But we start everything out as white. And then as we scan these stacks, we're going to paint them black. And what we're going to do is we're going to find these values right here. And these are our root values. We paint them gray. Here are our root values. I have 3 on the board. They get placed into a queue. And now what we start doing on the next phase is we pull these values out. We paint them black. We paint it black. We paint it black. And if they point to anything else, we paint it gray. We paint it gray. We pull them out. We paint it black. It's this whole idea of that we're going to iterate over this entire tree with the idea that when we're done, all we have left are black values or white values. Now, anything that's black has to stay in memory because there's a reference to it from a stack or a global variable. Anything that's white means there is no reference to it. And guess what? We get to sweep these things in the next phase. And then while we're doing this mark phasing, we're able to run concurrently. We're able to do that while we're also running at the same time. And when that mark phase is done, then we've got some more stop the world time to do some cleanup. Again, it should be under 100 microseconds. And then the sweep can come in and do what I just did, finish the sweep. So this is what's really happening underneath. It's a lot of detail. There's a lot of complexity to let this stuff run concurrently. And there's great articles. From our perspective, this is what's important. We have to balance our value and our pointer semantics. We have to leverage value semantics to their fullest extent and know when to use the pointer semantics, understand the costs and the benefits of these things, and try to reduce the amount of allocations our program is having. You're not going to write zero allocation software. You're just not going to do it, okay? So we're not trying to prevent it. We're trying to reduce it. We're trying to balance our value and our pointer semantics the whole way. Less is always more. And if there's less work for the garbage collector to do, this is all going to happen much faster. If there's more work, it's going to take more time. And remember, a larger heap, even though if you have a small live heap, a larger heap doesn't necessarily mean better performance, because it just means that when the live heap gets to the top, it's got that much more work to get to the bottom. So we don't really play with configuration here. We let the pacing algorithm do it. We write software that's going to be consistent in our allocations. We're going to reduce allocations, let the profiler, let benchmarking tell us where there are wasted or unnecessary allocations, reduce that, and just learn how to maintain great balance between our value and our pointer semantics as we write code. Now we're going to talk about constants. And constants are really a fascinating part of the language for me because of the way they're implemented. And again, remember, Go is all about these costs and these trade-offs. So let's talk about the mechanics around constants. I find them really interesting, and I'll show you some of the cooler aspects of constants and how they work in the language. You'll end up using a few of them in almost every program that you write. All right, so one of the really interesting things about constants for me is that they only exist at compile time. Constants are something that really have a much different feel and flavor to than your common variables. Look at this right here on line 15 and 16. Right here I'm declaring two constants, but these are constants of a kind, and that's the interesting thing. I've only seen something like this in this language. Most of the time we think about constants as being read-only variables. It is absolutely not the case in Go. So when we look at constants, they can come into this flavor that you see here, that is of a kind. Notice that there's no type information during the declaration of these constants on line 15 or 16. And again, it's based on the value on the right-hand side of this assignment, whether they'll be of kind integer or kind float. Right below there, just to show you the contrast, those are constants of a type int and of type float 64. Now, the big difference between constants of a kind and of a type are that constants of a kind can be implicitly converted by the compiler. This gets really interesting. Remember, we talked about during the struct types that there's no implicit conversion of that concrete data. But when we start talking about constants of a kind, that goes out the door. Now, constants of a type still hold true that once something is of a type, then that's it. The implicit conversion goes away. But constants of a kind, there we get some flexibility. And it's a very powerful mechanism in Go. I'll show you from code readability. So there we go, UI, UF, two constants of a kind int, kind float, and TI and TF, constants of type int and type float. Now, if we continue to talk about the idea of these kinds and what happens there, there's something very special in Go, and it's called kind promotion. And this kind promotion will tell you how things promote. So floats promote over ints, and types always promote over kind. So on line 24, I've had to comment that out because once I made that constant of a type, uint8, it was bound by the laws of type, and you could only put a value within the scope of a 1-byte or 8-bit integer. But what's also really interesting about constants of a kind, because they're not type-based, they're technically not limited by precision. And if you look at the specification, around constants of a kind, you'll notice that the specification says that a constant has to be at least of 256 bits of precision. That makes constants of a kind almost like, or the compiler when it comes to constants of a kind, like a high precision calculator. Now, if you look at line 30, I want to show you some very interesting things here. What we're doing is we're multiplying the value of 3 by the value of 0.333. On the surface, we see that we have an integer and we have a floating point. And remember, you can't have implicit conversion between two different types. We could argue that these are two different types, an int and a float. but they're constants. Literal values in Go are constants. They're constants of a kind. They're technically unnamed constants of a kind. And so through this idea of kind promotion, that kind integer 3 will be promoted up to kind float. We now have like kind on both sides of that multiplication, and var at this point, this variable, ends up being a variable of that float 64 type. Very, really interesting, powerful stuff where we're able to work with literal values from a kind perspective. We don't have to worry about doing any explicit conversions. And then this promotion takes care of making sure that everything is right. But remember that we're dealing with 256 of precision, 256 bits of precision when we're dealing with constants of a kind. And when we now convert this back to a variable where you see answer, we're moving that down to a 64-bit level of precision. There will be some precision loss. But again, remember that floating points are already not precise, right? IEEE 754 binary decimals. Look on line 33. This time we're doing division between basically a kind int 1 and a kind float 3.0. Again, we get the same thing. That integer promotes up to be of kind float. And we actually, what we would say is have the exact representation of 1/3. Sometimes in the old days we used to call what we considered constants of a kind to be exact. They were like these very exact numbers because we had such high levels of precision that that they were exact. So we would look at third there truly as 1/3, even though eventually at 256 bits of precision there would be some precision lost. But then on line 36, you can see that there's no promotion going on. 1 is of kind int, 3 is of kind int. We do the division and we end up with 0 because that's what that's going to be. Everything stays within the kind integer. Now I also told you that we can promote from kind to type. And look at this on line 40. We're creating a constant of type int 8. We're assigning the value of 1. So it's still a constant, still only exists at compile time, but it's bound by the int 8 type. And now this is where the real power of kind and type comes in. Look on line 41. We're taking the literal value of kind int 2, multiplying it by the constant of int 8. And now, again, through promotion, that kind 2 value promotes up to int 8. It now promotes to be a typed constant. Again, we've got to have those like types across that expression. And 2 ends up being a constant of type int 8. So these are the mechanics, okay, of constants with a kind, constants of a type, and the promotion. And I want to show you how powerful this stuff is. But before we do, I want to show you as well that this idea that constants only exist at compile time, and they have these high precisions, like a minimum of 256 bits of precision is real. Now, it's hard to show you this is real when things only exist at compile time and we have to run a program at runtime, but I want you to look at these constants that I've declared. This constant is called maxint, and it represents the maximum signed integer you could have for 64-bit precision. There it is. But look on line 14. I'm storing a much larger number there, much larger than our 64-bit variables could ever hold. Now these are integers, but again we have 256 bits of precision. If we didn't have these higher levels of precision, we really wouldn't be able to do this assignment at all. So what I'm really going to show you is, as I run this, the compiler accepts line 14, even though this is a much larger number we could ever put in a variable. I mean, look, if I take this and say, let's create a constant of type int64 with the same number, this won't compile. That number is much larger than a 64-bit can hold. And I've still only scratched the surface on what I could store in this constant. I mean, I can keep going. I've got 256 bits of precision here. So the compiler is really like this high precision calculator when it comes to constants. Let me show you a more practical use of constants and how this kind and type promotion really makes our life a little bit better. Look at this constant here of type duration. This is a second way to declare a type here in Go. What I would say is the name type duration is based on int64. This is not an alias. We have really two distinct named types here. We're just using int64 as our base information or our base memory model for duration. And I only want to do these types of things when the new type has its own representation and meaning. And it does here in the time package. Duration represents time. It doesn't represent an int64. It represents nanoseconds of time. And I want you to look at these constants because this is a real practical and clean way of how this idea of type and kind work together in constants. So we create a typed constant named nanosecond, which represents one nanosecond of time. It's based on a duration. And then if you go to line 16, look at what we're doing. We're taking the literal value of kind int 1000. This is a constant, an unnamed constant of kind int. We're multiplying it by our typed constant nanosecond. This gets promoted to be of type duration, and we end up with another constant of type duration. How amazing is this? This looks simple on the surface, but the engineering behind this is really, really powerful. In fact, all of these constants end up being of type duration and represent the proper int64 value for these incremental units of time. And more gets into this. I mean, look at this add method. We're going to talk about methods later, but I want to focus on the parameter here. Notice how add takes a value of type duration, right? And we might do this. We might say, I only want to pass duration values into add. Well, one of the interesting things about constants of a kind, again, is that they can be implicitly converted when there's compatibility. This is one of the first things that really messed with me when I started learning Go. I mean, look at this. On line 39, I call the now function off the time package, and I create a variable which gives me the current time. Now, when I call add on line 42, notice I'm passing the literal unnamed constant of kind int minus 5. You might say, whoa, that's not of type duration. What's going on? Why would the compiler accept that? This is one of those trade-offs, because values of a kind, right, constants of a kind can be implicitly converted. We can pass that in. It would represent minus 5 nanoseconds, and this would really mess you up. This is one of the reasons why we can't have enumerations in Go. We don't want to create types as aliases to get compiler protection when they're based on, let's say, those built-in types, which is what constants are allowed to be. Constants can only be based on the built-in types because, again, they only exist at compile time. But look at this. This is something that we're going to do a lot in Go. The timeout constant, right? 5 is of kind int. There it is. Time second is of type duration. It's still a constant, but it's a constant of type duration. That 5 in kind promotes up to duration, and timeout becomes a constant of type duration. And that constant of type duration supports the API very, very cleanly. This is really nice and great API design, leveraging constants of a type and constants of a kind. Very, very powerful stuff. The one thing you could never do is what we see here. Notice that I'm converting our integer, right, our constant minus 5 of kind int into a variable or a value of type int64. I cannot pass minus 5 to add because that is a value based on a named type int64, and it only wants duration. So those constants of a kind can be implicitly converted through those calls. Any value that's based on a type, we've got to have like types everywhere, everywhere. Very, very interesting and powerful stuff around constants. Now, there's one last thing about constants that you'll probably want to use as you're writing production level code. This is the idea of the keyword iota, I-O-T-A. And it's really interesting, and it can be very, very confusing at first. If you notice that I'm using the concept of a block, we can do this with vars and types, and we do it with imports all the time. Notice that we're using the parentheses here to block a bunch of, in this case, constants, so I don't have to write const again over and over again. And this iota stuff works very, very well when it comes to constants. Now, when we start a block of constants like we did here, iota starts at the value of 0. And then every time we use it inside the block, it will increment by 1. The output of this right here, if I just run it, you'll see here that it's 0, 1, 2. 0, 1, 2. We get this incrementing feature for free inside the constant block. Now, most likely, because we want the incrementing feature, we're going to do it like this. We only have to assign iota one time to the very first constant in the block, and we will automatically, for free, get the incremental. Again, on the output here, what you see here is 2, 0, 1, 2. Same exact output, Thing is, I didn't have to repeat myself and keep putting iota there. Now, this is something also that you'll see a lot of. Maybe we don't want to start at 0, we want to start at 1. So the first constant we know what the starting point is for iota is 0, increment it by 1 initially on that first constant, and then we'll start at 1. 1, 2, and 3. And we do this in the log package, and sometimes what you want is a set of constants that bit position in some sort of flagging system like we do with logging. Notice this time what we're doing is we're using the iota value to shift bits to the left one, and that gives us 1, 2, 4, 8, 16, 32. You might see that a lot with constants as well. So this iota is a very powerful mechanism if you're creating a set of constants that are going to have some unique IDs, and it just kind of lets the language set all that up for you. So constants are really, really powerful in Go. Remember now that there's two types of constants, constants of a kind and constants of a type. Your literal values in Go are constants of a kind. They're unnamed constants. Constants of a kind can be implicitly converted by the compiler, which means that you can't really have enumerations in Go. You're not going to get those compiler protections. Once the compiler is based on a type, then the full laws of type are going to restrict its ability to be anything other than its particular precision. Remember, constants of a kind can have up to 256 bits of precision. We've got really like a high precision calculator in Go. And then again, those literal values are all constants of a kind. Welcome to Lesson 3, Data Structures. Maybe one of the more important lessons that we're going to learn here early on. They're all important, but this one's early on because this is going to teach us mechanical sympathy and data-oriented design. We're going to learn why Go only has arrays, slices, and maps. It was one of those things that confused me early on in the language. Where are my lists? Where are my stacks? Where are my queues? No, 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 no. Go's got arrays, slices, and maps. And in this lesson, we're not just going to learn the mechanics and the semantics. We're also going to learn the history of why Go has made those choices. Data-oriented design. So before we get into data structures in Go, I really want to share some information around data-oriented design. It's a really important aspect, I believe, of the language, and one of these things that you're going to have to kind of start switching your brain into away from object-oriented design. Now, I've said a few times already in this training material that what data-oriented design is about is the understanding that every problem you solve is a data problem. We're all data scientists at the end of the day. Integrity comes from the data. Our performance is going to be coming from the data. Everything we do, our mental models, everything's going to be coming from the data. And so if you don't understand the data you're working with, you don't understand the problem you're trying to solve, because all problems are specific and unique to the data that you are working with. And data transformations are at the heart of everything we do. Every function, every method, every encapsulation is really around the data transformations that we're working on. But here's a big part of it. Everything we do right now that we've been talking about is in the concrete. Our problems are solved in the concrete data. Our manipulations, our memory, mutations, everything is in the concrete. But here's the problem. When the concrete data is changing, then your problems are changing. And if your problems are changing, guess what? Your algorithms have to change. And there's nothing wrong with that, except we start to fall into these areas where once the data is changing and our algorithms change, sometimes that creates changes, cascading changes across an entire code base. And there's a lot of pain. And this is when we start focusing on how do I decouple the code from these data changes so these cascading changes are minimized. We will be talking about that in this class when we start getting into methods and interfaces and things like that. But here's the thing. If you're abstracting in a general way, if you're building abstractions on top of abstractions, you're really walking away from all the things we've talked about so far, that the idea of optimizing for correctness and readability. You're walking away from your really ability to even understand the mental models of your code because it's too abstracted. What we need is this balance of decoupling, but thin layers of decoupling to deal with change. Change is still going to be important. But look, if you're starting to write some code and you're uncertain about the data, this doesn't give you a license to guess. It's a directive to stop. Stop what you're doing, sit back and ask yourself, What are the data transformations that are in front of me? You don't have to know about all of them, but you can only code the ones that you're comfortable with, that you feel very confident about in terms of what my input and what my output is. And look, if you are solving problems you don't have, you're now creating more problems that you do. We are writing code for today. We're going to design and architect for tomorrow. Don't add more code to the code you need today than you do. We've talked about that. That just lends itself to bugs, more lines of code, places for bugs to hide. We've had these conversations already. And I want to just keep reiterating this thing, that data-oriented design is about understanding the data, writing the code that we need, the algorithms that we need, and eventually decoupling those algorithms that we have in the concrete to deal with the data changes. And everything we must do is focused around minimizing, simplifying, and reducing the amount of code we need to solve every problem. And we're going to learn very soon about mechanical sympathy. And if performance matters, then how the hardware works and the operating system work has to matter to you. And it all, again, is going to be tying back into data-oriented design. Data, 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 data. You're going to hear me moving forward quite a bit, constantly talking about data's driven everything. Data's driving everything. Everything is being driven that way. All right, so we're going to start looking at Go's data structures and start understanding why Go only gives us arrays and slices and maps. And I want to show you the mechanical sympathies that these data structures have and how we're able to not hide the cost of the things that we're doing. And we're able to gain more efficiencies when we're working with the data and be able to write algorithms that are readable and yet still very, very performant. Because again, on the scale of where do you lose your performance in Go, algorithm efficiency is really at the bottom of that. It's going to be latency at networking and I/O, latency on allocations and memory, and latencies in your inability to write code that can manage and work with data efficiently. These are things we're going to talk about now. So we're going to start trying to, I'm going to start trying to break you down and build you back up to get away from these object-oriented design principles and start moving towards these data-oriented design principles. All right, so what we're now going to start learning is Go's data structures, and we're here in the array section. But before we get there, a little story. When I first came to Go from C#, and I had done C++ before that, one of the things that struck me as odd was all my data structures were gone. Where are my lists and my queues and my stacks and these data structures that for 20 years I've been working with, and it's gone. All Go gives you is the array, gives you this slice, which looks like an array, and it gives you maps, which I can understand, key value pairs. And my brain is just starting to shut down, because when I went to school in the late 80s, we were taught arrays, but we were also taught to stay away from arrays. They were complicated and hard to work with. They were static in size. They were not dynamic. We learned how to use linked lists and other data structures, and I've been using them my whole career. And now I come into Go, and they're all gone. Arrays, slices, and maps. That's all I got. So when I first started coding in Go, I started just using the linked list package. It's what I knew. It's how I knew how to deal with data, and I started using it. But over and over again, I kept seeing this use of slices. Slices were everywhere in the language. And then I started to learn how deeply built in to the standard library they were as well, and the built-in functions. And this was a core data structure in Go. And in fact, today, the slice is the most important data structure we have in Go. But I didn't understand why. And I'm one of these people where I really want to understand what I'm doing and why I'm doing it. Again, the mechanics and the semantics, and I can make better engineering choices. So what I want to do is share with you a little program that's going to help us on our journey to understand why Go only has arrays, slices, and maps, and why we should be using these core data structures as our first choice. And when we go beyond that, it's usually more of an exception and not the rule. So let's take a look at this piece of code here. This code starts out defining two constants, rows and columns both at 2,000. And we're going to use that to create this matrix of bytes. Basically, we're going to have about 4 million elements in our matrix, each a byte in size. And what we're going to end up with is this data structure here, right? Nothing fancy, just a big square matrix. It's going to have rows. It's going to have columns. And each one of these elements is 1 byte in size. Then, on line 21, what I've done is I've defined a data structure which will be simulating my linked list. And the linked list is nothing more than you allocate a small block of memory, you put your data into it, and we use a pointer that shares us to the next piece of data somewhere in memory. These were really great data structures that we learned. It's a core data structure that's used by lots of algorithms because instead of trying to allocate one big contiguous block of memory, we can allocate these smaller ones. And back in the old days when we didn't have a lot of memory, this type of data structure was very, very important. So we've got v, our byte. We got a pointer to the next piece of data. Right? It looks recursive in the that it can point to itself. And then on line 27, we have the linked list pointer. That's the head pointer. That gives us where the beginning of the list begins. Now, in the init function, I'm doing a couple things. What I want is a node in the linked list for every element. Basically, I'm going to have 4 million elements in the array. I want 4 million nodes in my linked list. And another thing that this code does is every other element and every other node, we reset the byte from 0 value to FF. Because we're going to operate on every other element or every other node. Here's the real idea behind this code. I wanted to know what was the CPU performance, how much time did it take to traverse from beginning to end the matrix and the linked list. Now, the linked list is unidirectional. So I want to know, as I traverse and walk down this data, how fast can I do that? And just to do some extra work, I increment a local counter on every other access. Now, when we talk about traversing a matrix, we can go in 2 different directions. I can do column major order, where we're going down, 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 or I can do row major order, where I'm doing across, 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 across. So it's the same block of memory, but we can traverse it in 2 different directions. I want you to notice something about the 3 algorithms. They all are basically 4 lines of code. I need 4 lines of code to traverse the linked list and increment the local counter. I need 4 lines of code to do row major traversal and column major traversal. From an algorithm perspective, these algorithms all have essentially the same kind of algorithm efficiency when it comes to the lines of code. I cannot reduce the number of lines of code, and I really can't do anything more or less than I'm doing in these functions to make this code any faster. I'm at my highest levels of efficiency right now. OK, 2 data structures, 3 different traversals, 2 different directions on the matrix, 1 direction on the linked list. But how can we look at how long it takes to do these traversals? Well, Go's testing tool gives us the ability to write benchmarks. And what we're going to do is create an underscore test file. You can see here in the name, caching underscore test. And we're going to write 3 functions that start with the word benchmark and take a testing B pointer. Linked list traversal, column traversal, and row traversal. Now, this is what's cool. The way the benchmark works is the Go testing tool will find these benchmark functions and call them one at a time. And when it calls the benchmark function, it will set this b.end variable to be 1. All of the code that we want to benchmark must be inside this loop. Now, it's important that the code inside the loop is as accurate to the way it's being used in production as possible, or the benchmark isn't necessarily going to be accurate. And in order to make benchmarks accurate, your machine also must be idle. I am doing this on my Mac. This machine is really technically not idle. But if you're going to be running long-term benchmarks, especially on your desktop machines like this, make sure you're not browsing the web or watching cat videos online. You really got to leave the machine alone, because anything this machine's doing other than running the benchmark is affecting your performance. Now, another thing you have to understand is when we run these benchmarks, the Go compiler is going to recompile this code. The compiler has the ability to throw dead code away. In other words, the compiler could identify that this function doesn't mutate anything, yet it returns a value and we're not storing it. That means the compiler could say, I'm not going to waste my time calling this function because it has no impact on the output of this program whatsoever. So notice that I'm performing the assignment to a local variable and then to a global variable, so the compiler has no chance to throw this code away. You don't want this blazing fast benchmark, and you don't want it to be blazing fast because it didn't do anything. So by default, a benchmark will run for 1 second, which means it will run for a few seconds, and b.n will increase over time. So the first time it gets called, b.n is 1. The next time it will be larger. The next time it will be larger. The idea is to run the code inside the loop enough times, hopefully millions of times, that we feel confident with the results. So we've got our 3 benchmarks, linked list, column, and row. And what I want to do right now is run these benchmarks. Now, I'm going to run them a few times because, again, my machine is not idle. And I want to see what the consistency is on every one of these runs. So I'm moving into my terminal window. I'm already in this location here. I'm already in the location where these files are. And what I'm going to do is ask the Go test tool to run the benchmarks. Now, by default, the Go test tool wants to run test functions. These are functions that start with the word test, not benchmark. And the -run flag says, what test functions do you want me to filter out and only run? I'm saying none. It's any sort of regular expression you want. I'm saying none because there are no test functions, and it can just very quickly forget about it. But I do want to run all the benchmarks. So I'm going to use the dot operator as the regular expression for all, and say run all the benchmarks. I'm also going to increase the bench time to 3 seconds from 1. That way it just runs a little bit longer. OK, let's do this CPU profile then, and we'll see what the benchmarks show us. So there's our 4 million elements or nodes in our linked list. We're starting with the linked list, and every 6 digits would represent, at this point, a millisecond. So you can see that we're at 6.0 milliseconds for the traversal of the linked list. You can see here we're at 10.4 milliseconds for the column traversal and 3.6 milliseconds for the row traversal. Now, this is already a really fascinating result. Remember that row and column traversal are using the same memory block. This is the same memory. It's not that it's allocating or working against something different like the linked list. It is the same block of memory. But look at the difference in performance. It's more than double the cost when you go column traversal over row, and the linked list is sitting somewhere in between. I'm going to run it again because I like to see if there's any real consistency in the runs over time. So we're at 6.0 milliseconds. We're still at 6.0. It actually ran a little bit faster, 6.08 to 6.06. Notice the drastic change in the column traversal. I mean, that's drastic. I mean, we're only talking like 3 milliseconds. From our perspective, that's like eternity. And then the row traversal got a little faster, but again, it's very, very consistent. Our linked list and our row traversals are consistent, and our column traversal is all over the place. All right, when I ran this for the first time, my head was spinning. I saw very, very similar results. And I'm saying to myself, what is going on here? Why is it that my algorithms are as efficient as they can be, yet the performance difference is in some cases, like column row, drastic, and in column and row, I'm using the same memory. It's not like I can explain it away that I'm somewhere else in memory. This is the same. All right, so what I want to do is show you an animation that came from a great video from Scott Myers, where he talks about CPU caches and why they matter. And I really think everybody should watch this video. But here's an animation that Scott shows during the talk. And I want to walk through this with you because it's going to help us to begin to explain these results that we see right here. Now, what this animation is going to show us is the relative cache speed of accessing data from the different caches. You know that your processors have L1, L2, and L3 caches, and then there's main memory. So this is a level 1 transfer of memory. That's fast. Here's level 2. This is level 3, a little bit slower, but there it is. And here is main memory. Look at how slow it is. Main memory is so slow to access here. Whew. OK, it just finished. Let's do this one more time. I want to show you again the relative speed between these caches one more time. Level 1, super fast. Level 2, a little slower. Level 3, still pretty slow, but we got it done. And then level 4, oh my God, really main memory, not level 4. You know, I wish that I had something to read while we waited for this to get done. Boom, there it is. That's the relative speed of fetching memory, accessing memory from the different caches. OK, how is that going to help us understand what's going on? Well, let's take a look at this. This is the Core i7-900 series. This processor is the one that Scott used when he put that animation together. And this processor is going to allow us to talk about hardware at a representative level. We don't need to get into the guts and the deep, understandings underneath the hardware. What we need to do is have a mechanical sympathy, an appreciation for how this hardware works. We could talk about hardware from a representative level, because when we have a piece of hardware like this processor that has a caching system, then from our perspective, everything is really the same in terms of what our responsibility is. So Scott used the i7-900, Intel i7-900 core series, and again, it's still very representative for the processors we use today. Now notice this processor, it's a 4-core processor, 2 hardware threads per core, and every core has its own L1 and L2 cache. Now in this particular processor, the L1 is 64,000 bytes, split in half for instructions and data, and L2 is 256,000, L3 is 8 meg, and then you have main memory. Now, one of the things that's interesting here is that animation that I showed you is showing the relative clock cycle cost of accessing the data from these caches to get it into, let's say, that hardware thread, into the registers, so the hardware threads can do their job. That's going to be that latency cost that we saw in the animation. And if I scroll down here just a little bit, we'll be able to start to see what those numbers were. Now, to best understand the latency and the numbers, let's start with this idea that the processor was a 3 gigahertz clock. So now, if you notice, we have this 3 gigahertz processor. But if you really notice, lately, processors, not even lately, for years, processor speed has been going down, not up. A lot of that has to do with the fact that you have to deal with heat if you run these processors at a very high clock speed. But even though we've been bringing clock speeds down, and the idea of the clock speed is how we're pumping electrons through that processor, right? A 3 gigahertz processor means that we have 3 clock cycles or 3 pumps every nanosecond. We've been bringing this down, but we've been getting faster and faster throughput in terms of instruction execution. Part of that is because we should be able today at least to execute about 4 instructions per clock cycle. And this is what we're really going after. We're not necessarily going after, can we burn the processors faster? Can we raise the clock? Can we execute more instructions per clock cycle? Then we're going to get better performance. And it's not unreasonable to be able to get about 4 instructions per clock cycle, sometimes a little less, or we'd love to have maybe more. Which basically means that we basically should be able to execute about 12 instructions per nanosecond on that 3 gigahertz processor. Now, based on those numbers, that animation that I showed you was basically this. And you have to look at your hardware for the actual numbers for the hardware you're using. But on that i7-900 core series, to access data out of the L1 cache, that cost us 4 clock cycles of latency. Where basically, for that core, we stalled for 16 instructions or 1.3 nanoseconds. But that's the best we can do, right? I mean, that's it. That's going to be our best latency in terms of accessing data. Now, if the data you need is in L2, well, on this hardware, that's costing us 11 clock cycles of latency, 44 instructions or 3.6 nanoseconds. Right? Still not so bad, right? You saw the animations, they weren't that bad, but again, a little bit slower. When data's in the L3 cache, well, now we just went from 4, 11 to 39. Still within reason, but now we're looking at 156 instructions of stalling with 13 nanoseconds. And finally, why main memory is so slow to access is on this particular piece of hardware, it's costing us 107 clock cycles. This is like an order of magnitude larger, right? An order of magnitude more memory, but also an order of magnitude more slower. 107 clock cycles of latency, that's 428 instructions, or 35 nanoseconds. We've just stalled on that one core. And God forbid this is happening across all 4. I mean, we could be talking about 1,200 instructions that we are now not executing because the data we need is not in the caches, but in main memory. And main memory is just incredibly slow to access. This is why the caching systems are here, to help speed up this latency, to reduce the latency of getting data out of main memory and getting it there close to where it's needed by those hardware threads. That is the thing. And the majority of the hardware you're going to be using today, including your ARM processors and things, are going to have these caching systems. So what we're talking about is going to be, apply across all of the hardware and the systems that you're building when a caching system's involved. All right, so this was the animation that we were looking at. We were looking at the relative clock speed of accessing data from the individual caches. And something else that's very interesting, at least on the Intel platforms historically, that any data that's stored in L1 and L2 is copied or duplicated also in L3. So you can't add the three caching hierarchies together. From our perspective here, 8 meg is the total amount of memory you have to work with if performance matters. And I want to make this clear. If performance matters, well, main memory is so slow to access, it might as well not even be there. If you've got to keep taking a 107 clock cycle hit every time you need to access data, you can kiss your performance goodbye. So there's two core things here around the mechanical sympathy of the processor and the caching system. Okay? Main memory is so slow to access, it might as well not even be there. The total amount of memory you have is the total amount of cache, and in this case, 8 meg. Also, small is fast. When we say small is fast, what we mean is if the data you're working with is small enough to fit into the caches and small enough to stay as close to the hardware thread as possible, you're also going to see some better performance. All right, now let's talk about how these caching systems work, because we'll be able to tie that back into our results. Let's say on core 0, we have an instruction that we want to execute, and that instruction needs the letter M right here in the word main memory. Let's pretend that this is our data, and we need the letter M from main memory to come into the caches. Now, it would be very inefficient for the caching system to just pull in 1 byte into this L1. So what the hardware does is it takes all of the memory that we work with and it breaks it up into what we call cache lines. And a cache line historically is 64 bytes of memory. Mainframes could have cache lines that are like twice that, 128. I also believe like you can go into CMOS and make these changes, but 64 bytes is the historical size of a cache line. So you can think of all of the memory that's laid out on that machine, right? All of our virtual memory, and from a caching system perspective, it's the cache line. So the full cache line of memory that letter M is on, so if this is holding the word main, well, those letters are going to be on some cache line. There's going to be some more bytes here, more bytes here. The entire cache line is moved from main memory and into that L1 cache. Now, when we're going to move that cache line into the L1 cache, we're going to have to move a cache line out. Remember, everything is sharing this. Your operating system code, other applications, we're all sharing the hardware. So we're going to have to move some cache line out. The hardware's got to figure out what cache line we should move. Maybe it decides it wants to keep the cache line close and move it into L2, which means we've got to move a cache line out of L2 now completely. And there is already a copy on these Intel processors of cache lines in L3. We get some mechanical sympathies with that. Maybe we take a hit a little bit as data's coming in because we're going to have to put this cache line on L3 and maybe L1 and move something out of L1 into L2. This is why it takes so long, right? But once that's set, we're good to go. The AMD processors historically have not made those extra copies in L3, and you could add the 3 caching hierarchies together and maybe get a little bit more memory to work with. I know the new Skylake processor from Intel is looking at having a much larger L2 cache than L3, and so some of those things would change. But again, from our perspective, what's important is that we want to try to reduce that 107 clock cycle bit of latency where we're taking the cache line out of main and moving it into L1 or say L2 at the time we need it. What we would prefer to happen is that this cache line is already in L1 or L2 before we need it. Because if we can get the cache lines into the processor before we need it, we don't take the 107 clock cycle. It's close. Maybe we only take the 4 or the 11 clock cycle hit, and we won't even feel that. It's all staying within inside the core. This is what we're doing. So the question then becomes, how can we create a situation where the cache line can be inside L1 or L2 before we need it? This is our job. This is something now that becomes our responsibility. What we have to do is write code that creates predictable access patterns to memory if we want to be mechanically sympathetic with the hardware. If performance matters, then what we have to do is be much more efficient with how data gets into the processor, not get the processors to run at higher clock speeds. Predictable access patterns to memory is everything. All right, so how do you create a predictable access pattern to memory? That's the next step. Here is the simplest way to do it. If you allocate a contiguous block of memory and you walk through that memory on a predictable stride, well, guess what? The prefetchers, which is little software sitting inside the processor, the prefetchers can pick up on that data access and start bringing in those cache lines way ahead of when you need them. The prefetchers are everything, and we must be sympathetic with them. Now, the cleanest and easiest way to create this predictable access pattern is to use an array. An array gives us the ability to allocate a contiguous block of memory. And when you define an array, you define it based on an element size, right? It's an array of string, it's an array of int. There's our predictable stride. Every index is a predictable stride from the other. Prefetchers love arrays. The hardware loves arrays. It really is the most important data structure there is today from the hardware. And I almost don't even care what your algorithms are. An array is going to beat it. Now, there are times where maybe you're dealing with data that is so large that a linear traversal isn't going to be more efficient. But overall, if you're dealing with data, small data, that array and those predictable access patterns are going to beat out performance every time on these traversals. All right. So the array is the most important data structure as it relates to the hardware. But I need to make it clear, the array is not the most important data structure in Go. The slice is the most important data structure in Go. And this is because a slice uses an array underneath. Technically, slice is really a vector. And if you've watched any C++ videos over the last 5 years, and go to CPPCon and look, and if you see any CPPCon video over the last 5 years that are talking about performance, you will hear the person on stage say, vectors, 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 vectors. Use vectors. Why? Because, just like the slice, we're going to be using arrays behind the scenes. We're going to be doing those linear iterations, and we're going to be creating predictable access patterns to memory that the prefetchers are going to pick up on. Brilliant stuff. Now, there's another cache in the hardware called the TLB. This cache is also very important. When we talk about how the operating system manages memory, the operating system manages memory at a granularity called a page. Now, operating system pages can vary in size, anywhere from 4K, 8K, 16K. There's even some Linux distributions that use 2 meg pages, and this is why. The TLB is a very special cache that the operating system is going to be managing. And what it does is it creates a cache of virtual addresses to operating system page and physical memory locations. In other words, your program is working in virtual memory. It thinks it's got real memory, but it's not, right? It's given a full virtual memory because the operating system gives it that level of abstraction. So when you say, go get me the value at this address, this virtual address, the TLB is there so the hardware can do a very quick lookup. Hey, where is this virtual address for this process physically located in RAM? That's the TLB. Now, if you're getting TLB cache misses, remember these are caches, these are small caches, high performing caches, but they're small. And if you're getting a TLB miss, now what has to happen is the hardware's got to go ask the operating system, where is this thing? And there has to be like a traversal around the operating system paging table. And if you're on a virtual machine, like a cloud environment, those virtual machines also have their own paging tables. A TLB miss could be really, really deadly. And so these predictable access patterns are not just helping with cache lines, they're also helping with making sure the TLB is also properly cached, so all of this access to memory is as fast as possible. Again, performance today is not about how fast we can churn that clock, how fast we can push the clock in terms of cycles per nanosecond. It's about how efficiently we can get data into the processor before we need it, so we can reduce all of the latency there is in accessing data, especially in main. And if we can even reduce more of the L3 latency, well, guess what? We're better off. So if we go back to our results now, I want you to notice something here. We should be able to understand now why we see what we see. Look at row traversal. Row traversal was not only the fastest, it was also incredibly consistent. And why is that? That is because when we start walking through the matrix row by row, we're walking it down cache line by connected cache line. That row major traversal is creating a predictable access pattern to memory, and the prefetchers are coming in and reducing all of the main memory latency costs. It's brilliant, right? We're going to get the best performance I can get on my machine through row major traversal. But why is column traversal so slow and inconsistent? I played a small game here with the matrix. I made the matrix large enough so this element and the next element, not only were not really in a predictable stride, let's say, but made sure that those two elements ended up on two different operating system pages. Yes, they were very far away from each other and on different operating system pages. I've got a ton of problems. This is basically pure memory access memory, random access memory. Sorry, this is basically pure random memory access when we're doing column traversal. This is why our results are so inconsistent and so slow. Now the linked list sits somewhere in between. We're probably getting cache line misses because this data is not guaranteed to be on a predictable stride. But we're probably getting this data all on the same page. This is why when we talk about a 2 meg page, if you're dealing with a system like a database or something that's going to be very, very large amounts of memory and data storage, those 2 meg pages can come in really, really handy because the TLB means there's more data on a page and our TLB cache will be better off for it. So we're probably getting cache line misses on the linked list, but we're not getting so many TLB misses, and we're falling somewhere in between. Really interesting. So we're starting to now understand why it's not so much how fast we push the clock. It's about how efficient we can get data into the processor, and efficiency is all going to be around creating predictable access patterns to memory. So now when we come back and we look at what Go's given us, arrays, slices, and maps, it all starts to make sense. We don't have linked lists and stacks and queues and these things because they are not mechanically sympathetic with the hardware when your model is a real machine. I will never say anything negative about Java. The JVM is an amazing piece of engineering because it takes these mechanical sympathy issues and deals with them for you with compacting garbage collectors and data layouts. They are making sure that when you have your linked list access, when your object-oriented patterns, which are all really linked list oriented, that underneath the covers, without you realizing it, they're creating predictable access patterns for you. We don't have a virtual machine here. You have the real machine, which means you are more responsible for your data layouts. You're more responsible for your traversals. But that doesn't mean you have to get overwhelmed. What it means is if you use the slice, which is the most important data structure in Go, not the array, but the slice, if you use it for the majority of your data needs, you are inherently creating predictable access patterns to memory. You are inherently being mechanically sympathetic. And by the way, the Go map also is constantly creating data underneath it that is contiguous. Its job is to keep the data contiguous. Think about it. Your stacks, contiguous memory. Your maps underneath, contiguous memory. Your slice, a vector, contiguous memory. Predictable access patterns are everything today. This is why that processor speed can go down, and we can still get some better performance. So this is what we have to understand. We want to use the slice, and a slice of values is our first choice until it is not reasonable or practical to do so. And it may not be reasonable or practical because the problem you have in front of you may be easier to solve, simpler to solve, maybe with a binary tree or a linked list. And I'd rather you say to me, Bill, I'm not using the slice because if I use this other data structure, my life and the algorithms, everybody's life around us is going to be better. This is easier to maintain. And I'm going to say, you know what? That is worth the small performance it will take. Because you've already seen over and over again, if you've been following from the beginning, that we take integrity and we take integrity first, right? Which means we're going to take some performance hits. We got a like 0 value. We care about memory resources being low first. That's going to take us some performance hits. So again, what we're trying to do here is maintain mechanical sympathies until it's not reasonable or practical to do so. And this is why Go's just given us the array, the slice, and the map. So we just reviewed around how mechanical sympathies of using arrays and slices and maps a little bit. And we showed how these mechanical sympathies are real as it relates to hardware that handles caching. Now I want to try to sum up a lot of what we've talked about up to this point while using arrays and to get back into some of the conversations we started earlier around value and pointer semantics. So there's a lot here in this section I want to cover that's going to give us a really, again, a strong base foundation as we move forward and learn about data-oriented design and our data structures. So let's start with this piece of code here. Now, we're not doing anything special on line 14. We're declaring an array of 5 strings, again 5 being that constant of kind int, right? But the compiler knows about the size of an array at compile time because the size of an array must be known at compile time. You can't use a variable for an array, but we will be able to do that with our slices. We'll see in the next section. But when I see line 14, what I see is 40 bytes of memory. Remember, a string is a 2-word data structure. We're on our playground. So what I see is starting at index 1, 2, 3, 4. I see 5 strings laid across contiguously, all set to their 0 value, which makes them empty strings. So this is what we have after line 14. This is what I see. This is our fruits array. Now, I want to focus on line 15 for a second. What we see on line 15 is a literal string named apple. That's also a string. That's going to be a pointer to a backing array of 5 bytes, apple. And we're going to have the number 5. Now, it's a literal string. It's a constant. That data will be in our data segment. But let's just imagine right now that we have our string. We've got this pointer. There it is. One of the questions I always like to ask in a class is, what is the cost? Remember, we're talking about engineering costs and benefits. What is the cost of this assignment on line 15? Now remember, an assignment is a copy operation. So the question is, what is being copied on line 15? This string is really the combination of 2 data structures. It is the string value and a pointer to the backing array. What's really interesting here is that the cost of this is just the 2-word data structure. So all we're going to be copying is the 8 or 16 bytes, depending on the platform, of memory that's associated with the string value, which tells us right away something very special. Remember, pointers are for sharing. Pointers are for sharing. And if you look here, this pointer is giving us the ability to share the backing array across these 2 distinct string values. Remember, pointers are for sharing, and that sharing gives us a level of efficiency. I only need 1 of these backing arrays for the 2 string values that we have. Now, Go only uses a for statement for all of its iteration. You can use the for in a traditional way, like I'm showing you on line 31 here. You can also use for like a while, where you just specify the condition. But the for range is a very special and powerful iterator in Go. And the reason why it's so powerful is because the for range comes with two different semantics. Here we go again with semantics. There are value semantics and pointer semantics associated with the for range. Remember again, when I talk about value semantics, what I mean is that every piece of code is operating on its own copy of the data. So as we transition across program boundaries, in between functions, as we do things, we're operating on our own copy of the data. What are the benefits about? Again, we get the sense of immutability, isolation, mutation is isolated, and we don't create these side effects. But we also have the ability to have pointer semantics. What is pointer semantics again? It means that we're sharing. We're going to get efficiencies. But because we're sharing it, mutation has to be dealt with either through synchronization, orchestration. We have to understand the effects mutation can have because they can create side effects throughout our application. Now, what you're seeing on line 22 is the value semantic form of the for range. There's a few things happening here. We're going to be ranging over this array of strings called fruits. And on every iteration, we're going to get the index position, 0, 1, 2, 3, 4. And this local variable to the for loop, notice we're using the short variable declaration operator. This local variable to the for loop is going to be a copy of every value that we're iterating over. So in other words, our fruit variable, that ends up also being a 2-word string value and a copy as well. And after that, if you notice, we now have three string values on the board, all sharing very efficiently this one backing array. Now, we're not done yet because I want you to look on line 23. On line 23, we're calling print. And when we call print, look at what we're doing in the second parameter. We are passing fruit. But what are we really passing? What is the data? We're passing a copy of the value of fruit. What does that mean? It means in the stack frame below us, we now get a second, or now 1, 2, 3, 4, our fourth string value that is sharing the backing array. Think about this. I've got this on our stack frame here, this on our stack frame, this in the data segment, and now this in the stack frame below us. 4 string values sharing with efficiency the backing array. What I really want you to notice is how powerful this is. I've got 5 values on the board. 1, 2, 3, 4, 5. And yet, because we're using our value semantics here and our pointer semantics here, think about it. The only thing that ever would have to be on the heap, if anything, and nothing here is on the heap, it's a literal string. But let's say it wasn't a literal string. Let's say that the string was created dynamically. Then the only thing that would have to be on the heap is this one thing. Everything else can stay on our stack. I want to stress that our job is to identify and balance when do we use value semantics, when do we use pointer semantics, and to balance that and to try to minimize allocations the best we can. Look at how powerful the string is. The string value is designed to be leveraging value semantics. It's designed to be copied. And when something's designed to be copied, we have a great chance of keeping it on the stack. The only thing that has to allocate to the heap is this. What this means is that the garbage collector doesn't have to deal with 1, 2, 3, 4, 5 values. It only has to deal with 1. And there's a chance that that value also maintains a longer lifetime. Do you see what we're talking about here? Your value and your pointer semantics are important. They're critical. They're critical to everything you do for optimizing for correctness and performance. And so we have to continue to talk about these semantics as we continue to talk about code and start to really appreciate the balance that we have to have. And again, when to use those value semantics and when to use those pointer semantics. It's critical. Now, I want to share with you the idea that these semantics really go deep into the language. This is not anything that I'm making up. I'm not making this up to make a point. These things are real. The value and the pointer semantics are very real. And I want to show you that with this particular piece of code right here. Now, what we're going to be able to do is predict the output of this code because we understand the semantics. Remember, mechanics is about how things work underneath. Semantics are about how things behave. Now, before I run any of this code, I want to add an extra print line here so we can just kind of break the output up. And what we're going to start with is on line 12. Now, on line 12, we declare that array of strings again. Here we do it again. Let's just map this out on the board. We kind of already have it here. And we can reuse this, no problem. And what you notice right now is we have this array of friends, right? It's the 5 strings again. The first one there is going to be Annie. I'll just put A. The next one over there is Betty. And then we've got Charles. You see that? And those integers are going to be what? 5, 5, 6, right? So 5, 5, 6. No big deal. You're getting a sense of that. What's important right now is this. OK. Now look at what I do on line 13. On line 13, I say display the string at index 1, which is Betty. So we should see Betty when we run the program. There it is. But now let's go into the for. Now what you're seeing for the first time is what I would call the value semantic form of the for range. This time, all we're asking for is the index position on every iteration. Remember before, we were using the value semantic. We're asking for an index position and a copy. What does value semantics mean? We're always operating on our own copy. But this is the pointer semantic form of the for range. Now, on the very first iteration of this loop, we change out Betty to be Jack. We change this out. This now says Jack. Great. And then we iterate again. We get to index 1. We replace Jack with Jack again. It's very inefficient. It's not the point of the algorithm. What the point is that on line 18, once we're iterating over 1, I ask to display the value at index 1. And we should see Jack. And if I were to run this program, we would see in the output Betty and Jack. Not surprising. Exactly what we would expect. OK, let's take the same algorithm, the same piece of code, but this time let's use the value semantic form of the for range. So we start up all over again. We've got Annie. We've got Betty. We've got Charles. We keep going. And I display the string at index 1 again, which should be Betty. Now, the one thing that we've changed in this code is we're now using the value semantic form of the for range. Notice again, I go in, and on the first iteration, I change Betty to Jack. No big deal. We change it again. Everything looks the same. We do it a second time, and on the second time, we print V. Now, we would assume that V would also be Jack because we changed it out before we got to the second iteration. But notice the output. It still says Betty, and then it says Betty again. What is going on? Understand this. Value semantics mean that we're operating on our own copy of the data. When I say this for range is using value semantics, what it means is the for range in this form makes a copy of the array it's iterating over. It's not iterating over this array, friends. Before the iteration started, it made its own copy of this. It made its own copy, which means that it's pointing to its own Betty and Charles. We're not iterating over this. We're iterating over the copy of this. That's what value semantics are all about. That is the behavior. I've told you over and over again, if you don't understand your mechanics, and more importantly, don't understand your semantics or your behavior, you cannot predict how this code's going to run, and therefore the impact that it's going to have. Very, very interesting. And it's going to be important to choose the right form of the for range based on the data that you're operating on. What we're going to learn at some point is the data drives the semantic. And whatever semantic we're supposed to use for the data, we have to be consistent and clean throughout our code base. We're going to continue to see this over and over again. But let me show you something that I never want to see in code. I've tried to tell you several times that if you mix semantics, code becomes complicated and hard to read. But look at this code here. We're using the array of 5 strings. There it is. we display Betty like we did before, no change. But look, I am going back and using the value semantic form of the for range. However, I'm not making a copy of the array like I did before. This time, the value semantic form of the for range is making a copy of the array's address. That means that when we iterate on this for range using value semantics, we're actually doing it over pointer semantics, which means that when we update friends, we're updating it indirectly through the pointer, and we still see Jack. This code is so nasty and confusing. It makes me sick. We cannot be mixing semantics like this. This is when code gets ugly, it gets confusing, it gets impossible to read, and impossible to predict. So I'm going to be stressing over and over and over again that we do not want to be mixing semantics. We're going to look at our data, we're going to understand our data, we're going to choose our data semantic, and then all of the code we write will follow and respect the semantic, not the other way around. Now, for those of you who might be a little new to arrays, remember that we said that the array provides that contiguous block of memory. So look at this code here. I've got that same array of 5 friends. We're going to range using our value semantics. But what I'm going to do is ask for the address right here at the end of every single element and what that is in memory. And what you're going to see is when we display the addresses here, you'll see that we're at 150, 158, 160, 168. You're going to see 2 things in this output. One, every one of these elements are next to each other. They are in a contiguous block of memory. The other thing you're going to see is the predictable stride. Remember, a string on the playground is 8 bytes. 2 words, every word is 4. 4 plus 4 is 8. And so what you're seeing is an 8-byte step through the array. That is our predictable stride, 8 bytes. You could see it on the address. We also talked before, remember, about alignments. So we shouldn't be confused that an 8-byte value falls on a 0, 8-byte alignment. Everything that we've talked about is coming together. But what's important again here is that we do have a contiguous block of memory. We see those addresses are next to each other. We see the predictable stride. And again, the hardware loves this because the prefetchers are going to be able to come in and make those great predictions over the cache lines that this data is on. And we should get some better performance because it's about how efficiently we get data into the processor, not how fast we pump it. So we just finished talking about arrays, and I showed you a lot of mechanical sympathies around that, and we started seeing more of the value in the pointer semantics around that. But slices are the most important data structure in Go. This is something that you must learn, you must master, you can't cheat on, because all of the data you'll be working with, or at least the majority of it, should be and probably will be stored in slices. This is your go-to data structure. Are there times where the slice is not reasonable and practical to use? Absolutely. But right now, until you know that it's not reasonable and practical, this is the direction. And a slice of values over a slice of pointers, again, when it is reasonable and practical. Let's start off with some slice code right here. Now, notice that I'm using the make function. This is a built-in function in Go. And what it does is allows us to create 3 of the reference types that are also built into the language. Up until now, we've been using the built-in types, and we've been using our user-defined or struct types. Go has another class of types called reference types. That is going to be our slice, our maps, our channels, our interface values, and our functions. They're all reference types. They're reference types because they are data structures that have a pointer. They're also reference types because when any of these types are set to their 0 value, if we create a variable of a slice or a map and they're set to their 0 value, they're considered to be nil in this language, just like a pointer set to its 0 type is nil. A string is actually very close to being a reference type. The problem is that when a string is set to its 0 value, it's not nil, it's empty. So I can't really put it in that class. But we're using the built-in function make to create this slice. And we're going to use make when we already know ahead of time what type of, how much memory to allocate towards its backing data structure, which is an array. So once this make call is done on line 13, what we really have is this fruits slice. Now a slice is a 3-word or 24-byte data structure on our AMD 64 architectures. And it's very similar to the string, where you get a pointer and you have the length of bytes. In this case, not bytes though, but the length here of 5, which means we're going to have 5 strings. So what we're going to end up here now is an array of 5 elements, 0, 1, 2, 3, 4, and our pointer pointing to that. So kind of similar to the string. But we end up also having a third value. That's why it's 3 words. This is capacity. And when the length is only set on the make call, then the capacity matches the length. So here's the question. What is the difference between length and capacity? Length represents the total number of elements you can access from this pointer position. And I want you to know as well that the make call is going to set all of this here in the backing array set to its 0 value state. So length is the total number of elements that you can access from that pointer position. Capacity is the total number of elements, period, that exist in the backing array from that pointer position. Capacity can be larger than length, but not the other way around. Now, in this particular case, I've initialized it with apple, orange, banana, grape, and plum, and the same costs apply that we saw before. We're only going to have to copy the 2-word string value. Now, if you try to access a slice beyond its length, like you see on line 21, then we're going to get a runtime error. This would be like going past the bounds of an array. Your length sets the bounds, just like an array has a bound that's set at compile time. And this is also really important. I want you to notice that we're passing a value of this slice into the print call. In other words, the slice value, just like the string, is designed to be using value semantics. As we're going to learn, our built-in and our reference types are designed around value semantics. They're designed to be kept on the stack. Notice again, I've got this slice value on the frame here. Below us now, on the frame below, the one for print line, we've got this string value. And thanks to the pointer, they share the backing array. There's efficiency in sharing. And we also have consistency in copy cost. This array could be millions of strings, but as we pass it around these program boundaries, the cost is always consistent. It's 24 bytes. How beautiful is this? The only thing that has to end up on the heap, if anything, and in this case right now it doesn't, but the only thing that have to end up on the heap is the thing being shared, the backing array. This is beautiful. This is that balance and minimizing allocations and only allocating those things that need to, which are the things that are going to be shared. Again, right now there's no reason for this backing array to allocate because we know the size of it at compile time. We've given the compiler a very specific number here, 5. We're never leaving the stack frame. So they won't necessarily have an allocation here. This should be on the frame. But in the end of the day, if we end up making a copy of the slice value and passing it up the call stack, well, that's the only thing that would have to allocate. All right. Now, let's take a look at a slice where the capacity is larger than the length. Here I am again using the make call. But instead of just saying 5, I've said 5, 8. What I've now said here is I want a slice whose length is 5, but also has a capacity of 8. And what that basically means is that I'm going to have 3 more elements right in here, 3 more elements, 1, 2, 3, 5, 6, and 7, where we have extra capacity. And capacity is for growth. I want you to remember that. Length is what we have access for today, and capacity is for growth. So we have the ability to grow this slice beyond that length of 5 here efficiently up to 8 elements. Capacity is there for growth, but efficient growth. There we go. Now, there's a function here that I wrote called inspect slice. We're going to use this in some of the other examples that we're going to go through. The first thing I want you to look at is the parameter. see how we're declaring the slice value is what we want, right? There's no value in here. If I put a value in here, we have an array. Now I'm asking for an array of 4 strings, right? An array of 4 strings. Now I'm asking for the 24-byte slice value. That's what I'm asking for. Again, as we're going to continue to talk about, I don't want to see you sharing the slice value. It is designed to stay on your stack. It's designed to be using value semantics. We should be making copies of it. So if we want to display this in spec slice, we'll end up getting its own copy of the slice value, the 24 bytes, there it is, and in spec slice will operate against its own copy. Now, there's 2 other built-in functions that you see us using here. One is called length. Length is used both just for maps, it's used for slices, it's used for channels, and you have capacity, which is isolated just to slices, and slices are the ones that have a capacity. That would give us the values of 5 and 8 when I run this code. If I run it right now, we should see this output length 5, capacity of 8, and we should see the contiguous block of memory. Notice as I'm ranging over the slice using value semantics, but I am asking for the address of every element. You could see that this memory is contiguous, and we have an 8-byte stride, 08, 08, 08 for every string. All of that is predictable because we know that the string is an 8-byte value on the playground. So our inspec slice function we're going to use very soon to do more, because one of the problems with slices is this pointer. This pointer means that as we begin to start doing things like mutation, we could create side effects, and it's something that we have to be aware of when we're working with this data structure. So there's 2 things that we do with slices all the time in Go code. We append values to them, and we take slices of them, which is where the name comes from. Let's start with the idea of appending. So let's go ahead and start right here on line 13. Now, on line 13, this is very interesting. I'm using the keyword var. Remember, var is an indicator for us that we're using 0 value. In fact, what we're doing here is creating a slice named data, but set to its 0 value. So this slice looks like this. A 0 value slice would still be 3 words, but everything is set to its 0 value. All those bytes are set to 0, right? They're 0 bit. And we call a slice that is set to its 0 value a nil slice. Remember, when it comes to a reference type, anytime a reference type is set to its 0 value, we consider it to be nil. Interfaces, channels, maps, slices, functions. There you go. But I want you to see something here which I find very interesting. I find lots of things interesting with Go, but this is one of them. We talked about before that when we're dealing with struct types, that an empty struct literal will give you 0 value. Here's a case where the empty literal for the slice will not give you a 0 value. What that code does on line 14 is creates what is called an empty slice. Now that means the empty slice isn't zeroed out, and there isn't. Though the length and capacity are 0, we still do have a pointer. Now we need this semantic, because imagine that you made a database call, and the call completed. It wasn't an error, but it didn't bring back any data. I mean, that's not really an error. It just means that the query had an empty result, empty. So this concept of empty is a really important semantic when it comes to collections. And this is what Go is giving us. So we use var for 0 value. We got a nil slice. Would want to return on an error. If we use the empty literal construction, like you see on 14, we end up with the empty slice. And that would mean that everything was OK. There was no error. It's just there wasn't anything. Now, I'm sure you're asking, Bill, if this is empty and there's a pointer, where is it pointing to? Well, there's another special type in Go. It's called the empty struct. And the empty struct is declared like this. What's interesting about the empty struct is that it's a 0 allocation type. I can create a million values of this empty struct, and there would be 0 allocation. And that's because there's an 8-byte value tied inside the runtime, like a global variable, that this empty struct is referencing. That means all million empty struct values would have the same address. So basically, this pointer points to the empty struct. That's what it does to represent empty. Really cool stuff. OK, let's go back to our original code here. This code is showing you appending. And so we're going to start with our nil slice. It makes sense to start with a nil slice anyway, because unless you know exactly how much data you need, we don't want to pre-allocate the backing array. That is a waste. Remember, it goes about minimizing resources. We'll take a small performance hit to do that. And even that performance there will only even show up on a profile, right? I mean, it's so low in the areas of where we're going to be losing performance. So let's start with the nil slice when we don't know. If we know exactly what we need, then it is inefficient to do that. We should use the make call to pre-allocate length or capacity. So we're starting with our nil slice. And what this code here does is it goes ahead and it adds like a million or five zeros there, right? So 10,000 right now, 1, 2, 3, 4, 5, 6, 100,000, sorry. 100,000, I had to do the math that quick, right? My brain is shutting down. 1E5, add 5 zeros. So we're going to add 100,000 strings to our nil slice and just keep appending values up to 100,000 of them. And I want to show you how this works, and we'll look at the output. What this program does is outputs every time changes are made to the backing array for the slice. Now, what you also see here on line 22 is our sprintf function. We're just generating a string based on the record ID. And then we go ahead and we call append. Notice that append, notice the API for append. This is important to me. The API for append is really using value semantics. I love append because append is what we call a value semantic mutation API. Notice that append does mutate, but we're not using pointers, we're not sharing. Append gets its own copy of the slice value, mutates it, and returns it back. This is critical. Append is able to do mutations in isolation without causing side effects because it's leveraging a value semantic mutation API. Plus, I told you, slices should be using value semantics. We'll talk more about that, I promise you, when we get to methods. But it's using value semantics, so the APIs have to respect it. OK, great. Let's walk through the first 5 appends here, and we'll get a sense of how append works, and then we'll run it for 100,000. So on the very first call to append, the append function gets its own copy of the slice value. Again, we're using value semantic mutation. There it is. Now, append is really just going to ask one question. It wants to know if the length and the capacity of the slice value it just got a copy of is the same. Because if it's the same, then what that tells append is I don't have enough capacity for this append, and I need a new backing array. In this case, there isn't any backing array at all. So it will create one. It will mutate in isolation its own copy of the slice value, there it is, and make that modification. And now return a copy of that slice value back out to the caller. Everything is nice and safe and clean thanks to our value semantics. And the caller now gets a new slice value pointing to a new backing array. Let's do it again. We call append again. It gets this copy again. It asks the question, is length and capacity the same? The answer is yes. Oh, we got no room for this append. Let's allocate a new backing array. We now get a new one. This means that we have to copy A into here, and now we go with B on the append, which now also means that we're going to mutate right here, our slice to point here, and we now have a length and capacity of 2. Brilliant. We return that back out by copying it, and a couple of things now happen. Our slice value is now pointing to this backing array. In fact, at this point, we have no slice values pointing to the original backing array. What does that mean? It means on the next garbage collection, this can get swept away. There's lots of little interesting things happening, even if we just stop here for a second. The first thing is that sweep makes me think of this. What is a memory leak in Go? I mean, what is a memory leak in a programming language like C, or maybe C# or C++, where you get a function called new or malloc, and you get to allocate memory? In programming languages where you're responsible for those allocations to the heap, you have a responsibility to free it. And that type of memory leak just means that you've allocated something without the corresponding call to free or delete. And we can instrument code for that. That's not really a problem when we do that in those programming languages. But in this language, escape analysis is determining the allocations, right? When append had to create that backing array, that's happening on the fly. That's in the heap. This is in the heap. We don't know about these things at compile time. These are all heap allocations, right? This is garbage collection time. This is costing us. But what is a memory leak in Go? Well, a memory leak in Go is when you maintain a reference to a value in the heap, and that reference never goes away. This is complicated because you can't instrument for a memory leak when it's reference-based. Who is to say that reference is or isn't supposed to be there at any given time? So if you think you have a memory leak, which is the only way is to look at the GC trace. I'll show you how to do that at the end of this class video when we start getting into tooling. But if we look at a GC trace, what we're going to want to see is the memory going up on every garbage collection? And if it is, we have a memory leak. And right away, one of the first things I'm going to ask you to do is take a look at this. The first thing we're going to look to see is, are you creating extra Go routines or paths of execution? Are they supposed to be terminating and they're not? It is a classic memory leak. Both the Go routine is leaking, and anything that Go routine was holding on to never gets released because it never terminates. A very classic place in Go where you could have memory leaks. So we're going to look for Go routines first. The next thing we're going to look for is possible maps. You know, lots of people like to use maps for caches. And that's great, but at some point you have to delete keys, right? Entries in your map. You have to either do it based on time, you got to do it either based on like an event, like an IP or something dropped, right? You have to do it. You have to at some point delete keys from a map when things happen, or all that does is the map just continues to grow and grow and grow. So maybe we could argue it's not a memory leak, but you know, the resources aren't forever. So you either have to do it on time, you have to do it on some sort of event, right? You have to make a choice on when the map keys get deleted at some point. You can't grow it forever. Another place where you could have a leak is right here on like on an append call. One of the very first things I'm going to look at on append call is if the slice value being copied is the same exact one that we're going to replace on the return. If I saw something like this, this would be very, very scary to me, because this could be potentially meaning that we could be holding a reference to old backing arrays because we're not replacing certain things going in. So I'm going to be looking for this because I want to make sure that we replace this and therefore reduce or remove those references to the old backing data structures. These are all really, really important. The last step might be APIs that we know about where you're supposed to call close and you forgot to call close. Classic memory leak. Okay, let's keep going here. We've done two. Now, I'm just for efficiency here, we already know we're making a copy, so I don't have to make the copy. We'll just talk about what comes back out. Okay, we pass a copy of this to append. Append looks at length and capacity, says it's the same, goes, okay, I don't have any more capacity, so I'm going to go ahead, I'm going to double the backing array, and I'm going to copy A and B, and I'm going to append C, and now the new mutation looks like this. We now point here, our length is 3, and our capacity is 4. This is the first time you're seeing a situation where capacity is greater than the length, and it's happening naturally because we doubled the size of the backing array and we only added 1 to its length, because that's all we ever do on append. We add 1 to the length. We have a length of 3, capacity of 4. This is great. We have an element of capacity now for efficiency and growth, which is going to happen on the next append. On the next append, we ask, is length and capacity the same? The answer is no, it's not the same. This is brilliant. We don't have to do a copy anymore. We can just bring that capacity into the length. Boom, 4 and 4. But what happens on this very last one? We're going to do one more on the board. Length and capacity is the same. OK, no problem. Now we're going to double the size of the backing array again. We're going to have to copy all this down. And what are we going to end up? Well, length increases by 1, 4 to 5. And in this case, the backing array is doubling in size, 4 to 8. And now we have 3 extra elements of capacity ready to go without the cost of the copy. OK, I want to run this for 100,000 iterations and show you something interesting about the append algorithm. Now, you can't change the append algorithm. It's there. But what's interesting about the append algorithm is when we finally get to a slice that has a backing array that's at 1,000 elements. You see, before 1,000 elements, append doubles the size of the backing array on growth. That's what I was doing on the board. But once we get to 1,000 elements, the algorithm is using 25%. It uses 25% growth over time. And so the backing array won't double, but it will grow by 25%, which gives us 25% of efficient growth moving forward without, again, the extra allocation. But everything you're seeing here on the screen in the output of this program is technically an allocation. All of these allocations had to take place to add the 100,000 strings. Now, what's interesting here is we know what this is. It's 100,000 strings. We know what our capacity already is. So ideally, if we were going to be more efficient, I wouldn't want to start with the nil slice. This is an opportunity where we can set the capacity ahead of time. Notice I'm setting length to 0 and capacity to 100,000. Why? Because append works off of length. If I set the length to the 100,000, then we're going to have 100,000 zero-valued strings and another 100,000 actual strings. We've got to remember that append works off of length. Now, if I run this, we won't see any output. Why? Because we never, ever have to make a copy of the backing array. That never, ever has to happen. But we could even be more efficient here. We could literally just get rid of the append call by just indexing everything that we need. If we start at 0 here, then what we could just do is use the index position and do the assignment. This is even more efficient because we don't have the function call anymore. But now this is a case where we have to set up length because we've got to make sure that all of that is available for use up front. So you can see here that if we don't know what our capacity is, then guess what? We don't know length of capacity. Let's start at nil. Append will help grow and do that as efficiently as it can. But if we do know exactly what we need up front, let's set that length of capacity, get away from the append call, and then everything is going to be great. All right, now let's really learn why slices are called slices and the efficiencies we're going to get out of using pointers. This is really important stuff. Again, slices are your most important data structure when you're coding in Go. So let's start off right here. We're going to make a slice of strings again, and we're going to start with a length of 5 and a capacity of 8. And this backing array is going to have that capacity of 8. We're going to point to it. And we're going to have apple, orange, banana, grape, and plum. Apple, orange, banana, grape, and plum. And you can see here we've got the 3 extra elements of capacity. Remember, length is what we are allowed to access. That's these 5 elements here. Capacity is there for future growth. And I'm using my inspect slice function that we were looking at before. Now I'm going to add some extra print lines here so I can just look at the output of this very first slice. And you can see here, length 5, capacity 8. We have a contiguous block of memory underneath, apple, orange, banana, grape, plum, 0, 8, 0, 8, 0, 8, 0, 8, all the way together. OK, great. So we've got that in place. Now, one of the important things about a slice is the efficiencies that come with it as it relates to the data we're working with. And what you want to see here on line 24 is our slicing syntax. What you can do is take any existing slice value, like we have here, and create a new slice value, sharing the backing array for efficiency. The idea, again, is the only thing that has to be on the heap is the backing array. If anything has to be on the heap, if it has to escape, the only thing that should ever escape is the backing array, the thing being shared. Our slice values get to stay on our stack. So what this syntax is saying is take your slice, and what we're going to do is say A comma B. And what that A comma B means is index A through index B, A through B. Now, the first value is very, it's intuitive, 2, index 2. And what that is saying is let's create a new slice value where the pointer is going to point at index 2 of slice 1. Okay, we get that. That's no problem there. That should mean now that we're going to be basically starting here as it relates to this new slice, which also now means that that's going to be index 0 of this second slice. But the b value is a little bit more complex. I wish it wasn't, but it is. And what this syntax really means is it means go index A through B, but not including B. In other words, indexes 2 through 4, not including 4. Now, when we say not including 4, then what we're saying is that we want a length of 2, because our length is only going to be able to access indexes 2 through 4, not including 4. But our capacity is always going to be the total number of elements from that pointer position, which is 1, 2, 3, 4, 5, 6. So here we are. We have 6 elements on the capacity side, 2 elements on the length. Now, I hate this idea of 2 through 4 not including 4. It's too complex. What I like to tell people is if you don't know your length, you shouldn't be slicing. Your length is everything when it comes to slicing. So what I like to do is think of the slice like this. Let's start at index A, or 2. But then let's do A plus whatever length you want. And if you always slice with the idea of length, guess what? You'll never, ever make a mistake. And that's what we did here. We said start at index 2. I want a length of 2, so 2 plus 2 is 4. There we are. We've got our new slice. And now what's very brilliant about this is if I run this code, what we see is the original slice had a length of 5 and a capacity of 8. There it is, working through Apple through Plum. But our new slice value is only a length of 2, capacity of 6. Notice that when we range over the slice, we're only ranging over its length. But also notice that banana and grape in both slices have the same exact address. Look, that really shows you that we are sharing this backing array, and we're sharing it efficiently. This is the only cache line that has to be cached by the core that's working at these 2 different slices, right? These slice values are like a view, a unique view of the core data structure, the larger structure here that we're going to be sharing. And we have that. But I told you that pointers are dangerous. Sharing is dangerous. Pointer semantics can be dangerous because of side effects. And I want to show you some of these side effects right now. Look at what I do on line 30. On line 30, I take slice 2 and index 0. Notice something. Banana can be accessed in 2 different ways. Index 2 on slice 1 or index 0 on slice 2. This is very, very dangerous. I got 2 different ways to come in and do this mutation. And I use slice 2, index 0, and I come in and I change this out. Here's that concept of a side effect, right? Let me put those print statements back in here. And now let me, after we make this mutation on line 30, let me display the value of both slices. And what you're going to see is that both slices see the change. We see it in index 2 on slice 1. We see it in index 0 on slice 2. This is really the beginnings of a nasty side effect. What if we didn't want slice 1 to see this change? What if we wanted to isolate this change just to slice 2? At this moment, we can't because we're sharing the backing array looking for those efficiencies. All right, let's put this back for a second, and let's try something else. Let's go ahead and instead of going right into that index position and making that change, why don't we try to use the append call? So in other words, I'm going to come in here. I'm going to say, let's use append, and we'll append it to slice 2. Now, what kind of behavior should we see when we use append? Maybe life will get better for us. I don't know. Let's take a look. So we go ahead here, and we say, let's append the new value to slice 2. So append gets a copy of the slice value. It says, is length and capacity the same? The answer is no. Brilliant. We can add to the length because we have the capacity. But what's going to happen now is append is going to bring in this element right here. It's going to bring that element in. And when it brings this element in right here, right, here it is, it brings it in. This will now be index 2. Well, what happens? Well, since we brought that index in, we now have to go ahead and replace the value that's there, and we'll replace it with change. Look, we just replaced plum out for change. Who's going to see that change? Guess what? Everybody sees it again. We didn't really fix our problem. We didn't get rid of our side effect. All we did was move it 2 indexes down, because the append brought in an element that was already in use by slice 1. This is really scary, nasty stuff. But let me ask you a question for a second. Let's put this back again the way it was. Let's pull this out. All right, we'll pull this out again. I'm going to pull all that back out. We're going to make that plum again. And let me ask you a question. The whole problem with append was that our length and the capacity were not the same. But what if length and capacity could be the same when we make this slice? What if this could be 2 and 2? I mean, if we, during the slicing operation, could add a third value and say, let's not just adjust the length of this new slice, let's also adjust the capacity to also be 2, A through B not including B, and A through C not including C. If we could adjust the length of the capacity to be the same, what would append do? Well, append would say, do I have any extra capacity? And the answer would be no. And append would basically give us a copy on write. Look at what happens when I run this code. Notice now that we don't have a length of 2 and a capacity of 6. We have a capacity of 2. We're still sharing the same backing array. But now after the append, look at the addresses for banana and grape. They're different. On this call to append, we made a copy of just the elements that we were working with, and we're good. Copy on write. We just got rid of the side effects because of the 3-index slice. 3-index slices are fantastic to help reduce side effects. When you know you're going to be doing appends on a second slice value and you don't want those mutations to affect the original or other slice values that are sharing the backing array. Very cool stuff. But there also may be times where you have to maybe manually do your own copies. Try to avoid these, but sometimes you have to do it. And that's why Go gives you the built-in function copy. And the built-in function copy will let you take the source of one slice and make it the destination of the other. You can see here that I'm making a slice of the same length as our slice 1. I'm using slice 1 as the source, slice 3 as the destination, and you'll see that slice 1 and slice 3 have different memory addresses when we do this, because they're really, at the end of the day, this is going to have its own memory address, slice 3, because we've manually did the copy as opposed to using the 3-index slice. So you're starting to see how pointers give us levels of efficiency, right? Sharing means that this data is not duplicated, which means the hardware only has to worry about copying this one thing. We get to reuse it. We get to create different views. But you can also see that now that we're sharing data, we have different ways of getting to it, and therefore different ways to mutate it. And now we've got to become careful about when we're mutating, and we're not mutating behind someone's back to the point where they didn't expect it, and now they're going to have problems with the data. I want to show you another piece of code here around the idea of side effects and how dangerous they can become if you're not aware of it. And this is all I'm trying to do. I'm not trying to scare you away from the data structure. I'm not trying to make you go and have to use the built-in function copy all the time. That's not it at all. I just want to continue to iterate that when you're using pointer semantics and we're mutating memory, We have to be aware of the side effects. This is what makes programming difficult. Your functional programming language friends don't have to worry about this stuff. Functional programming says everything is value semantics. Every piece of code, every function we call operates on its own piece of data, but we don't get all the efficiencies we need to have the fastest programs that we want. And this is why Go is brilliant in giving you the responsibility of both value and pointer semantics, but we have to be aware of when we're using what, and when we're using the pointer semantics, we have to be aware of the mutations and the problems they can cause. So let's take a look at this program here. I've got a user-defined type called user, and the idea is that I have a system of users, and we're going to track likes for this user. We're going to track likes throughout the app. Now, let's just say I have a small system, and we start the system up, it starts running, and we only have 3 users. So I go ahead right here in this program, and I create my slice. Here it is, my slice of 3 users. There they are. Now, this is set to its 0 value. It's a slice of users, so I don't know why I'm writing strings here. Funny stuff, Bill. But we're just going to maintain our likes here. And we know right now that these users start with 0 likes. And let's just pretend we're going to use the index position and bind it to a user value. So there we are. We've got users 0, 1, and 2. Their likes are set right there. We've got a length and capacity of 3. Now, I go ahead like I would normally do in a program, and I want to share the user 1 right here. I want to share it. And I create some sort of pointer that now points to user 1. It's very possible that I'm going to do this. I want to share that user down the call stack, some other part of my program that's handling likes on some event, so we can continue to increment this. And in fact, on line 23, what you see is through the use of the share user pointer, we increment the value that the pointer points to. After line 23, this user doesn't have 0 likes, they have 1. Brilliant. But guess what happens? If you notice here on line 26, and I'll add some extra print statements here so we can isolate the output on the screen, we should see that that user 1 has 1 like and the others have 0. And there it is. User 0, no likes. User 1, 1 like. User 2, 0 likes. Brilliant. It's exactly what I wanted to see. Now, the system is running, it's dynamic. Some user now registers on the system, and we go ahead and do what I would expect us to do. We append a user. But watch what happens on the append. Is length and capacity the same? The answer is yes, it is. Uh-oh, what does that mean? It means that we're now going to have to create a new backing array. Well, our new backing array will be doubling in size, and our length and capacities are going to change. Suddenly, we're going to have a length of 4, but a capacity of 6, which also means that all of this data is going to have to be copied. And it will. Here we are. And we now point to this. Notice what has just happened. This pointer that was pointing to this backing array is still pointing to this backing array. But this is no longer our data. This is now our data because of the append, which means that if I continue to increment likes for the user, like you see on line 34, guess what? They don't get registered. And you might think, Bill, this would never happen. This would never happen. We're incrementing this. We're not incrementing this. But this is the data that we're working with now. And guess what? We kind of have a memory leak in a sense that this memory can't get released because of this pointer right here. And you might think, Bill, this would never happen. And I know some of the best Go developers on the planet who have created bugs like this, not thinking how append, when length and capacity are the same, is going to make a copy of the current data, which is the point of truth, and now make this the point of truth. And yet we have these pointers now working against the old data structures. This is a side effect. These are the nasty bugs that are so hard to find. And so anytime we're working with pointer semantics, that's great. It's going to give us levels of efficiency, right? We have to be careful there, but we also have to make sure that we're very clean with data updates, like with slices, and that our mutations are not going to cause problems, or the mutations are happening in the wrong place. This is just a program to show you what a side effect really can look like in production level code, and how careful we have to be when we're sharing these slices beyond program boundaries especially if the call to append is going to happen. And one of the things that I do a lot is anytime I see a call to append in code, I immediately put the brakes on the code review, because append can create some of the nastiest side effects you've ever seen. So unless the code is decoding or in marshalling, usually an append call is somewhat of a smell, and it's not necessarily wrong, but we're going to have to double and triple check that we're not causing some sort of side effect with a backing array that's going to get replaced. I want to show you again more practical slicing code, and at the same time teach you a little bit more about what strings are in Go. So let's take a look at this sample program. Now, strings in Go are UTF-8 based. In fact, the entire language is UTF-8 based. If you're not saving your source code as UTF-8, you're going to have a real problem with those literal strings and raw strings that you're storing inside your code files. Everything has to be UTF-8 encoding all the way through. Now, what's interesting about UTF-8 is that it's a 3-layer character set. You have bytes at the very bottom, and really we would always consider strings just to be bytes at the end of the day. But you've got bytes at the bottom. In the middle you have what are called code points. And a code point is a 32-bit or 4-byte value. And then after code points you have characters. And the idea is that a code point is anywhere from 1 to 4 bytes. And then a character is anywhere from 1 to multiple code points. You have this kind of like n-tiered type of character set. So let's take a look at some code here. On line 38 here, I have a literal string. And this string actually is going to be a literal string of 18 bytes. Why is that? Well, if we look at what this string is, it's going to be 18 bytes. What you're going to see is that the array of bytes, all right, I'm just going to draw out a bunch of them till we get to 17 there. That first Chinese character that you see, the very first one, that requires 3 bytes of encoding in order to store it. 3 bytes, which represents 1 code point to that 1 character. And the next 3, also, the next Chinese character there is 1 code point that requires 3 bytes. This is why we're getting to 18. 3 bytes, and then everything else is 1 byte all the way through. Now, I want you to look at the next variable. Notice that we're creating a variable named buff. But buff is an array. It's not a slice. Okay? This is a constant in Go, which represents the max number of bytes you need for a code point. So buff is an array of 4 bytes. That's our buff. And that is also set to its 0 value. See the use of the keyword var. Now things start to get interesting here. I'm about to range over the string. And it might be interesting to think, I mean, wait, I can range over a string? Yeah, you can range over a string. Notice we're using value semantics here. But what's important here is that we're going to get the index position and then a copy of what? I love this question. When we range over the string, we're going to get the index position of what, and we're going to get a copy of what. You have 3 choices. We could get a copy of every byte, we could get a copy of every code point, or we could get a copy of every character on iteration. A lot of people want to tell me that I think we're going to iterate by character. What we're really going to do is be iterating by code point. Code point by code point, and the index position is going to respect that. So what does that mean? It means that on the first iteration, we're going to start at index 0. Absolutely start at 0. But on the second iteration, the next code point, this is the first code point, the next code point is going to start here, 3 bytes in, because that Chinese character has its own code point that's also 3 bytes, which means on the third iteration, our next code point is here, then here, then here, and then here 1 byte away. So when we range over a string, we're ranging code point by code point, which means R is going to give us back in that position the code point that we just iterated over. R represents the type rune. And rune really isn't a type in Go. It's an alias for int32. In fact, the type byte really also is an alias for uint8. But R represents rune, our 32-bit, right, our 4-byte value. So look how this code works. On the first iteration, what's going to happen? On the first iteration, I equals 0. That's where we're starting, right here. 0, 1, 2, 3, 4, 5, 6, starting at 0. We get the rune length, and the rune length is going to tell us how many bytes we need for this code point. That's going to be 3. We needed 3 bytes for the first code point. Then I created the string index position, which is the sum of both of these values. That's 3. And now we get to line 54. And line 54 is interesting to me. We're using the built-in function copy. And copy says destination source. I want you to notice copy works with both slices and strings. But since a string is immutable, it can only be a source. I also want you to notice that we're slicing the string here. Now, that's not going to create a slice value. That will create a new string value. So look at what we're doing. As the source inside the copy, s bracket I colon si, we're saying create me a new string value. Here it is. That starts at index position I, 0, through 3. That's going to give us a length of 3. So basically, what we're going to end up having is a pointer that points here with a length of 3. That's our source. Now, what is our destination? Our destination is the buffer itself. We're saying that we're going to copy this into the buffer. But there's a problem. Copy only works with slices and strings. It doesn't work with arrays. Buff is an array. But notice something here. This buffer, this array, the syntax in Go allows us to apply by slicing syntax to an array. One of my favorite sayings in Go is that every array is just a slice waiting to happen. And this is what we see here. So in order to be able to use the array as the backing array, that syntax that I've highlighted will create a new slice value using the backing array as our storage and setting length and capacity to 4. This is brilliant. I can now use our local array in the copy, and we could tell it to just copy the first 3 bytes. So these bytes here come into here. There you go. And we've copied this data. I'm trying to give you a sense of what this program is going to try to do is range over the string, code point by code point. We're going to store that code point inside of our local buffer, and then we're going to display information about it. And if you notice here, I'm slicing the buffer one more time. And this time what I'm saying is I want to make sure that the length in this case is only 3. So I'm saying from the beginning to RL, which is 3, which will now do this. And that way we only display those 3 bytes. Now on the next iteration, what happens? Well, on the next iteration, we come back and we're going to be here, which now means that I isn't going to be 0. I is going to be 3. The rune length is still 3. SI is still now 6. And we go ahead now, and this time we're going to create a string value. It will still have a length of 3, but it will start here. And we do it again. And then after that, it will be 1, 1, 1, 1. So if you look at the output here, you could see that we're ranging code point by code point through this string data that we have, code point by code point. You can see the 3 bytes for the first Chinese character, the next 3 bytes for the next Chinese character, and I'm even able to display those characters out the way you see it right there. And then we ended up going into single byte characters all the way through, and you can see what those values are. So really cool, more practical code, and we learned a little bit more about how strings work in Go. Now, I showed you the range mechanics, the idea that a for range has both value and pointer semantics when we were talking about arrays. But I also want to show you the behavior that you can get with the same range mechanics when we're working with a slice. So let's take a look at that next. Now, here it is. It's very similar to what we saw with the array, but we're only going to look at 2 versions of this. And I'm going to put some print statements in here just so we can isolate the output and talk about each one individually. Now, let's talk about this first one. Here we go. So I start with my slice of strings. We know that we're pre-populating it using our literal construction. There it is, Annie, Betty. So we're going to have 5. We're going to have 5. Here we go. We're going to have our 5 strings. 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. There it is. And what do we have? Annie, Betty, Charles, and Doug, right? Annie, Betty, Charles, and Doug. Here we are. We have that again. What was that last one? Ed. Yeah, out of my name of my business partner, Edward. There they are. And we're using our for range. We're using our value semantic form of the for range right there on line 13. Now, when we use the for range, right, in our value semantic mode, that means we're making a copy of the value that we're iterating over, right? Which means we're going to be making a copy now of the slice value. So this is what we're going to be ranging over. This is our copy right here, hidden behind the scenes, behind the for range. And this is what our friends are right here. This is our friends. And we're not ranging over this slice value. We're ranging over this slice value. Now, we're going to iterate once, right? So we're going to get that Annie. But I want you to look at the next line of code. Notice that what I'm doing here is I'm slicing the friends slice, right? And I'm saying beginning to 2, which means what? Which means that what we're going to do is be replacing this slice value right here while we're in the middle of iterating to say, no, 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 we're going to have a length of 2. Only a length of 2 here, right? And pointing right here at the beginning. So what that now means is, still have 5, that from this slice's perspective, there's only 2 elements in the backing array. But this shouldn't cause us any pain because we're not ranging over the slice that we just mutated. We're ranging over the copy, and there's still 5 elements there. I mean, if I run this, everything should still work exactly as designed. And it does. The mutation to this slice doesn't affect us because we're using value semantics on line 13, and we're iterating over our own copy. But what if I use pointer semantics and make the same change? That's what we're doing right here. Our pointer semantic form of the for range. And while we're iterating, we now perform this modification. Well, guess what? When we made a copy of the slice here, the for range already took a length of 5. It still thinks that we're going to have to iterate 5 times. Then I go ahead and I mutate the slice to say, no, we only have a length of 2. Guess what? The code underneath at some point is going to recognize that we're going to be iterating over the slice's length because we're no longer iterating over our own copy. We're iterating over the original slice, which just got mutated there on line 21. Whew. This is some nasty stuff. Again, what's beautiful about value semantics is that we're always operating on our own copy of the data. That tends to keep us isolated, tends to keep us safe. It tends to allow us to do mutations that can't affect other parts of our program. Pointer semantics, however, means that we have shared access, which means we start mutating in the middle of an operation like this, we're going to cause ourselves pain. I cannot stress this enough. Now, we still haven't learned about when to use values and when to use pointers. I've just been trying to show you that the mechanics of value and pointer semantics are very, very real. And they're really going to allow us to understand the behavior and the cost that our software has. All right, we're going to look at that third data structure that Go gives us. Remember, we had arrays, we just went through slices, and now we're going to talk about maps. And maps are just key value pairs. There's a hashing algorithm underneath. You can't play with it, you can't touch it. But like everything in Go, it's about convention over configuration. They've done a great job with all of the algorithms to make them really general purpose and work for most, if not all, of the use cases you're going to have. Now let's take a look at some of the mapping code here. Now, here's a basic right here. Here's a user-defined type. It's called user there on line 11. And then we're using, again, the built-in function make. Remember, the built-in function make allows us to make slices, allows us to make maps. We're going to see it again later when we're talking about channels. And so right here, we're making a map. Now, a map is not usable in its zero value state, even though a slice is, a map is. And it has to be made or at least constructed with that literal form, which we'll look at in a second. Once you make the map, then you can go ahead and deal with the key value initialization like you're seeing here. So here, the map is going to be a key string. We're going to be able to store user values in there, and then we're just using a standard assignment syntax here to assign user values into the map. And again here, if you really look at it, we're using value semantics, right? The map is getting a copy of the user value, not a pointer. So that means when we pull things back out, there's going to be copies. This is all user value semantics all the way through. Now once we populate that map with some values, we can iterate over it. Again, we're using the for range. Before, when we were using the for range for a slice or an array, it was index and then a copy of the value if you were using the value semantic form. Here, for maps, we can get the key and the value. All right? And again, it's going to be copies. Copies of the key, copy of the value. So remember, we're not really operating on the user value you stored inside the map. It's going to be a copy of that value. So there we are. We're ranging over it. Nothing, no big deal there. But part of this code is trying to show you that, and this has been done purposely. When you iterate over a map, it's random. It's been randomized, and they've improved the randomness throughout the years. And that's because they don't want you to write code that is assuming some sort of ordering based on how values are keyed in and then coming back out. So you have to recognize that everything is random here. And if I run this code here, you can see how on the first iteration, Jackson, Roy, Ford, Mouse. On the second iteration, you see a different Roy, Ford, Mouse, Jackson. So we understand here that when we iterate over a map, it's going to be random when you run it. Now there's other interesting things about the maps, and you have the ability to do literal construction. So here is that user-defined type again, it's user. And instead of using make and then the assignment operators, what I'm doing now is using that literal construction. Remember, we saw literal construction with structs. We saw it with our slices. We saw it with arrays. Here it is again now with maps. So this is going to construct that map, allow it for use, and we're inside the literal form there, doing the key value pairs, again with that colon there and the closing comma. And now I can iterate over that data again. There we go. But notice also there's a built-in function called delete. And delete will allow you to remove a key from the map. This is important because we talked about the potential of memory leaks. And one of the things I've seen when memory is growing out of control is sometimes people are using a map as a cache and they don't remove a key. Remember, at some point in time, if you're using a map as a cache, you must remove keys, whether that's going to be based on time, whether it's going to be based on the size, or based on some sort of event that's occurring in your application. But notice that once I remove the Roy key, right? So Roy was the first value that we placed inside the map. Once I remove the Roy key, all right, if I try to go find that key now, we're going to end up with false. And I want you to look at the syntax here because I can pull data out of a map and just ask for the value back. And if that key is not found, then U is going to be set to its 0 value. And that doesn't necessarily always mean that the value is not there. You could have stored a 0 value user for some key. So the second form of the retrieve out of the map right here, which is a Boolean variable found, is really what you want to use if you want to validate whether a key exists or not. If I run this program here, you'll see that we've got our data. I removed that key Roy on line 32, and I go ask for it, and the found variable is false. So we've got the built-in function delete to remove keys. We're going to want to do that. You can't be storing everything forever. And then you see the two forms of the retrieve where you can get the value and an indication of whether that value is there or not. Now there are restrictions on what a key can be, not a value. You can store anything you want in the map. It uses the empty interface. But when it comes to the key, it has to be something that they can execute a hash against. So always think about the key as being something that you can use inside of an if statement. If you can compare the value, then you can use it as a key. As an example of a key violation here would be on line 17. Notice how I've defined a type called users, which is based on a slice of user. This slice of user really isn't something that we can compare against. And therefore, if we try to use our type users here, we're going to get what you see on line 24, which is a compiler error that is an invalid key type. So remember that not everything can be a key, but everything can be a value. And if you can't use that piece of data in some sort of if statement, it's probably going to be a key violation. Now let me show you a few more things here Go introduced a new package called sort. And I want to show you how we could use it maybe to sort a map so we could be more predictable when ranging over a map. So here's my user-defined type. It's user, and again, storing data inside the map. Again, this is, even though we're storing it in this particular order, it's random, always going to be random coming out. So look what we do here. We define a collection of strings, right? There's our slice of keys. And we go and we range over the map, again, randomly. I don't really know what order these keys are going to come back. We append them using the append function into our collection of keys. Then right out of the box here, we can use the sort package. We can use the string function. And there we go. We're going to sort the keys inside that slice. I now have the keys ordered by alphabetical. And now on line 38, when I'm ranging through the slice, I'm now ranging in the order, right, the alphabetical order of the keys, and then I can just do a key lookup. From the key lookup at that point, everything will be in alphabetical order. So the new sort package is really powerful. It's giving us new ways to be able to do sorts, and when it comes to maps, not have the output be so random. So maps are really big. They're a key data structure. You're going to be using them in your Go programs. Anytime you need that key value pair or you've got to index into something, it's going to be a really great data structure. Remember, we really want to use the slice first. That slice is giving us the mechanical sympathies of predictable access patterns. Your map is going to do its best to keep the data contiguous as well. So there is some help around mechanical sympathy as you traverse and work with your map. But think about that map really as one of those data structures when you want to pinpoint and get to data quickly based on a key. Welcome to lesson 4, decoupling. You are not allowed to start here. I really need you to have looked at those first 3 lessons before we get here, because everything happens in the concrete, and that's what decoupling is about. Decoupling the concrete. So to appreciate decoupling mechanics and semantics, we've got to know and learn our concrete. So in this section, we're going to learn how we can create thin layers of decoupling that are precise. We're also going to learn the cost and the impact that decoupling has on your Go programs, because what I want is to minimize pollution and be able to maximize the advantages that decoupling gives us in our software, both in terms of design and architecture, and include the cost of what decoupling brings. We want to minimize these things, and we're going to learn those things in this section. We're about to shift gears now. We're going to start talking about methods. What we're really going to start talking about is decoupling. Up until now, throughout the video, we've been really talking about the concrete data. And I've been trying to stress to you that everything we do is really built in and around the concrete data. The problems you solve are based on the concrete data. If you do not understand the data, you do not understand the problem. If you don't understand the problem, you can't write code, right? And if the problem is changing, that means the data is changing, the problem is changing, your code's going to have to change. Our work, our daily lives are built in and around data. Remember, we're all data scientists. And what we also been trying to show is that your performance comes from the data. Your performance comes from everything we're doing with data. And again, latency on network disk I/O, latencies on memory, right? Latencies on how we access data on the machine. All of it's data, 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 data. But here's the problem. When the data is changing and the problem is changing, we're changing our code. What we want to try to do is minimize the cascading changes that are going to rip through the entire code base. And this is where the decoupling comes in. And so we've been focusing down here on the concrete data. What we now have to start dealing with is the decoupling. And how do you decouple? Decoupling is going to be a big part of what we do. And decoupling is all done through behavior. And we're going to start wanting to focus on behavior now. Behavior is where we do design, architecture, and decoupling. And our real work, the real work we're doing is all down here in the concrete and the data. And one of the things we're going to want to learn is we want to start from the concrete and the data and move up this way. I really, really, really don't want you to work in this direction. Too many developers are doing this. They're starting with the behavior. They're starting with the decoupling. They're thinking about these. And you're guessing. If you start up here, you are guessing. I want to take the guesswork out. Solve the problem first in the concrete, then work towards decoupling. I'm going to show you this more anyway as we start getting into the design sections of this class. But right now, I still have to teach you mechanics. I've got to teach you the mechanics of what's happening above this line so we can get into design and architecture. All right, so what we're going to do is take a look at some code here. And the code we're going to look at is giving us the ability to allow data to have behavior. I want you to think about this for a second. To allow data to have behavior. Now, Go has functions. We've been looking at functions since we started. But Go also has the concept of a method. And a method is a function, okay, a function that has what we call a receiver. So let's take a look at what a method looks like in Go. Here's our user-defined type. It's user. It's got a name and an email. And if I scroll up just a little bit above the type, you see two methods. I always want those methods to come after the type. Now, this is a method because what we have is a special parameter being defined. It's a parameter. Look at it as a parameter. We call this parameter a receiver. So between the keyword func and the function name, we have a parameter. We call it the receiver. And now this is considered a method. And it's these methods that allow data to have behavior. Now, one of the things we have to learn as we continue to move forward, especially after the mechanics, is when should a piece of data have behavior? I want this to be the exception, not the rule. And this is going to be hard for you if you're coming from an object-oriented programming language, because OOP wants you to always think about data as having the state, the data, and always having behavior. Object-oriented programming wants you to try to say that everything in your program should resemble some sort of object like in the real world that has state and behavior. And I don't think it's really the best way to go in Go, right? Like, this is not what we want to do. In fact, I'm going to show you how Go is really separating state from behavior most of the time. And if we do this, you're going to be able to write less code and things are going to be simple. Functions should be your first choice until they're not reasonable or practical to do so. This is where we're going to get into methods. So I still got to teach you when you should take the exception and use a method. Really, the question is, when should a piece of data have behavior? But let's start with some of the mechanics here. Now, Go is interesting, right? We've been talking about our value and our pointer semantics. And normally, value and pointer semantics don't hit Go developers in the face until we get to methods, because now as we get into methods, you have to make a choice. Should I be using a value receiver? If you notice this, we have two receiver types that we can choose. Should I be using a value receiver, or should I be using a pointer receiver? This is very interesting. And a lot of Go developers get stuck and they don't know what to do. And too many Go developers, especially early on, start doing this. Okay, I know. If the method I am writing has to mutate the data, I'll use a pointer receiver. I'll share the data in. But if the method doesn't have to mutate, I'll use a value receiver. I'll let it just have a copy. This is very, very, very bad. We cannot do this. I'm not going to be able to stress enough that we must be consistent with our semantics. Data drives the semantic. So once the semantic is chosen, either everything is value or everything is pointer. And the method and the code you write has to respect the semantic for the data. Now, if you're used to programming languages like C++ and C# and Java, you actually deal with receivers. You've heard of the this pointer before. You've heard of the self pointer. Yeah, these are receivers. They're pointer receivers, and they're named for you. One of the things that Go does, which is brilliant, is they give you the choice of value and pointer semantics, right? Value receivers, pointer receivers. But Go also allows you to name the receiver. And we never want to use this in self when naming the receiver. You want that receiver name to be short and sweet. It should never even be more than 3 letters long, right? This is at the highest level of context in your Go program. So you can see I'm using U for user, U for the star user. Anytime we're using a user here, regardless of the semantic. Okay, great. So our value semantic methods, right, like notify, means that the method is operating on its own copy when we make the call. Our pointer semantic methods there, right there, change email, means that we are having shared access when we make the call. There it is. We've got these two choices. Now, while we continue to learn mechanics, you're going to see code that is got a mix of value and pointer semantics. Once we move to design, you will not see this anymore. No more. No, 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 no. But I'm teaching mechanics, so I need both sides of this so I can show you the behavior. Remember, mechanics, the semantics teach us the behavior. Now we can understand how this code's going to perform. All right, great. So if I move into main, I want to show you a few things. On line 32, I'm constructing a value of type Bill. A value of type Bill. There it is right there, named Bill. So let me clear this up a little bit so we can take a look at and visualize what's going to be happening in this code right here. I'm going to be constructing a value of type Bill on line 32. We know Bill is a value of type user. Now notice the call on line 33 to change email. Change email was using our pointer semantics. Change email said, hey, you got to share a value with me. Now you might think, well, why would that compile? Because Bill is not a pointer to a user, it is a value to a user. This is interesting. When it comes to calling a method, Go only cares that the data, remember data, value, pointer, that the data is of type user. It doesn't care that it's a value or pointer of that data. All it cares is that we are working with user values in some form, which is brilliant because now when we make that call to change email, what's going to happen is Go is going to be able to adjust to make the call. It's going to take the address of Bill, satisfy the receiver type, and share Bill with change email because change email is saying I want to use pointer semantics. When we call line 34, notify, which is using our value semantics, no big deal. Bill is already a value, and notify will operate on its own copy, right? Value semantics means we're operating on our own copy. Pointer semantics, shared access. Now, on line 38, I'm doing something I told you I don't want to do. Anytime I am constructing a value to a variable, I do not want to use this syntax. I don't want to start my life out as a pointer. Don't use those pointer semantics on construction, all right, if we're going to assign to a variable. That being said, I wanted to show you something with the pointer. Notice again, change email is already using pointer semantics, no big deal. Joan is a pointer, yada, yada, yada. But on notify, notify says I want my own copy of the value. Go again is going to come in and say, no problem, I will take the value that the pointer points to for you, and I will satisfy the call. Now, what you're seeing me do on the board might be interesting because Go is adjusting to make the call. But now what we're doing is switching semantics in the code, and I've tried to tell you over and over again, you start switching semantics, life is going to be very, very bad. And in fact, this call on line 40 is the worst of them all. You're really not allowed to take a copy of a value that a pointer points to. Not all data can be copied, and if it's shared with you, you should pretty much assume that it's not copied. So if I ever saw a code like on line 40, that would really scare me. Right? We want to really maintain our value semantics. We'll continue to talk about that. But I want to show you here how Go is able to adjust to make the call to match the receiver type with the data that's there. Okay, so what I want to do next now is really try to give you some guidelines around when we should be using value semantics and when we should be using pointer semantics, so we can come back into this code in a bit and get a better understanding of what we're doing in this code block and why. So now I want to give you some general guidelines on when to be using value semantics and when to be using pointer semantics. There are exceptions to everything. That's important. But if you don't know when to take the exception, don't. Engineering is all about choices. It's about cost. It's about knowing when to take those exceptions. So these general guidelines are very, very good, and they're going to work for you most of the time, and they're going to keep you out of a lot of trouble. Remember, semantic consistency is everything. So let's go and start taking a look at some code. And we're going to pull some code from the standard library. But before we start with this code, let's look at what we're dealing with here. There are really three classes of types that we're going to be working with in a Go program. You're going to have the built-in types, your numerics, your string, and your bool. You're going to have the reference types, slices, maps, channels, interface values, and functions, right? These are the reference types. And then you're going to have the user-defined types. These are really going to be your struct types. There are really three classes of types that we deal with, or three classes of data that we deal with that we've got to make these decisions on. So I'm going to make this as simple as I can for you. if you are working with the built-in types, strings, numerics, and bool, you are to be using value semantics. In other words, I don't want to see any code that takes a pointer to an int, any numeric, a string, or bool. I don't want to see that. Everybody can get their own copy of the built-in types. In fact, strings are designed, they're immutable, they're designed to be copied, right? We saw that before. So when we're dealing with these built-in types, including fields in a struct, I don't want to see pointers. Everything should be value-based. Now, there are some exceptions. I'll give you one exception. If you're dealing with a SQL database and you have a struct that's going to be used to be unmarshalling or marshalling data, the concept of null doesn't exist unless there's a pointer. So if it's not obvious to me that that struct's being used in some sort of relational database scheme and I see a pointer, we've got to have a conversation. So when I say value semantics, I mean not only values being passed in and out of a function, I also mean the fields when we're defining a struct. Okay, so let's see, right? Built-in types, value semantics. Everybody gets a copy. Reference types, we're going to follow the same rule. Value semantics for reference types. I don't want to see you take the address of a reference type. There's one exception to this, however. A slice and a map. You may take the address of a slice or a map only if you're sharing it down the call stack and to a function that's either named decode or unmarshal. That's it. I see that. We're not going to have a conversation. That's reasonable and practical. Decoding and unmarshalling require pointer semantics, and those data structures, slices, and maps are collections of data. Other than that, everybody should get a copy of the slice value, the map. Since maps and channels anyway are pointers, there's no reason to take the address of the address. And our slice, and you'll see our interface values or data structures, still, it doesn't matter. They're designed to be copied to stay on stacks. That means fields should also respect the value semantic form. In other words, I don't want to see pointers to slices, pointers to interfaces. We're not going to do that value semantics all the way for those reference types, except for the exception I gave you. Great. So that means 2/3 of the types are using value semantics, right? This is fantastic. I've told you value semantics are a really important part of your ability to keep the heap clean, which is going to give us a tremendous amount of performance. But not all data can leverage the value semantics. And when it comes to our struct types, this is where things get interesting. You've got to choose, if you're defining your own struct type, what semantic is going to be in play. You're going to hear me say that a lot now. What's in play? What's in play? And if you're not sure what to use, then we're going to use those pointer semantics, okay? And then if you're absolutely sure that we can use value semantics, guess what? We want to use those value semantics. They're really our first choice. Pointer semantics are really the exception when we need it. But I want to take a look at some standard library code to kind of bring this stuff home. And I want you to look at these two types that I've pulled from the net package, line 20 and line 21. Now again, what we would say is we're declaring a new type named IP, which is based on a slice of bytes. Line 21, new type named IP mask, which is based on a slice of bytes. And what we really have here now is two brand new types that are truly based on a slice. That means that they are reference types. IP is a reference type. IP mask is a reference type. And what did I tell you? Reference types follow value semantics. Now, based on that, we shouldn't be very surprised about line 26. Look at how this method is being declared. Notice that it's using value semantics. But notice that mask is a mutation API. You might think, well, mask is going to have to mutate. I should be using pointer semantics. No, you would be wrong. Remember, the code, the methods, the functions, the code has to respect the semantic. It's type, semantic, and code. So notice that mask is a value semantic mutation API. It gets its own copy of IP. It mutates that copy and then returns a new copy out. Look at what it's doing. And this is a very safe mutation, isn't it? Because the mutation happens in isolation, in our sandbox. It can't create side effects. This is a beautiful thing. But the choice of this API is driven off the fact that IP is a reference type based on its declaration of being based on a slice of bytes. Notice we're also passing a value of IP mask. Why? It's a reference type. And this goes beyond It goes beyond just the method receivers. Here's a function, a value of type IP, returns a value of type string. Why? Strings are built in type value semantics. IP is a reference type value semantic. You will see this throughout the entire standard library. There is nothing random about code in the standard library. It follows these semantic rules to a T, and there are very, very few exceptions there. And you can go and search for this stuff yourself. This is the key to having a code base that can be maintained by more than one person over time and can grow and maintain a consistency, which is going to, again, help reduce bugs and give everybody the ability to predict reasonably well how this code is going to behave on the machine it's running on. Now, let's talk about those struct types again. When there's a struct type, you have to decide what semantic you're going to use. Here's the struct type for time. I pulled this out of the time package. So let me ask you a question. If I asked you to write the time API, and I've given you this struct, what semantic would you choose? Would you choose value semantics or pointer semantics? Remember, you have to choose a semantic before you write a line of code. Let me give you a couple of questions you can ask yourself, which in many cases can help. It doesn't help all the time, but sometimes this helps. So let's start with time. If I gave you a value of type time, here it is. Here's my value. Remember, data is concrete. Here's my concrete time value. Now, if I add 5 seconds to this value, is it the same value, just slightly mutated, or is it a new value? Is 2 different points in time discrete data, different data, or the same data mutated? I would argue that if I add 5 seconds to this time value, I have a brand new piece of data. And when we have that scenario, it's usually a good indication that value semantics could be at play here. So we can make copies of this data, and mutations make new copies of data. We do this with strings, right? You mutate a string, you get a new string. So that's interesting. Now, what if I was dealing with a user type, Should we be making copies of users? And this isn't a technical question. I'm not asking you if technically it's safe. I'm asking you, should we, from a correctness standpoint, right? It's not optimizing for performance, it's optimizing for correctness. Now, I could make an argument here. If I met you and I just started calling you Jack for the rest of the day, like I decide I don't know your name, but I don't care. I'm going to change your name. You are now Jack for the rest of the day. Does that make you somebody different? If I take a user value and change their name, is it the same user, just slightly modified, or is it a completely new user? It's not a new person, right? It isn't. It's just somebody now whose name has changed. That's a good indication that we probably should be using pointer semantics. And I also want to apply the idea that since we can't make copies of people in the real world, why would we do something like that in our software? Our brains would not reasonably predict that sort of behavior because we don't do that in the real world. We need to bring all of this stuff into a code base. When we're coding, we don't want to confuse people. So probably users should be using pointer semantics because mutation doesn't create a new piece of data. It just modifies the existing data. This is a great question to ask. It doesn't always help you answer the question, but it's a good starting point. And when you're not sure, we should always be using pointer semantics because it's always safer to share than make copies because not all data can be copied. So let's see what the language team decided to use for time. Now, what I've done is I've pulled the factory function out of the standard library. Your factory functions should always come before the type, and they are the most important function in the API because the factory function tells you the semantic that is at play, the semantic that has been chosen by the developer. Where is it coming from? The return. Look, the now function is returning a value of type time. You are getting your own copy of the time value. What is the factory function saying to you? It's saying that value semantics are at play. I am creating a time value. I'm giving you your own copy. You can give other people copy, store it as a value, leverage the value semantics. Keep this data on the stack to the extent that we can. Make your fields also of the time value. Brilliant. Factory functions are everything. This is where we start. This is where we choose our semantic. If you're working with a struct type that you're not familiar with, maybe part of the standards library or somebody else's library, look for that factory function. And I pray it's right after the type. Shouldn't be hard to find. And leverage this information that I've highlighted to show you and tell you how to work with the data correctly. Now, since value semantics are at play, look at add. Add is a mutation API, but it's not using pointer semantics. It's using value semantics, right? A value semantic mutation. This is not an accident. This is not random. The code, the functions, the method has to respect the semantic, not the other way around. So add gets its own time value, mutates its own time value in isolation within its sandbox, right? Levels of immutability, and then returns a new one out. This is going to allow us not to have any side effects while all this stuff is going. This is beautiful stuff. Time could be using value semantics. The API is using value semantics. Okay, here's another function called divide. Takes a value of type time, value of type duration, value of type in, value of type duration, duration 2, leveraging value semantics. And if you saw the declaration of duration, it's really a type that's based on an int 64. Int 64 is a built-in type. Wow, look what's happening. Look, the reality now is that you could look at almost any type in your language, identify what it is, or its base, and start to understand already what semantic you should be using. And nothing should be random. Code that has semantic consistency is going to always be better over the inconsistencies. Okay, here's another factory. Oh, that's right, I forgot about this. Look, I told you there are exceptions to everything. And here's one of those exceptions. When you are implementing or using functions that have unmarshal or decode in it, they require naturally to have pointer semantics. You need to share because they're going to be mutating. So here are 4 APIs in the time package that are switching semantics from value to pointer. But guess what? Unmarshal, decode, unmarshal, unmarshal. They're implementing contracts or interfaces for this behavior. Absolutely fine. That's reasonable and practical. But if I saw the pointer semantics for anything else, it would raise a really big flag with me. Okay, look, here is a factory function for the file, for OS. Notice that this factory function returns not a value of type file, but a pointer of type file. You see that? What does this mean? It means that pointer semantics are at play. It also means that you do not have a right. Remember this. This is incredibly important. You do not have a right to make a copy of a value that a pointer points to when it's been shared with you like that. Assume that it is dangerous to make copies if something has been shared. Put that in your head. That is a major violation of semantic law. We do not make copies that pointers point to. Okay, assume that that is very, very bad. Now look at the change directory method. It doesn't mutate the value used to make the call, but it's still using pointer semantics because that type requires pointer semantics. Again, with this function here, pointer semantics because we have to use. The API, the code, has to respect the semantic, okay? And not the other way around. It doesn't get to choose the semantic. We define the data, we define the type, we get the semantic, and we write code. This is critical. So to sum up, built-in types, value semantics. Reference types, value semantics, except for decoding and unmarshaling. And then our struct types, we have to make a choice. If you're not sure, you use the pointer semantics first. I want to remember that you could choose a semantic in the beginning, realize that you're wrong, and then just refactor that the other way. Right? We are working on mostly closed-based source code systems, right? Private source code systems. Unless you're doing open source, we have the right to break APIs. We're going to talk more about this during design. I want to break APIs when we do things that are wrong. If we're dealing with open source that's been versioned, then we can't break APIs, but we can always add new ones and deprecate old ones to make improvements. We've got to constantly be reviewing the code we're writing, adjusting the code, refactoring that code, and making it better. So I don't want to get hung up where we're like stuck because I don't know what semantic to use. Choose a semantic, be consistent, and if it's the wrong one, no problem. We'll refactor later. All right, so now that we've learned the guidelines around when to use value and pointer semantics, let's go back to that other code I showed where we're looking at a slice of user values and a iteration over that. Now again, I always want to create a slice of values as my core data, and that is the point of truth, those two values right there inside the slice literal. But we talked before, for a value of type user, should we be using value semantics or pointer semantics? I mean, is it reasonable to make copies of people? And the answer really for me is no. I mean, we really should be using pointer semantics for that user value. I want to show you how mixing semantics can cause a huge amount of pain. Look on line 50. Notice that I'm using value semantics for my user collection. Already that's a smell. We shouldn't be making copies of users, right? Because think about it. We're making a copy of the slice here, which is fine. But now we're operating on a copy of the data. On the first iteration, we're not working with this data. We're working with a copy of this data. That's what we want when we're dealing with value semantics. So that's not what's wrong. What's wrong is we shouldn't be working with a copy at all. We should be working with Ed directly or Eric directly. But we're not. And here's the mix. I'm now using a pointer semantic API against a copy of the data. And if I run this, guess what? Ed's email address or Eric's email address isn't going to change. The copy's going to change. And this code is very hard to read and reason about. This is why I cannot stress enough. We must have semantic consistency throughout the code base so we don't get into this kinds of trouble. Now, one of the things I want to make sure you understand is that methods are really made up. They really don't exist. All we have is state and all we have is functions, right? Methods give us a syntactic sugar that a piece of data has behavior. That's what it's there for, to give us syntactic sugar, this belief system that data has behavior. And there are times where it's very important for data to have behavior. Again, we've got to learn when should data have behavior and when it shouldn't. And I want data having behavior to be the exception, not the rule. This is one of the things you've got to kind of fight because you've been trained. Always allow data to have behavior. No, 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 no. Functions for me are always going to be better choice when it's reasonable and practical to use them. So let's talk about a couple of things here in this code as we continue to go through it. I want you to look at this type data. There it is, data. And data has two acts of behavior, right? Display name, which is using our value semantics, and set age, which is using our pointer semantics. The other thing I want to mention something really quick. Setters and getters are not an API. If I see in a code review any function like this, or in this case method like this called set, we've got to have a conversation. Setters and getters just bloat a code base, require more testing, and really add no value. An API really should provide something. We're going to talk about that more during design. But setting and getting is not providing anything, and I really want to avoid these types of methods, okay? But here we are. We got set age using our pointer semantics and display name using our value semantics. One of the things I want you to see very quickly, that is if I define a new type, let's just say I even call it Bill. Does this new type Bill have behavior like data does? Remember, we're saying this new type, this new name type Bill is based on data, yet I want you to understand that behavior, there is no behavior associated with Bill data. All of the behavior is only still associated with data. Why is this? One, because these methods are not declared inside the type like you would see in a class-based system. They're declared outside the type. This is go again, separating state from behavior. We're not really wanting to combine it. We're keeping it separate. Your syntax is also keeping it separated. So understand that even though Bill is based on data, the basing is based on its memory model, not on this idea of behavior. Okay, so I've got this data type right there. I've got display name. I've got set age. There we are. And what I've shown you here is how we call methods. There's nothing new here. I'm going to create a value of type data. There it is on line 29. So nothing new here. Here's our data value, right? There it is. I've put Bill inside of it. Let's do that. There's Bill. And then on line 36, I call display name using D. I call set age using D. Again, Go will adjust to make the call. But what I really want to share with you, because you'll see this in stack traces anyway, but the reality is that, again, methods are made up. It's syntactic sugar. This is giving us a belief system that D has this behavior display name, D has this behavior set age. But when you call D dot display name or D dot set age, really what you're doing is calling a function. that receiver really is defined as a parameter, because it really is a parameter. It's actually the first parameter to the function displayName. So when you call d.displayName, the compiler is actually going to make a call to data.displayName, that's the full function name, passing the receiver d as the first parameter. Notice here when we call setAge, the name of the function leveraging the pointer semantics as part of its declaration, star data parentheses dot setAge. That's the real name of the function. And here what you're seeing is Go adjusting to make the call. This is why Go can adjust to make the call, because it's really just data being passed in. Now, you are never, 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 ever, never, ever allowed to call a method like this. Don't do this, okay? Please, if you do it and you say that Bill showed you this, I'll throw you under the bus. I'll deny this is even in the video. You can't do this, okay? When we're calling methods, you gotta call methods with that syntactic sugar. But if you looked at a call stack on some sort of panic and you're seeing method calls, they're gonna look like this. So my point here is that methods are syntactic sugar. They give us this belief system that a piece of data has behavior. It does give data behavior, but we really have underneath technically are just functions. The receiver truly is a parameter, and it's really the first parameter. Now, I want to drive home a little harder now the idea of value and pointer semantics with this, with the idea that if you know your semantic, if you know what semantics in play, you know behavior. This is everything, right? This is where I've been trying to get you since we started this video. So let's take a look at this code here. Now, on line 52, what are we doing? I'm getting the method displayName, already bound to D. There it is, already bound to D. But I'm not making the method call. Look, there's no parentheses. I'm assigning it to a variable named f1. Functions in Go are values. They are literally typed values. And that means that we can pass a function by its name anywhere we want in our program, right? As long as, again, type information is the same, the function's signature. But here I'm creating a variable. I'm creating a level of indirection, if you think about it, to be able to access and call displayName. I'm creating a level of indirection. I'm going to be able to make the method call like you see on line 55 through the variable itself. But in order for that 55, line 55, that function call through the variable to work, we need to set up some things here. So f1 is a reference type, and it's just a pointer. But if it's just a pointer, it's got to point to something. And it does. It points to a data structure that is a 2-word data structure. Now, the first word here is going to point to the code for, in our case right now, displayName. Remember, displayName really is a function, right? So we now have a level of indirection here. I want to specify this. This is important. I have a level of indirection, 2 pointers to get to the code. OK. But remember, I can't call this code. I can't call displayName without D. The whole point here is I need D, right? I need D. But what D am I using? This is where the semantics are critical. Let's go back and look at displayName for a second. DisplayName is using value semantics. Value semantics means that every piece of code is operating on its own copy of the data. Value semantics are at play. Copies of the data. You know what that means? It means that this f1 variable is not allowed to reference D. It has to be given its own copy of D. This variable always is operating on its own copy because displayName is making sure that we're using value semantics. Guess what? Also, we have indirection here. And anytime in Go we have indirection, we're going to have some interesting things around escape analysis. But right now, we've already made a copy. We made a copy. You know what that means? Allocation. It has to allocate. We don't know about this at compile time. This is happening at runtime. What you're seeing here at the function is really our first introduction to decoupling in Go. F1 is decoupling not only the code we want to execute, but the data we need to execute against it. And since we're making a copy of D, there's an allocation. OK, great. So now when we call F1 on line 55, we have an indirect line to the code, and we know what data. So therefore, on line 58, if I make a change to the data here, if I go, OK, you're no longer Bill anymore, you're Joan, are we going to see that change? Absolutely not. We're not operating on this D. We're operating on our own copy. Why? Value semantics were at play. Why was value semantics at play? Because display name uses value semantics on the receiver choice. OK, great. Let's do this again. Look at this code here. Now we're going to leverage setAge into a variable named f2. OK, no problem. Here's f2 right here. We know it's a reference type. It's a pointer. It also is going to have its own internal data structure. We know that this is going to point to the code for setAge. We've got that. We've got our double indirection, right, which is giving us our levels of decoupling. But what semantic is at play for setAge? Well, we know that setAge is using a pointer receiver, pointer semantics, sharing the data, not making a copy. What does that mean? It means that now this pointer doesn't point to its own copy. This pointer points to the original. So when we use f2 to make the method call on line 73, we're operating against the original data that's been shared, which means on line 76, if we change Joan to Sammy, guess what? We see the change. Pointer semantics are at play. Now, this is something that's very interesting. We have double indirection again to get to the data. And the escape analysis algorithm has what we would call a flaw in that once we have indirection like this, double indirection, the escape analysis algorithms can't track whether or not this value can stay on a stack or not. In other words, even though there's no reason for D to end up on the heap, it has to now allocate. So there's a cost to decoupling in Go, and it's really important. We're going to continue to say this. When you decouple a piece of concrete data in Go, you're going to have the cost of indirection and allocation. There's no way around it right now. No way around it. And so we have to make sure that if we're decoupling, that the cost of indirection and allocation is worth it. We do not want to blindly decouple code in Go. We want to do it because it's the right thing to do. It's the right engineering choice. It's reasonable and practical. Because this cost, we know, is great. Remember, this is number 2 on our lack of performance list in our programs. Allocation is number 2. So we don't want to take these allocations lightly. But if the decoupling is adding value, then I'll take this cost all day long, because if I can make sure that I can minimize cascading changes throughout a code base, if I can make sure that I can work with different pieces of concrete data without blowing up a code base, well, I'll take the cost of allocation all day long. Then it's worth it. All right. So our methods are giving us the ability to give a piece of data behavior. We still have to learn when is it reasonable, practical for data to have behavior. I want this to be the exception and not the rule. So we just finished the topic on methods, which teaches us how to, or the mechanics behind how you add behavior to data. And I told you that I want this to be the exception, not the rule. But I want to start showing you now the mechanics, and we'll look at some of the semantics, of interfaces. Okay? And interfaces give us the ability to have polymorphism. And there's a saying, or a quote, from the inventor of BASIC, Tom Kurtz. And he describes what polymorphism is perfectly. Polymorphism means that you write a certain program and it behaves differently depending upon the data that it operates on. I want to change that up a little bit and just say polymorphism means that a piece of code changes its behavior depending on the concrete data that it is operating on. This is critical. I keep talking to you about concrete data drives everything. Concrete data and semantics drive everything. And here it is. We're talking about decoupling, which is focused on behavior, but guess what's driving it? The data. And so when should a piece of data have behavior? Well, one good reason, one good practical reason is when we need to implement polymorphism, and that polymorphism is going to give us that levels of decoupling. So that's when a piece of data should have behavior, when we need that decoupling and we want to be able to process all different types of concrete data with a single piece of code. That's good. Now, there may be other times where you want to have a have data, have behavior. If it's an API, that has to be what I would say stateful, right? It's got to maintain sort of state around the API, but we got to be very careful about API design when we do that. We'll talk about those things as we go forward. Okay, so what I want to do is give you an example of polymorphism in Go and continue to drive the idea around this idea that concrete data is driving the polymorphism because the concrete data has behavior. Now, in this program, we'll start off right out of the box on line 10. On line 10, what we have is the reader interface. Notice that we're using the keyword type. This type reader is not based on a struct, it's based on the interface, right? And it's got one active behavior read, which takes a slice of bytes into error. But let's go back and look at reader for a second, because this interface type always boggles my mind. It's a type, right? So that means that I can do this. I can say var r reader. I can do that. I can declare a variable of this reader type. But what blows my mind is the fact that an interface type is not real. And we've got to make this very, very clear throughout. Interface types are not real. R is not real. There's nothing concrete about an interface type. Struct types, yes, concrete. That's real data. We can manipulate it. We can have fun with it. But interfaces are not real. They only define a method set of behavior. They define a contract of behavior. There's nothing real about an interface. Nothing at all. There's an implementation detail behind R, but from our programming model, R does not exist. It is not real. There is nothing concrete about it. And this is going to be an important concept for us to follow through with as we continue to look at this code. Okay, so I've defined this interface type. There's one active behavior read. And one of the things, even though we're looking at mechanics, and we'll talk more about this, it's very important that your interfaces define a behavior. Verbs, right? From my perspective, we're reading, we're writing, we're running, we're printing, right? The interfaces are about behavior. I don't want to see interfaces that describe things. I don't want to see an animal interface or a house or a user. These are not interfaces. Those are not behaviors. Those are things. That's your concrete data. The more you get away from that and the more your interfaces describe behavior, here we've got reader, has one active behavior read. This is behavior. We're going to be much better off with the decoupling because, again, we're focused on what? Behavior. Behavior, that's it. And we haven't been taught that kind of stuff in our object-oriented programming world because we want to decouple everything. I'm trying to go back to let's use our concrete data, because that's the problem, and let's decouple what we need to, and that's the behavior. And I want to keep this philosophy. I want to keep these mechanics and semantics throughout our entire program. Now, I've got the reader interface. It's got one active behavior read. It takes a slice of bytes, returns an int and an error. Okay, but let me ask you another question before we get going here. You know, I could have defined read to look like this. I could have said, you know what? Let's do this instead. Let's pass in the number of bytes I want to read and return that slice of bytes out. We might even argue that this is a simpler API. But why is this API horrific? Why is line 13 so bad of an API design choice in Go? That's because if we design our code or write our code like line 13, every time we make a call to read, we are going to be allocating on the heap. Remember, you have a responsibility in API design, not only to write precise APIs where you avoid misuse and fraud, but you also have a responsibility on the impact your API is having on the user machine. There's an impact here, and this one is allocation. You might say, Bill, where is the allocation coming from? Look, you can't implement methods like this inside the type. I'm just doing this so I can just write a little code to show you that if we were implementing it, where these allocations would come from. Look, your first allocation would come from the fact that you are going to have to make this slice of bytes here based on n. That's going to be an allocation because n, we don't know at compile time what the backing array should be. Immediate allocation. There's one potential allocation for this API design. But you might say, you know what, Bill? I'm not going to then allow you to pass an n. I'm going to make it even simpler. I'm just going to say read, and I'll hard code that. Yep, okay, compiler knows what the size of the backing array is now. We've gotten rid of that allocation, but guess what? Eventually, you've got to return the slice back up. That's now going to cause an allocation on the backing array because you can't have a pointer down the call stack. Do you see that this API design is not the right choice when we're going to have an API that's going to be in a tight loop? The other API, the one that I've chosen here, doesn't allocate because we're asking the caller to allocate the memory and share it down. So in Go, you do have a lot of control over your memory management because you understand escape analysis and you can drive data down, which means that the caller can define the slice, even hard-code its size, share it down the call stack, and there's no allocation. OK, great. Just want to keep bringing up where we can, where the allocations are going to be the escape analysis stuff. This was one of those places. Now, I've got my reader interface type. There it is. I can declare variables. Remember, R is not real. Interfaces are not real. Put this into your head. The only thing real is concrete. And on line 15, that's exactly what we've done. I got a concrete type named file. And this file represents a concrete piece of data, some sort of file that we might have on a file system. And I've got just a name in there. But more importantly, look on line 20. On line 20, we have declared a method. And this method has the same signature as the interface. Look at that. Read, slice of bytes, int error. Now, Go is about convention over configuration. So I want to listen to every word that I say right now. Listen to every single word, because not a single word here isn't important. Because of the method declaration on line 20, I can now say the following. The concrete type file now implements the reader interface using values semantics. Think about everything I just said. Every word's important. Because of line 20, I can now say the concrete type file now implements the reader interface using value semantics. You see, Go is about convention over configuration. We do not configure an interface to the concrete type like you might see in other languages. In other languages, you would probably have to do something like this. This is not Go. This is configuration. This is going to limit us at the end of the day. It actually does limit us and cause our software to have more lines of code. Go is about less lines of code. Go is about being more productive. And because of the static code analysis, it's going to give us a lot of benefits, as I'm going to show you as we move away from mechanics and into design. So we don't have to do this in Go. We just have to declare the method like we're doing on line 20. And the compiler, compile time, can identify interface compliance, satisfaction. Great. So now the concrete piece of data associated with the concrete type file, notice I'm using the word concrete, that structs concrete, now implements the reader interface, using the value semantics. Line 20 again. The concrete type file now implements the reader interface using value semantics. There we go. Forget about the implementation. The implementation is silly. We're just pretending to read a file. Now look, I have a second concrete type named pipe. It's supposed to represent some sort of networking pipe, right? But look on line 32. I also have a method named read with the same signature, right? That's part of the reader interface. And therefore, since there's only one method in the reader interface, we are satisfying the entire method set of the interface. Now, because of this, because of line 32, I can now say the following. The concrete type pipe now implements the reader interface using value semantics. There we are again. I have two distinct pieces of data, two concrete types, both with their unique implementation of the reader interface. Brilliant. This is setting us up for polymorphism. Remember what polymorphism says. A piece of code changes its behavior depending upon the data, the concrete data it is operating on. Oh, God. I love that saying. I love it. It gives me chills every time I say it because I really want to stress this data-oriented design and focusing on the concrete data and letting it drive everything we do, even through the decoupling. Okay, let's look at what I would call our polymorphic function. There it is on line 50. It's called retrieve. This is polymorphic and knows nothing about the concrete. In fact, you might even be confused for a second. Look at the parameter. The parameter in this function seems to say the following. It says, pass me a value of type reader. Can you do that, please? I would love a value of type reader. Guess what? We already know this is impossible. There are no such things as values of type reader. Values of type reader do not exist because reader is an interface type and interface types are valueless. Whoa, what did I just say? Think about this. Interface types are valueless. So it is impossible for this polymorphic function to be asking for a value of type reader because it doesn't exist. Well, if it doesn't exist, and that's what it's saying, what is it then really saying? Well, actually, this is what retrieve is saying. It is saying, please pass me any piece of concrete data, any value, any pointer that satisfies, that contains the behavior of reader, the full method set of reader. Think about this again. Remember, we could only pass concrete data through those program boundaries, through our app. That's what's real. That's what we manipulate. That's solving the problem. So what is this function saying again? Pass me any piece of concrete data, any value, any pointer that satisfies the reader interface, that implements this contract, that has the data, the full suite of behavior method sets that satisfies the reader. And don't we have two concrete pieces of data in this program already, file and pipe, that have the full method set of reader? We do. But this is my polymorphic function because it knows nothing about the concrete. It can operate against any piece of concrete data that implements the read method. And you can see here that we're going to be executing that behavior through the interface. Okay, you know what? Let's look at the mechanics on the board. Let's draw all this stuff out so you can see this polymorphism in action, both the semantic side of it and the mechanics. Okay, so look what we do right here, right there on line. I got to turn this around again. Line 41. Look at line 41. Okay, brilliant. What are we doing on line 41? We are creating a value of type file. There's F, there's our file value. I'm also creating a value of type pipe. There it is, P. I've got these two values. Remember, we're constructing to a variable. We're going to use our value semantic construction. We've done that great. But now look on line 45. On line 45, we're making a call to retrieve. Now, I'm always going to be asking you the same question. What semantic is at play when we make this function call? In other words, is the function receiving its own copy of the data, value semantics, or is it being shared the data, pointer semantics? We look at this and we realize that this polymorphic function is being given a copy, its own copy of the file. So we are passing a copy of F across this program boundary. The compiler during compilation knows that this piece of data implements the reader interface using value semantics. You can see that during static code analysis. Remember, retrieve is saying, pass me any concrete piece of data, any value, or any pointer that satisfies, implements the reader interface, has the full suite of behavior. We know that this does, right? We know that this piece of data has a read method. We know it's there. Brilliant. Now, on the other side, though, even though we're giving it this copy, what we have is R. And R is an interface value. Now, there's only an implementation detail because from our programming model, R is not real. It is valueless. There's nothing concrete about it. But what is R then from an implementation detail? R is really an interface value, which makes it a reference type. And when R is set to its 0 value, there it is, 2 pointers, 0, 0. Now, when we pass this concrete piece of data over the program boundary, the whole idea here is there's a relationship between interface values and our concrete data. And that is one of storage. We store concrete data inside of interface values. And when we store the data inside of interface value, that finally makes the interface value concrete. Everything's always got to get back to the concrete. So though interfaces are really valueless, through the mechanism of storing, when we pass this concrete data across the program boundary, now we have something that's more concrete. And it's this second word that we're using for storage. So look, we made a copy of F. We're now storing it inside of the interface. This is giving us our levels of decoupling. And because we made a copy of F, what does that mean? It means what? Allocation. There it is. Allocation. Every time I draw that little red, I'm showing, hey, oh, allocation. So we've got an allocation now. Brilliant. What about the first word? OK. We're going to get a little technical here. The The first word points to a very special internal table that we call the I table. Now, if you've ever heard of V tables before in an object-oriented programming language, then an I table is very much like the V table, but it's an interface, so we replace V with I. And V tables are just a matrix of function pointers that allow us to have base class pointers call into derived class objects behavior. And the I table is kind of doing the same thing. But the first word of the I table will always describe the type of value that we're storing inside the interface. In this case, we've got a value of type file. The rest of the I table will be that function pointer. So this is going to basically point to the concrete implementation of read for file, right? So what's going to happen now on line 53? Remember, interfaces are giving us a level of decoupling. So on line 53, when you call read against the interface, we do an I table lookup. Guess what we have here? Again, in direction. We do an I table lookup to find out where the implementation of the actual read is. And then we call that implementation against, in our case, our copy. And there we have indirection. Indirection and allocation. That is what decoupling costs us. But guess what? I've got a polymorphic function that can handle any kind of concrete data. And remember, retrieve is changing its behavior. The call on line 53 is changing its behavior depending on the concrete data it's operating on. Right now, retrieve is accessing a file system. How cool is that? But let's go look at the next thing. On line 46, now we call retrieve again. Again, what semantic is at play? Value semantics are at play. Retrieve is going to receive its own copy, not of F this time, but it's going to retrieve its own copy of P. And we know P also knows how to read. That means this time the I table doesn't say file here. It says, no, I've got a pipe value. Brilliant. Now this time, when I call read against R, I'm going to call read against our copy of P. Allocation, but the behavior has changed. Polymorphism means that a piece of code like retrieve changes its behavior depending upon the concrete data it is operating on. It's still all driven from real concrete data. This has now made the interface value concrete. But at the end of the day, interface values really are valueless. They're not real. Only the concrete data is real. Now, moving forward, I don't particularly care about I tables. It's a little too technical. I want you to know they're there. I want you to know that this is a pointer. But what I'm going to be doing moving forward is putting inside of this word the type of value that we have stored inside of the interface. Okay, so I would be saying here that we have a value of type pipe. That means we're using value semantics with the interface. Here's the copy. And now when we call read against R, we're calling read against our copy. And the I table's giving us all that. So there's no magic going on here. Now this is our basic polymorphism in Go. It's really showing you when a piece of data should have behavior. And this is one of those cases when we need to implement polymorphism. I cannot stress enough, though, there is a cost to decoupling here. And again, it's the indirection and the allocation. All right, let's look at another polymorphic example here. And things are going to get a little more complicated, but that's OK. We're going to build up to this. Now, I've got another interface here called notifier, one act of behavior, notify. Again, I want that relationship of behavior. Interfaces should describe behavior, not persons, places, and things. And here it is, the notifier, notify. We got this one act of behavior. There we are. Now, here's my concrete data. It's named user, name and email. And here we are on line 22. And remember what I can say. The concrete data user now implements the notifier interface using pointer semantics. We were using value semantics before. Now we're using pointer semantics. All I had to do was implement the notifier method. Based on the fact that that is the full method set now for notifier, I can say again, the concrete type user now implements the notifier interface using pointer semantics. Now, I go ahead and I look down here, and we have, again, our polymorphic function. What is this function saying again? It's saying, I will accept any piece of concrete data, any value, any pointer that implements the notifier interface. It can't be asking for notifier values because they don't exist. That's an interface type. And interface types are valueless. Pass me any concrete piece of data, any value, any pointer that implements, that has the full method set of behavior for notifier. And then we will call into that behavior from a decoupled state through the interface value. Brilliant. So let's go through this program now. So I go ahead on line 31 and I construct my user value. There it is, user right there, and we put Bill in it. There it is, there's my concrete data. Now, just like we did before on line 36, I call my polymorphic function using value semantics, just like we did before, which means we want to pass a copy of Bill across this program boundary. But something very odd happens. When I try to run this program, the compiler very quickly says, whoa, 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 whoa. Look, I'm sorry, but this piece of data you're trying to pass across this program boundary, it doesn't have the behavior that it needs. It doesn't have notify behavior. And we're like, what? What you talking about, compiler? I did everything you asked me to do. I went ahead and I defined a method named notify, and notify matches the notify method inside the interface. I have compliance. There it is. I've got a method right there named notify for the concrete type user, and implements the notify interface using pointer semantics. Compiler, it's all there. Why are you not letting me pass this value through? Why does this piece of data not implement the notifier interface? Well, the compiler is absolutely right. And what the compiler is trying to do here, I call it love. You see, the compiler loves you, and the compiler doesn't want you to have an integrity issue in your software. And if the compiler allowed you to use value semantics here, we would be in a tremendous amount of trouble. Now, I want to explain to you and show you where this integrity issue is. There's really two parts to it. But before I can, we've got to talk about method sets. There's a set of rules in the specification around method sets. And these method sets are there to protect us and our software. Now, I'm going to write the rules for method sets as it relates to the specification, and then I'm going to switch it up just a little bit to make it a little easier for you to read and understand then understand where the integrity issues are with line 36. But this is all love. I don't want you to look at it any other way. This is the compiler showing you love. Okay, here we go. This is what the compiler says. It says, if you're working with a value of type T, right? If we're working with our value semantics here, we're working with a value of type T. Then what it's saying here is only those methods using value receivers, right? Only those methods using value semantics belong to the method set for this value. That's it. And if you're working with pointers, right? We've got like pointer semantics here. Then when it's saying your pointer receiver methods, right, and your value receiver methods, what it's saying is all the methods that you declare for that concrete type, they exist for pointers. You get the full method declarations for your pointer data, but only your value methods for your value data. In other words, these pointer receiver methods are left out of the method set for values. And if we just quickly go back and look at what's happening here, notice that I implemented the notifier interface using pointer semantics, and now I'm trying to use value semantics. I'm mixing semantics, am I not? And the compiler's going, whoa, you're trying to create a copy of T, but guess what? T doesn't have any methods. The compiler was right, because the pointer receiver method didn't get included in the method set. The real question again now is why? Why can't we include pointer receiver methods for this value of T, but we can for pointers? And why do value receivers get to apply to both? Okay. So the two integrity pieces here, one I would call minor, one I would call major. Let's look at the minor integrity issue. Now, what if I said to you that not every value you work with has an address? Think about this for a second. What if I told you that you could not take the address of T? Well, think about it. If you can't take the address of t, you can't call a pointer receiver method. You cannot be using pointer semantics if something can't be shared. Remember, integrity is about 100%. If you can't have something 100% of the time, you cannot have it. You're setting yourself up for integrity issues. Look at this piece of code right here. I define a type named duration based on an integer. Duration is based on an int. And then I implement the notifier interface, right, using pointer semantics. I have a method using pointer semantics named notify. But look at what I do on line 18. On line 18, I go ahead and I take the literal value 42, which we know is a constant of kind int, convert it to a value of type duration, and try to call notify. And the compiler says, dude, I'm sorry, this value has no address. And the compiler's right, because still at the end of the day, this is a constant. It's a constant of type duration. And we know constants only exist at compile time. They never find themselves on a stack or on the heap. There is no address. Even though it does satisfy the interface, there is no address. So this would be very bad to store this duration inside of our interface because there's no address, and therefore the pointer receivers can't be applied. Look, we're getting at least compiler messages here. This is a minor one for me. This isn't the big one. This isn't the one that's like hugs and love here, okay? But I want you to understand that if you can't have something 100% of the time, you can't have it all. So we can't assume that we can always get the address of t. But if you already have an address to t, then we already know it's in memory, so we can always use the address, or we can always get a copy of the value that the pointer points to. We can always do this, but you can't assume the address. But what's the bigger play here? Why are these rules really in place? And remember, this stuff has been known for a decade. Well, let's look at this a little differently. When we talk about decoupling, I really want to focus on the behavior side, not necessarily on the data side, right? And when we do that, something very interesting happens. If we read this chart from right to left, read it in this direction, focus on the behavior, something really, really interesting happens. And what this chart is saying is the following. If you've chosen pointer semantics, right? If you've chosen your pointer semantics, and which remember something, we define the type, we choose the semantics, and then we implement. So if the pointer semantics were the choice, then what this chart is saying is you can only share. If you've chosen pointer semantics, then the only thing you're allowed to do is share because that is the only safe thing to do. If you choose value semantics, then we want you to make copies. But I told you one thing. I said to you that sometimes it is absolutely safe to share a value even if you're working in value semantics. I don't really want to change semantics if I don't have to, but even if you're using value semantics, there are times where it's safe to share. But what this chart is also saying is it is never safe. It's never safe to make a copy of a value that a pointer points to. It's never safe. So if you're in pointer semantic mode, you're only allowed to share. You're never allowed to make a copy of the value that the pointer points to. How amazing is this chart? When we look at it from the behavior point of view, it all begins to make sense. The compiler is saying, if you chose pointer semantics, you're only allowed to share. If you change your semantic back to value, that is a major, major violation of law. If you're using value semantics, please, let's make copies of things. Let's give the interface its own copy, right? But there are times where you might need to share something like decoupling, like unmarshalling. But we never, ever, never, ever want to go from pointer semantics to value semantics. Never, ever, ever. This is a major violation. And what the compiler has done here is said, when we're storing data inside of an interface, we're never going to allow ourselves to break this major law of pointer semantics to value semantics. No, 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 no. We're never allowed to make a copy of the pointer the point points to. You cannot assume that that is safe. So when we come back and look at this code now, what we realize is we implemented the interface using pointer semantics, which now means that we can only share data with the interface. We're no longer allowed to make copies of the data, which is what I was trying to do. So if I turn around and now say, okay, let's maintain the right law here. Since we're using pointer semantics to implement the interface, I can only share the data with the interface. Boom, there it works. How cool is this? So this chart, again, is here to protect us, to maintain the right level of integrity when we're dealing with decoupling. So if you are using pointer semantics, which was chosen at the time you defined the type, right? Those methods were declared based on the type, then you can only share data. If you're using value semantics, let's make copies, but you also have the ability to share when it is important. This is never allowed. Never allowed. Using pointer semantics, you may not make copies of the value that the pointer points to. So I want to show you one more time how the semantics really drive our ability to read and understand the impact code's going to have. And that when we are decoupling in Go, it's going to come with the cost of indirection and allocation. And this is not unique to Go, by the way. I mean, decoupling is just inherently an allocation type of operation. But let's take a look at this code here. See, we can really see this, and again, begin to understand that when we understand our mechanics, and then we understand our semantics, we understand how code's going to behave and the impact. We can make some better engineering choices. Here is the printer interface, when active behavior print. And here's our concrete type user, has a name, and it implements the printer interface using value semantics. And what do we now know? When we're implementing interfaces with value semantics, we can both use value semantics and pointer semantics, but we prefer to use the value semantics and keep our semantics clean. OK, here we go. Value semantics is at play with this concrete data user. Now, I go ahead and I create a user value. There it is. There's you. I put Bill in it. Beautiful. There's my concrete data. That's our work. And then on line 32, I do something really interesting. I create a slice, a collection of printer interface values. I now have a collection of data that is not bound to just one concrete type, but any concrete data, any value or any pointer that implements the printer interface, right? The behavior of print. And I'm using my slice literal here to do construction. And on line 35, I use my value semantics to store the first piece of concrete data. So this will say user, and this will have its own copy of you. Value semantics are at play, which now means what? It means that since we're using value semantics, what do we have here? Allocation. There it is. We have a copy. There's our allocation. And then on line 38, what have we done? We're now not using value semantics. We're using pointer semantics on line 38. That means the interface is going to look like this. A star user, it means that it's referencing the original you. Pointer semantics, value semantics. Again, because anytime we store value inside of the interface, we're going to have allocation. Guess what? Allocation right there. There's our cost. Indirection and allocation. Boom. There it is. But when I go ahead on line 42 and I change out our data, only index 1, not index 0, will see the change, because index 0 is using value semantics. Index 1 is using pointer semantics. We can see and understand the impact that we're having. Now on line 46, we're using the value semantic form of the for range. This is not an accident. This is not random. Think about it. We are going to range over a collection of interface values. Interfaces are reference types. Reference types use value semantics. Guess what form of the for range we use? Value semantics. Do you see how everything is driven off of the data and the data semantic? What is the collection? Interfaces. Interfaces, value semantics. Value semantics, there we go, right there. For underscore blank identifier E. Now E then is an interface value as well, local to the for loop. On the first iteration, what do we get? A copy of index 0. We're using those value semantics, which now means, this is E, which now means I have two interface values sharing. Pointers are for sharing. Efficiency. I'm hoping by now you see the efficiencies that we're getting through our pointers. But we made a copy, value semantics. I've got two interface values now sharing the same user value. And then we call print, right? We call print against this. Sorry, we call print against our copy, which is going to call print against there, right there. We call print against E, which calls print against our copy. Now, on the next iteration, what happens? We get a copy of the next interface value. So we're not going to be pointing here anymore. This is now going to say star user. We're going to come here. And now when we call print against the same E, polymorphism, the behavior changes depending upon the concrete data that we're operating on. We now call print against this right here, against the original, and we see the change. We see the change. Polymorphism, again, is all about decoupling through behavior, but everything's still being driven through the concrete, and the concrete data having the behavior. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it's operating on. And right here, we were operating on two different user values, one in value semantic mode, one in pointer semantic mode, and we see different behavior. This is really important. And if we maintain these semantics and these semantic consistencies throughout our code base, life is just going to be better for us and everybody on the team and everybody that we haven't even met yet that eventually has to come in and maintain this code. All right, so we just learned the method mechanics and semantics. We just finished interface mechanics and semantics. There's a couple more mechanics and semantics we have to learn around decoupling before we can get into design, and this one is embedding. So embedding is a very important, powerful feature in Go. We're going to use it around composition, which is a design pattern that we use heavily in Go. So let's take a look at a base piece of code that we're going to start with here. Now in this code, we have our user-defined type, our concrete type user, name and email, and then we have a method named notify using pointer semantics. Again, one was going to be specifying that what semantic is in play. Without semantics in play, we don't understand behavior and impact. So we've got a notify method using pointer semantics. Now, nothing special is going on here. I've got the admin type, right? It's another concrete type named admin, and admin has two fields, person and level. But the person field happens to be based on the other concrete type user, or struct type, right? Okay, great. But nothing special. This is not embedding just yet. Just two different unique fields, just like level is a string. Now, I go here on line 33, and we construct the admin value. But because the person field is also of a struct type, we do our struct literal construction inside, and we initialize the person field to be of this user. Okay, great. And then nothing special. I can access the notify behavior through the person field through our AD admin variable. Okay, this is just setting up. Nothing special going on here. We've done this our whole programming lives. Nothing special. But let's make a change to this piece of software. And what we're going to do is go back to our admin type. Here's user. User has name and email again, our pointer semantics on notify. And then on admin, what we've done is removed the person field and just embedded a user value inside of an admin value. This is what I want you to think for a second. We are embedding a user value inside of the admin value. But for me, a little bit better way of thinking about this is to create this inner type and outer type relationship. I want you to look at user as the inner type and admin as the outer type. And when you do, what we have is this concept of inner type promotion. Everything related to the inner type can be promoted up to the outer type. In other words, promotion allows access to those things from the inner type through the outer type. So look, let's do our construction like we did before. Construction is very tedious in Go. Types have to be very explicit. But you can see here that the user type looks and feels like a field during construction. It's really not a field. We're just trying to access the user value that we've embedded directly, but we do it through the type's name. And so now what we're doing is initializing the inner value directly. But here's where inner type promotion really comes in. We can still access the notify behavior through the inner type value directly, but because of inner type promotion, I can also access notify directly through the outer type value. Look, it's the same exact output for both calls. Inner type promotion is giving us a sense of type reuse, but we're going to use it for much more than that. There it is. But now let's add a little more complexity to this program. Let's go ahead and add an interface. And here we are with the notifier interface, one active behavior, notify. And again, our inner type user implements the notifier interface using pointer semantics. Brilliant. Now, we go ahead and still embed user inside of admin. We do our construction, but this is the cool part here. We add our polymorphic function called send notification. What does send notification say? Pass me any piece of concrete data, any value, or any pointer that implements the notifier interface. Remember, it can't ask for notifier values. They don't exist. Interfaces are valueless. That being said, pass me any concrete piece of data, any value, any pointer that implements the notifier interface. And because of inner type promotion, the outer value AD, the address to it, because we used pointer semantics on the implementation, satisfies the interface. Think about how amazing this is. Look, embedding does not create a subtyping relationship. Embedding does not create a subtyping relationship. You cannot pass an admin value around as a user. This isn't base-derived class stuff like you see in object-oriented programming languages. Admin is admin and user is user. But because of inner type promotion, because of the behavior being promoted up, this admin value now satisfies all the same interfaces, contracts, as the inner type did, because we can promote that method set up. This is really, really powerful. Remember that our work is done in the concrete data. That's where our performance comes from. That's where our problems are solved. And the decoupling helps us deal with change. Then layers of decoupling, this is what we're looking at, architecture and design. All of this is happening through the behavior. And now this outer type, concrete piece of data, admin, now has the right behaviors because of inner type promotion to satisfy the notifier interface. Now let's keep going here and let's add one more interesting piece to this code. I've got the notifier interface, one active behavior. Notify, I've got my user, concrete type, my inner type, implementing the notifier interface. Brilliant. But this time, admin, my outer type, also implements the notifier interface. Look at that right there. I now have two implementations of the notifier interface, of the method notify, one from the inner type, one from the outer type. Well, when the outer type implements the same things as the inner type, then there is no promotion. The outer type will override the inner type's implementation. If you look at this, now when we call our polymorphic function with the address to the outer type, it is the outer type's implementation that gets called. Same thing when we call notify against the outer type value. But in this particular case, we can always still access the inner type's behavior through the inner type value directly, like we just did there. It's all there. So when I said that inner type promotion can, I meant can because only at compile time does the compiler really check, and only at compile time do those things that are being accessed promote up. So one of the very first questions a lot of people ask in classes, Bill, what if I have two inner types that implement the same method? What's going to happen? Well, nothing's going to happen unless you try to make a method call that has ambiguity, right? You can have all of that as long as you don't make the call. So until you access something, it is not promoted, and then at that point the compiler will validate there's no ambiguity, and life is good. So embedding looks like it's part of this concept of type reuse in Go, but we're never going to really use it for type reuse. We want to use it really for composition, which we're going to be seeing very, very soon. Okay, the last mechanic we need to learn before we can get into design here is exporting. And exporting is kind of like the encapsulation piece of Go. But it's not like your object-oriented programming languages around private and public. It is a little bit different. And there are concepts around packaging that we have to talk about, but I really want to save the larger packaging conversations for design. So let's just focus on what we need as it relates to exporting here. Okay, so let's go back. Let's go and use the VS Code editor to show this because we've got to talk a little bit about packaging. I'm going to scratch the bare purpose. So the basic unit of compilation in Go is a package. And a package in Go represents a folder. I really want to go deep into this later. But encapsulation begins and ends really at the folder level, and every folder represents a static library. That is our smallest unit of compilation. So here I've got a folder under example 1 called counters. And this folder also should represent the namespace for everything that's inside this folder or this package. And I also want to see one file named after the package name. That's going to help. We'll talk more about that later. Now, based on this basic unit of compilation, the idea is that symbols are either exported or available outside of the code in this folder, or unexported and only available to the code in this folder or package. Now, up until now, I've been very careful to try to keep everything lowercase because Go is all about convention over configuration. This is one of the more brilliant conventions that Go has. Notice that the folder name is counters. Notice that the package directive name is counters. You really want to match the folder name with the package name because we import packages by their folder name. And if these two names don't match, you're going to really confuse somebody because this is kind of the namespace and that's the folder, and we expect these things to match. And all code inside this folder has to use the same package directive or the compiler is going to get upset. Okay, great. So even though the compiler doesn't care that they match, there's tooling that will break, and you're really not being a great Go citizen if you don't match the folder name with the package name. So that name has to be very short and sweet. We'll talk more about that later. But I want you to look at the type I've declared. It's called alert counter, starting with a capital A. And what Go says is you just look at the first letter of anything that's been named, or any identifier. And if it starts with a capital letter, guess what? It's exported. It's available outside of this folder or this package. If it's lowercase, it's unavailable or unexported. So since this has been exported, I can now go into the example Go code right here. And what we can do is you can see this very long import. This import is pointing from your Go path where this folder or package of code is that you want. It's already a relative path. Don't do this. Please don't do this. This is going to make big messes for you and everybody else. Already a relative path. Okay, so we brought in the package based on its folder name. Since we matched the namespace with the folder name, we know already how to work with it. And you can see here, I'm taking the literal value of kind int 10, converting it to a value of alert counter based on the counters package, and I've created a variable, life is good. Because alert counter starts with a capital A, I have access to it. It's been exported outside of counters, right? It's like my encapsulation there. But what if in our counters package we decided, no, we're going to use a lowercase a. Now, only code inside this folder or package has access to this identifier. This time when I try to use it, I'm in trouble. You can see the compiler is going to tell us, sorry, I can't access this unexported name. Right? It's been unexported. It's undefined. So we're getting levels of encapsulation here. But I want you to understand it's really not private and public. Private and public is about the data. This is about the identifier. So let me show you this piece of code. Now, I don't want to write code like this in Go. If I saw this in a code review, right, we'll be fixing it. But it's still really interesting. There it is. I've got an unexported type named alert counter, an exported function named new. Very common to have factory functions called new. But look at what new does. It takes an integer in, converts it to the unexported type, and returns a value of the unexported type out. This is very interesting because how could we return a value of the unexported type when we can't access the unexported type from outside this package? It's very true that you cannot leverage the unexported type directly, but the compiler can. And look at what's happening here. Even though we're calling new, the compiler is able to declare a variable of the unexported type. We're not getting any encapsulation here, so please, 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 please don't do this. But it's just showing you how exporting and unexporting is much different. It's not about the data. It's about the thing that is named and whether you directly, not the compiler, but you directly have access to it. Now, if you do something like this, it's really interesting because you should be using your Go linter, and your Go linter is going to tell you this, right? Go lint. Hey, don't do this because it's annoying to use, and it's absolutely right. So if I saw this in a code review, we'd be making alert counter exported. All right, a couple more things here, which is interesting. Let's look at this. I've changed the package now to be not counters, but users. Users.go, I'm matching the file name. Package also matches the folder name. But this time I want to show you type level encapsulation. I saw package level encapsulation. Now let's look at type level encapsulation. Here the type users exported with 2 exported fields and 1 unexported field. That means that only code inside this folder or package has access to password when working with values of type user. But outside of the package, what we get is name and ID. So there it is. This code doesn't build because I'm trying to, during construction, access the unexported type. Again, the compiler says, dude, this field is unknown. So you also get field level encapsulation just by changing the first letter to capital or lowercase. Now, one last interesting example is right here. Back to the users package. Look at what I've done here. I've got a type named user, which is unexported. Only code inside this folder or package can use this user type. But it's got 2 exported fields, name and ID. Then I've got an exported type named manager. I'm saying that this is public, right? With an exported field title. But I'm embedding the unexported user value. Again, there's no value in this. But here's the question. Once I'm outside of this package and I have a manager value in my hand, what fields do I have access to? Here's the cool thing. Because of inner type promotion, I'm going to have access to both title, name, and ID. But the problem is during the construction, I can't initialize the inner value because that name, it's been identified using the lowercase u. See, we're really not getting any encapsulation here because all of the fields got promoted up anyway. We'd be making user capital U if I saw this code. But it is very, very common in Go to have this situation where the type is unexported and the fields are exported. And that's because the marshalling and unmarshalling code in Go only will respect fields that are exported. So you will have types in your Go programs where the type name itself is unexported and the fields are exported. I just want to be very clear that this isn't based on the data. This is not a private and public mechanism. This is that thing that is named, the named thing, is it accessible to the software developer outside the package or not? And remember, the compiler can always create variables of any or unexported types because it has the power to do so. Welcome to Lesson 5, Composition. This is where we start focusing on design. At this point, we've learned our language mechanics. We've learned our language semantics outside of concurrency. But this is where you're going to spend the bulk of your time as a Go developer. At least I hope so, because composition is a huge and important part of writing software that won't be legacy code. So we're going to learn how to design and build software from the concrete up and decouple things and learn the mechanics around these things as well. So this is an incredibly important lesson for us to learn because this is the stuff you're going to do every day. And I promise you that when Go's time is over, and it will be maybe in a decade or so, and the next languages come out. It is this lesson, the aspects of composition that other languages are going to be copying from Go. That's how important this lesson is. So we're going to start talking about some design-related material now, and this is going to be around composition. There's a lot of things to talk about around composition, and composition is something that you're really going to be focused on quite a bit as a Go developer, even much more than all of the concurrency multi-threaded stuff. So what we want to start off with here is the concept of grouping, because grouping is going to be one of these things where I've really got to kind of break you down and build you back up. Things are going to be a little different here in Go. Now, every once in a while, a couple times a year, I'll have somebody who I don't know reach out to me, maybe on Slack, and they'll say, Bill, I'm a new Go developer, and everything was good, but I've kind of hit a roadblock, and I don't understand what's happening. Do you think you can help? And I'll be like, yeah, absolutely, sure, no problem. Show me the code. And 9 times out of 10, this is exactly what I see. And I see this animal type. And normally the conversation kind of goes like this. oh, Bill, man, I'm learning Go, and, I'm coming from some object-oriented programming language, and, I was really getting the hang of this. I really thought I could be a Go developer, Bill. Look what's happening here. I have this animal type, right? An animal, it's a base type, Bill, for anything that's an animal. It's got a name. It's got an is mammal, right? These are common fields, Bill, right? You understand that? And you know what? Even animals, I learned that I can add behavior. So, here's this animal, and it knows how to speak. There it is. And I know, Bill, like animals generically don't know how to speak, but, I was able to add this behavior. This was all making sense to me. And, Bill, if you're going to have an animal, then you have to have a dog. And look, I was using embedding, just like, to be able to say that a dog is everything an animal is. And I extended it, right, Bill? We can do that with inheritance and stuff, but I'm doing it with embedding. And life was good. And then I really made this dog be able to speak properly. Woof, there it is right there, Bill, right? Like you see it there. Dog. And, Bill, if you're going to have a dog, then you got to have a cat. And here's the cat right there. Cat also embeds the animal because the cat is everything an animal is, right? Anti-promotion, Bill. And then I made the cat speak. Meow. There it is right there. And I got this dog and I got this cat. And everything was good. Like, this is exactly how I write code. And everything was good. But then, Bill, I ran into a problem. You see, I wanted to group the dogs and cats together. And I tried to group them by what they are, which is an animal. And I could do this before, but Go is not letting me do this. This code is not compiling, Bill. Why is it that I cannot group dogs and cats by what they are, which is an animal? Okay, this is one of the very first things you've got to realize, that Go is very strong on their type system. And the fact that you've embedded animal into dog and cat means zero. It means nothing. There is no subtyping. There is no subclassing in Go. Animals are animals, dogs are dogs, and cats are cats. And so I can understand how this developer has kind of gotten stuck here. So how do we answer this question? What is the problem here, and how do we solve it? The first thing I want you to understand that Go is about convention over configuration. Remember that. Go says that configuration is limiting. And it really is. I mean, if I'm in a room, in a classroom situation with 15, 20 people, I will ask them, is anybody in this room a sibling? Or is anybody a brothers, sisters, siblings? And normally the answer is no. And I say, well, look, if we really wanted to group people in this classroom based on who we are, based on configuration, we wouldn't be able to do it. We'd all be isolated from each other, because unless we have the same parents, there's no configuration in the room. And Go is very, very against that kind of limiting configuration. Go is really about diversity. Go is about not who we are, animals in a sense, but Go is about what we do. And if we look and group things by what we do and not by who we are, then we have a level of diversity. We can all in that classroom be paired up together individually in different groups. There's almost an infinite number of ways we can group ourselves, because I'm sure I can find some commonality with you on something that we enjoy to do. Obviously, I think we enjoy programming in Go. That's a behavior that we can group ourselves behind. So Go is very much about, let's not limit ourselves on configuration, but let's focus on what we do. And in this code, we have the behavior we're looking for. It's speak. Dogs know how to speak. Cats know how to speak. We can group everything by what we do. Now, I also, at this point, also want to be able to start reading code and identify smells. This is very important. And when we see smells in code, it becomes also critical for our ability to be able to talk about, verbalize, explain, have the right language to help people understand what the smells are and how to fix it. And there's a lot of smells in this code as well when I go through it. Look, just alone, when I see that animal type right there, when I see that animal type, I notice that this is really a generic type just being placed in the code for reusable state. I'm really always concerned about that. The bigger smell too is that I've defined a type called animal, and yet we're not really using it. I do not need a value of type animal in this program in order for the program to be able to work. I could get rid of animal, embed those fields in cat and dog, and I wouldn't have to break a single method or function. That again is a smell. I only want types where we need values of that type. I want to be very, very clear that to define a type literally for reusable state is a smell. There are exceptions to every rule. But because we don't need an animal, guess what? We don't need the type. From my perspective, it's type pollution. Believe it or not, a little copying and pasting can go a very long way. We've been taught these concepts of dry, do not repeat yourself. But I think the cost of do not repeat yourself in Go is worse than maybe some of these other languages you've worked on. Coupling is always going to be a bigger cost than a little duplication. And we'll continue to see that as we move on. Also, when we look at the speak implementation for animal, it is completely useless. There's no value in it. And think about what we've done. I've added a type. I've added a method called speak. These things need tests, which can't really be accurate. They're not used. This is code that we have to now increase our lines of code, increase our bug potential, increase our test cases, and it adds zero value to the software. We really don't want to be polluting software like that. So I understand where this developer is coming from with the idea of grouping things by animal and creating this reusable state, but this is not how, at least I want you to design and architect and write code in the future. So then how do we correct this program? What are we going to tell this developer? Well, simply what I'm going to tell the developers, stop thinking about who you are. Stop thinking about what cats and dogs are and start focusing on what cats and dogs do. This is what's important. What cats and dogs do. Let's configuration? No. Convention. Convention over configuration. So let's do this instead. Let's remove the animal type. It is pure pollution as far as I'm concerned. And let's just bring in an interface. The speaker interface, that behavior. Remember, interfaces should define behavior, not persons, places, and things. So I want the speaker interface. If I saw an animal interface here, I'd be very sad. That's not it. Let's keep the concrete types as those persons, places, and things, and let's have the interface describe the behavior. That's that convention we're looking for. Okay, so we got the speaker interface, one active behavior, speak, and then what I'm going to do is a little copy and paste. Yes, I'm going to copy those common fields into dog and cat. You might say, no, Bill, what are you doing? What if the common fields have to change? I'm going to then go and change what needs to be changed. I'm going to refactor what needs to refactor. This is going to make code more readable and easier to debug and easier to test. I promise you, because it's always there in front of you. Dog is more precise. Cat is more precise. These things I have learned over decades of software development that these benefits outweigh that cost of dry. So there's my dog, name is Mammal Pack. Here's the speak again. Here's cat again. We just copied a couple of fields in there. Here's speak. And now we're able to create a collection of cats and dogs by what they do. What they do. This is brilliant stuff because the compiler is dynamic in its ability to do static code analysis. We're able to leverage convention very powerfully here. We're going to see in our next section where we really show how composition can help us design code that's really decoupled from change. But before we look at that next example, let's just go through these notes because I want to give you some guidelines around declaring types that we're going to be using as we move on. I really want you to focus on declaring types that represent something new or unique. Always new or unique. I really want you to avoid the concepts of aliasing. When I see a type like this, let me just throw this out here. If I see somebody do a type like this, handle int, I start to cringe a little bit. I try to say, is handle something really new and unique, or are you just trying to abstract the concept that a handle is an integer? If I don't see a method set after this type, it's a good indication that maybe we're trying to do some sort of abstraction, really, of aliasing, right? But what I'm going to say is this. You might say, well, Bill, I want to do that because I want to write a function that can only take a handle, and I want the compiler to protect me from that. I understand other programming languages, this would really be possible, but it's not possible in Go. Remember that constants of a kind can be implicitly converted. That code on line 89 there would be compilable. We would be able to compile that. So since you can't get that protection, especially on a type like handle that's based on a built-in type, then I don't want you to do it at all. If you can't have it 100% of the time, you can't have it. For me, a better API design here for handle would be the variable name being called handle and the type being int, because handles really are int. Don't abstract or alias what the data actually is. So if you cannot define a type that truly represents something new, something that isn't truly the base type, well, guess what? I don't want you to have it. Look, again, the clear example of that is duration. Duration in the time package is an int 64. It's based on int 64. But really, duration doesn't represent an integer. It represents nanoseconds of time. So I want you to see the difference between handle and duration. It does represent something new. And there's actually method sets around that. We need to always validate that if you define a type, that we are creating values of that type. And we need to use values of the type on their own. If we're not, then you defined a type purely as an abstraction layer of reusable state. And I want that to be a big, big smell. Another thing here is we're going to learn, we're going to embed. Embed types for behavior, not for state. Remember, we're decoupling. Decoupling is based on behavior. The concrete data that has the behavior drives it. But if I see embedding and it's not clear to me why we're doing it, the behavior, I'm going to ask you. I want to know what behavior we are trying to promote or gain access to through the embedding. So question any type that is an alias or an abstraction of an existing type. Also, always question types whose sole purpose is to share common state. We always want to be focusing on behavior. So let's really look at how composition works in Go with this example. And I want to give you some guidelines around doing this and writing code in Go. It's probably a little bit against what you're used to doing. A lot of you have been taught to start with the interface, start with the behavior, try to figure out what those contracts are. I don't want you to do that. That is guessing. I don't want you to do that. Remember, the problem is solved in the concrete, not in the abstract. So we need a concrete implementation and solution first in order to know how to decouple. This is going to simplify your code and allow you to focus on what's important, which is the problem. And remember, the problem is the data. Now, there's a couple of things here also that I want to talk about before we get into this example, things that I see that are missing. And one of these things is the idea of done. How do you know when you're done with a piece of code? And if you manage people, how do you know that they are done? This is a really big, important question. And for me, done comes in two different answers. The first one is you really need to make sure that you have your unit tests. And you got to have some level of test coverage. For me, I want to see anywhere from 70 to 80% of code coverage on tests before you can come to me and say you're done. It's really hard to get above that sometimes in Go because we focus on so much error handling. And 100% code coverage really doesn't add value to you. It just means that you've executed every line of code once. I would like to see 100% code coverage on the happy path, but overall 70 to 80%, and I'm good. The other part of this question, which really relates to me, is the code decoupled from the change we expect to happen? Now, we might decide that we know what the decoupling is required, but we don't need it today because we don't have multiple implementations or something, or we don't have the need today. Remember, you're writing code for today. We're designing and architecting for tomorrow. So deciding to decouple may or may not happen immediately, but I want to ask the question, do we know what has to be decoupled, and do we want to do that? And I can do this, and I can ask this question because decoupling is part 2 of everything I do. It is a refactoring. We solve problems in the concrete first. We refactor into the decoupling. There's a couple other things that I see that developers have problems with. They have a real problem breaking problems down. I'm not talking about tasks or GitHub tasks or Jira tasks. I'm talking about looking at a problem and saying, I've got to solve this, and I've got to solve that, and I've got to solve this, and it has to be in this order. If I don't solve this, then the other problems don't matter. And these are larger. These could be multiple tasks to solve a problem. And we're going to go through that exercise as well. One of the very last things that I see quite a bit is software developers don't really understand how to create a layered API. And this is really going to help you with a code base. Instead of you trying to solve every problem in a few functions, what we really want to do is find a layered approach. And usually just 3 layers is all we're going to need. we can have what I would call our primitive layer. And this layer knows how to do one thing and one thing very, very well. We're always focused on what is it one thing and one thing very, very well. We write out the code for this layer. We write our unit tests for this layer, right? And we write this layer so it is testable. Now, when I say testable, this doesn't mean interfaces. Remember, I'm working in the concrete. Interfaces, decoupling happens through a refactoring, and yet I have to already start writing unit tests. Unit tests, that code that is testable usually means that the data that we're passing in is reproducible, and the data coming out, okay, is testable. So I'm always going to be telling you over and over again, testability is about the data. The code we're writing is about the data. Decoupling is about the data. The problem you're trying to solve is about the data. So when we think about unit testing here, I want you to think about, can I write a function at the primitive layer where I could give it a set of data, gets a set of data back out, and we can validate and test it. Now your next layer I would call the lower level layer. And that's a layer that sits on top of the primitive API that does maybe some raw things a little higher level than the primitive layer. And again, we're going to write those unit tests. And this layer too should be testable in its own right. We should be able to test everything coming in and everything going out. And a lot of times this layer and these layers are probably unexported. They could be. But sometimes it's nice to export the lower level, the lower layer API, because it's very usable if we write it correctly. And it gives the developer, the users, maybe more control over the things they need. And then you're going to have your high level API. This is where you're trying to do as much as you can for the user to make their life better. Again, it's sitting on top of the lower level, which is sitting on top of the primitive level. Since every one of these levels have been coded and unit tested, by the time we get up here, we're really just thinking about an ease of use for the developer. And we're going to be able to hopefully unit test this as well. Sometimes these higher level functions require more kind of integration kinds of tests, but we want to think about how we test every layer all the way up. Eventually, you know, your higher level tests might be able to replace some of your lower level and primitive unit tests because they cover those test cases for you. And so there are times where I'm even writing unit tests that I know aren't going to exist forever, because as I move up these levels of API, I'm getting the same code coverage on tests that I've written here. And that's okay. I cannot stress enough that I don't want you to be throwing code away. I don't want you to be worried about throwing code away, right? Refactoring is about making something work and looking at how we make it better, how we make it more readable, how do we do things. And the best days are when we actually remove code. So don't get hung up that I might be writing some unit tests here that eventually we're going to delete because we're going to get some better coverage here. I'm writing those tests right away because I want to make sure these layers are working. So this stuff is very, very important, and we want to have these things in our head as we move forward, okay, and as we start really starting to write more code, you're going to see me focus on what are the real problems in front of us. How do we layer this API, not only so it's usable, but it's testable. And it doesn't mean we need interfaces. It means that we need strong inputs and outputs around data that we can test against. And then how do we refactor code to then deal with change once we have a concrete solution? All right, let's go through a real concrete example of what I mean about decoupling, solving a problem in the concrete first, and then asking the question, what can be decoupled? And I want you to see the mechanics and the flow of this, and something that I think will really help you in the future as you're writing code in Go. And this idea of the concrete implementation could be one of two things. It could be a prototype, and I really believe in prototype-oriented design, because I don't want you guessing, I want you knowing. And so it could be a prototype. It could be a prototype that we could even put in production right away. It could be a production piece of code, even if it's in the concrete. The idea today is we have to be able to get code into production faster, but code that has integrity, code that we can really start solving problems. Because for me, technical debt is when you're working on a piece of code and it never leaves your laptop. It never gets into production. We have to be better at all of this. Okay, so let's start with the problem. And here's the problem. The client comes to me and says, Bill, I don't know if you know this, but we have a back-end system called Xenia, and Xenia has a database. And I go, yeah, I know all about Xenia. Well, I don't know, Bill, then if you know about our system called Pillar. Pillar also has a database, and what's special about Pillar is that it has an API that our clients use to write front-end clients with. They consume it. I go, yeah, I know your business model. I know it's all good. Well, Bill, I don't know if you know this, but some client of ours that consumes Pillar, they found out about Xenia, and they asked, hey, can you get that data out of Xenia and move it into Pillar? Because if you can, I'm going to sign a very large contract. I want to consume that data. So, Bill, do you think we can move data out of Xenia and into Pillar? So immediately I say to myself, well, this is like anything else we do, right? It's a data transformation problem. And I've got to be able to figure out how complex the data transformation is. But the first question I'm going to ask is, what is the latency that we can have in getting that data over? Make it reasonable. And they say, no, Bill, if we can write a program that maybe runs on a cron job every 5 minutes, we can move that data every 5 minutes. Bill, that is more than enough. I go, 5 minutes is brilliant. I mean, 5 minutes is eternity. I like that. Let me go look at it. Now, as I go ahead and look at this problem, there's a couple things that I really want you to understand. One, I am only focused on the problem at hand, the concrete problem, which is taking data out of Xenia and moving it into Pillar. I am not thinking about contracts, interfaces, decoupling, none of that. Get that out of your head right now. That is a refactoring for later. Right now, I have to solve this problem. And the best part is if I solve this problem, I can get this in production. And then I can ask, once this is in production and life is good, what can be decoupled in this code to make it better, to allow it to deal with change as the data or the business problem changes. But that's not my problem right now. My problem is moving data out of Xenia into Pillar. Now, when I look at this, I start to ask myself, again, at the higher level, what are the problems I have in front of me? And I begin to realize that I've got about 4 problems here that I have to solve in this order. The first one is I've got to learn how to connect to this database. Because if I can't connect to the database, then nothing else matters at all. That's problem 1 right here. Then, I've got to be able to figure out what data I haven't moved from the last 5-minute run. That's problem 2. If I don't solve that problem, then no other problems I have in front of me matter. If I solve those 2 problems, then I got to solve the connectivity problem here. That's number 3. And then I got to get the data in. Look, these are 4 problems that I have to solve. This is what I mean by problem. There's lots of little tasks involved, but at a high level, I got to be able to connect. I got to be able to find the data. I got to be able to connect. I got to be able to put the data in. Okay, this is it. These are my problems. This is what I have to solve. So I'm going to go now back to my desk, and we're going to start writing some code. And I come up with this solution. Now, I don't want you to worry about the full implementation. Don't worry about the full implementation here. I want to look at the mechanics. I want to look at the architecture and the structure of what we're doing, and then we'll continue to talk and refactor this code. So let's look at the base prototype code that we end up putting in production that solves the problem at hand. Now, look at what we do here. I've made the data simple. Obviously, it would be more complex. It's not important. I want you to look at the flow and the design and what we're doing here. So that's our data. That's the data we're moving, transforming, and putting into Pillar. Now, I need to focus on my primitive layer, right? I told you I want to work on my primitive layer, my lower level, and then my higher level. So we're focused here. The primitive layer API has to be able to do one thing, and one thing very, very well. So I decide, look, I've got this stateful system called Xenia. I've got to be able to connect to it. I've got to be able to maintain some state about what I'm doing. And so I'm going to build a type-based API. In other words, I'm going to build an API where it has a data-oriented, right? A data-oriented API like we were talking about. When should data have behavior? Normally when we're trying to decouple something, and sometimes we have APIs that are stateful. So that's what I'm going to do. So I define the Xenia type. There it is. Got host timeout information. Let's pretend already, though, I've solved the connectivity issue. Let's just do that. We're going to bypass that in this example. Well, let's pretend that I've solved that problem. And the next problem now is try to figure out what is the next piece of data I have to move. Again, this is a primitive layer API, so I'm just going to focus on this idea. One piece of data. What is the next one? So I've come ahead and I've designed this API. This API is called pull. It's a method off of Xenia, and it takes a data pointer, right? So we're going to share data down the call stack. That's going to help us with allocations. I don't want to pass data up. I want to share it down because this is going to be in a tight loop. The idea is this method knows how to find and pull the next piece of data that hasn't moved yet. And every time we call it, we'll get the next piece. Now, you might be sitting there already looking at me going, Bill, whoa, 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 whoa. You're telling me that if there's 10,000 pieces of data to move, you're going to make this call 10,000 times? Bill, that's going to be too slow. What are you doing? And I'm going to say, stop. If you're telling me right now that this API is going to be too slow, you're guessing, because until I have a working program and benchmark and profile it, we don't know. And I don't want you optimizing for performance. I want you optimizing for correctness. What is the simplest, cleanest way to solve this problem? And if it's fast enough, we don't need to make it any faster. And if it's not, then we'll try to be a little clever. And again, even to the extent of minimizing the cleverness. So please stop focusing on performance right now. We're writing code. We need something working because until it works, we don't know. So I'm going in this direction. My primitive layer knows how to pull one piece of data, the next piece of data, out of Xenia. A lower level can worry about pulling batches of data. A higher level can make it all very simple through a single API. Now, I didn't really implement it. I'm using a random number to generate the fact that maybe we've pulled the last piece of data, or we got an error, or we actually got some data. The implementation is not important. What's important is the API design and the fact that we're going to simulate whether or not things work or not. OK, guess what I just did? I solved my first two problems. Yay. Now we got to solve this problem. I got to connect to this database, and I got to store whatever data we pull. So guess what? Another good example of using a type-based API, because we've got to maintain state here, and we're going to have to be able to store. So just like we did with pull, we're letting store come in. We're using pointer semantics for the data. We pass it down. Again, we're going to be able to minimize those allocations, as we call this. And store knows how to push that data that we have into the database. We have just solved all four problems. We know how to do the core things we need to do. We also now have finished our primitive layer API, and we've written our unit tests. Let's pretend this layer is done. Now, we got to start focusing on the lower level. And the lower level's got to be able to pull a bunch of data out and push a bunch of data in. We've got to be able to pull and store from these two systems. And when I say pull and store from these two systems, something kind of triggers in my head. How cool would it be to define a concrete type called system, which represented Xenia and puller? And if I use the embedding or composition of the two concrete types, Xenia and pillar, now what I've done is I've said a system in this program knows how to pull and knows how to store. I'm not embedding because of state. I'm embedding because I want this behavior called pull and this behavior called store. This is critical. I have a concrete type that knows how to pull and store now, thanks to the embedding. We'll see how we can use this, but I'm going to go back into our lower level API, and I decide that what we really need is a function called pull. Remember, we want to use functions first before we go ahead and use a method set. And I want to ask you this question while we're here. This is a good time. Why would I say and believe that a function is always going to be more precise than a method can ever be? And this is true. Functions can always be more precise. And the reason a function can always be more precise is because a function requires you to pass in all of the input in order for it to be able to perform its data transformation. Methods, when they're not designed properly, hide information. And when we start designing method-based APIs, we still have to take extra care. It's a little bit harder, but to take extra care that we're not hiding things. Because when we hide things, then we're setting up for fraud and misuse. I'm going to give you an example here while we're here before we move on here. Imagine I needed to send an email to a user. And it might be really possible that I have this user struct, right? And that user struct probably has things like name, probably has an email field, and it's going to definitely have more fields, right? More fields. I don't know what it's going to have off the top of my head here, but it's definitely going to have more fields. Now we want to send an email. And you might go, OK, I know how we're going to do that. Let's just go ahead. We'll use our pointer semantics on a user. And I'll write a method called sendEmail. Look at that. I can do this. This is how we've been taught to design these APIs. I already have the user state. Then I add the behavior to the data. But this is a horrific, horrible API. This is exactly the opposite of what I want you to do. This API is not precise. It is riddled with fraud, because this API right now doesn't tell us what that user value needs to have in terms of initialization for this function not to fail. And I don't want things failing at runtime because the state of a value is incomplete. That is a no-no. That is a major violation. The compiler is there to help us around these issues. Don't do things like this, because the only time we're going to know if there's a problem is in production. I mean, today, maybe sendEmail is using name and email. But what if I change sendEmail one day to require the use of the person's age? Guess what? Nobody calling sendEmail, not even the compiler, knows that now we need age to be set, which means that anybody who calls sendEmail now, moving forward, will fail on sendEmail because they didn't know that age had to be initialized. And we don't know this until production. And when you have production bugs, this is the last thing you want to deal with because there's stress. This is a very bad API. It is generic, and it is not precise, and it's not going to help us. We've got a compiler. And by the way, this is absolutely no better. Functions like this are nothing more than methods. They're methods, right? We don't want this. So how do we write an API that's precise using this example? Well, this is what I want to see. I want to see a function. And I'd want to see a function that said, give me a name and give me an email. This is it. It doesn't get any more precise than this. And what's nice is we've reduced any misuse and fraud because everybody knows it's name and email is needed. It's also easier and more precise to test because we're not guessing about what that user value needs. And I'm sorry, but if we need age tomorrow, I am going to absolutely take the cost of the API breaking. Most of us work on a private code base. It is okay to break APIs. I demand that the APIs break because now the compiler can tell us everywhere in the code base we were going to have a problem with sendEmail before the code makes it into production. And I do have code in production level software that has functions that can take up to 8, 10, 12 parameters. The more precise, the better. So don't get into this idea that we have to abstract input, because abstracting input is going to hurt you with your testing. It's going to hurt with your users. It's also going to hurt with debugging. So we don't want to do these things. So this is why I'm going with a function-based API first right here, because this always should be our first choice when it's reasonable and practical, and it is. Pull can take the pointer to a Xenia and can take a slice of data values that we want to populate one at a time. Look at how the lower level API sits on top of the primitive API. We're now going to range right here. We're going to range over pointer semantics because we should be using pointer semantics with data. And we're going to pass the address of each index into our primitive layer pull. And after we get a batch of data coming in, we now have the same thing on the store. Store works with pillar because that's all we know how to store into right now. A slice of data values that we've pulled, we range over it, and we call store, and we can write tests to validate that all this stuff works as well. You see what we've done now, we've finished our lower level API, we've written our unit tests for that as well, and now both layers are working together. If we know this works, our lower level API is going to be easier to write, and we know it's going to be solid. And now we need our higher level API to bring it all together. And we go ahead and we say, okay, let's write a high-level API so users don't have to implement their own kind of higher-level stuff, and we'll call it copy. Now, notice that copy needs two behaviors. Copy needs to know how to pull, and copy needs to know how to store. And this is where that idea of a system comes in. Remember we talked about a system of Xenia and Pillar. A system knows how to pull and store. So now, since copy needs both behaviors, we can say, okay, give me a system that knows how to pull and store. Give me a batch size. We'll have one allocation here, but that's no big deal. It's based on a variable. We'll take one allocation per this. This is fine. And then we go into an endless loop, calling our lower level API, pull and store, passing our Xenia and our Pillar through. And guess what? We're done with our higher level API. We can even write tests for that if we want. We now have written every layer of our API sitting on top of each other. Nice and clean, mental models in place. If there are problems, then we know what layer that problem is probably going to be in, and we can find it and solve it quickly. So now we're in our application, and we go ahead and create a system. We initialize Xenia and Pillar. Let's pretend we've got our connectivity in place. We call our higher level function there called copy. We pass system batch size of 3. And guess what? We have a program that's working in the concrete. And we go ahead and take that program and we now push it in production. This is now in production. We have solved this problem. But here's the question now. Are we done? I mean, we're halfway done. We've written our unit tests for every single layer here. But we're not really done yet, because I told you you're not done until you ask this question. What can change? What can come to this program where we've got to do some decoupling? And when we really look at this and understanding the business problem, because a lot of times you can't answer this question technically, it's more of understanding the business, we realize that what's going to change is the systems are going to change. They're going to come in now that we've solved this problem, and they're going to say, hey, Bill, you know, I don't know if you know this, but there's a system called Bob out there. And Bob has a database, Bill. And it would be great if we can move some data out of Bob. And Bill, I don't know if you know about this, but there's also a system called Alice. And Alice is this new front-end API that we're building. And Bill, it would be great if we could start doing this. What's going to change? The systems are going to change. So what we now need to do is ask ourselves, do we want to decouple this code today for this change? And if the answer is yes, then we're going to take this concrete implementation and refactor it to deal with this change. And that's the next thing we're going to do. All right, now that we had that concrete implementation, let's go ahead and look at how we can decouple this code from change. Now, one of the very first things we want to look at is the lower level API. And the lower level API was this. It was pull and store. What we need to do is decouple pull from the concrete. Nothing that pull knows about should be based on the concrete. It has to be based on what? Decoupling our interface. And to understand what interface we're supposed to use, I don't have to guess. I already have an implementation of the lower level API. Remember, I've implemented Xenia, and Xenia knows how to pull. And I've implemented Pillar, and Pillar knows how to store. Look at this. My concrete implementation has provided us the behavior that we're going to use to decouple us from the concrete. This is why I don't want you to start with the behavior or the interfaces. We start with a concrete implementation. Let's go ahead and lay in those interfaces now. So I'm going to come in here, and I'm going to add two interfaces. There it is. The puller interface that knows how to pull, and the storer interface that knows how to store. And I'm not guessing. I already have a strong implementation of pull and store. We've worked this out. We've got a working program in production. We know these APIs are good. We also know everything was fast enough. I didn't have to worry about my primitive layer being too slow. Remember, it was fast enough. Life is good. Now we can go ahead and decouple. So let's go into our lower level API, replace Xenia with Puller, and now we can use the Puller interface to execute the behavior. We have the highest level of decoupling we can achieve in Go. It is thin and it is precise. We're asking for any piece of concrete data, any value or any pointer that knows how to pull. And we do it again with store. Give me any piece of concrete data, any value, any pointer that knows how to store. And we do that through the API. Look, all I've done is replaced my lower level API with a layer of decoupling. And guess what? Boom. Now I can create other concrete types for other systems and that lower level API can work with those other systems. Now, we're still not done yet. We've got to decouple all the way through main. The only code that should have to change is main before copy. And copy right now is working with the concrete type system. It would be nice to also decouple copy so it can work with any system that knows how to pull and store, right? So let's go ahead and now go ahead and we'll add a third interface. And what's cool about this is we can also leverage composition at the interface level. Look at that. That is the pull store interface. And it's very common naming conventions, very idiomatic in Go, to when we compose two other interfaces to use that pull store. We see it with read closers and write closers, and here we are, the pull store. So now through composition, embedding, now any piece of concrete data that knows how to pull and store is also a pull store. And isn't system already a pull store thanks to the composition of Xenia and Pillar? It absolutely is. Our concrete type system already knows how to pull and store. So look at what we're able to do. We're able to now pull system out of the API, another refactor, say pull store. System already implements the pull store interface, which now means that in main, and when I pass a copy of the system pointer, it already implements pull store, and this code now, at least from the lower level and the higher level API, is completely decoupled from change. But there's something very interesting in copy that might concern you. It concerns me initially. I want you to look at the calls to pull and store. You may not realize this, but we're passing the PS variable into pull and the PS variable into store. This should take some alarm. Whoa, 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 Bill. Pull isn't looking for a pull store. Pull's looking for a puller. Store's looking for a store. PS is not a puller or a store. Why is this code compiling? Well, let's do the following. Let's walk through this code, and I'll explain to you why this code's able to compile. So we start with our system. Here it is. And remember, our system is the embedding of Xenia and Pillar. We know Xenia knows how to pull, Pillar knows how to store, so our system knows how to pull, and our system knows how to store, right? We're getting all of this through the inner type promotion. Now we take the address of system on the call to copy, and when we get to copy, remember copy is completely decoupled. It has the pull store interface. Remember, interface values are valueless. Interface types are valueless. It's saying give me any concrete type, any value, any pointer, any piece of concrete data, any value, any pointer that implements the pull store interface. We know system does. So now what happens is we get our PS. It says I got a pointer to a system, and we're storing through pointer semantics our system value. Great. Now, here's the interesting part. We're able to pass PS into pull and store because remember, pull is not asking for a value of type puller. It does not exist. There are no such things as type puller. It's saying give me any piece of concrete data that knows how to pull. Store is not asking for a store. Any concrete piece of data that knows how to store. And here's the cool part. We're not passing PS to pull and PS to store because they don't exist, right? PS doesn't exist. Get this in your head. PS is valueless. It doesn't exist. What exists? The concrete data. So what we're really passing to pull is not PS. We're passing what is stored inside of PS, which is the concrete data, which means that when we call pull, what we're able to do is pass the concrete data through. Look at what we've done. Now, the memory models are the same, but what's more important is I'm not passing PS, I'm passing the system address. Boom. And the same thing with store. I'm not passing PS, I'm passing the concrete data that was stored inside. So get this in your head. We're always moving and copying concrete data, whether that data is directly copied by you or it's being copied indirectly from the interface, the valueless interface, right? Yeah. I mean, this interface now has a value thanks to the storage of this concrete type. So we're always moving the concrete type across the boundaries. And in this case, the data that we're moving is the address of system. That's why we're able to do this. Now, we could call this implicit interface conversion if you want, But I'd rather really focus on the idea that it's the concrete data that's being moved around, not the interface value. Again, the interface value is valueless. Now, we're not done yet because I already said that we have to decouple all the way through main. And though our APIs are decoupled here, the reality is that if I want to use Alice or Bob, I can't right now. We have a concrete type called system. And system is the embedding of Xenia and Pillar. If I want to use Bob or Alice, I either have to break system, which is not good, or maybe what I can do is define another system type. Maybe I can do this, right? But think about this for a second. If I do this, if this is not scalable, system 2 is a pull store. I mean, this will work. But what happens for all the different combinations of Xenia, Pillar, Bob, Alice, all of that? This isn't scalable. This is really not the direction we want to go in. That being said, how can we solve this problem then? Well, let me ask you a question. If system wasn't the embedding of Xenia and Pillar, but the embedding of our two interface, if I can type this right, interface types. Whoa, what does this mean? Think about it. I have just defined a concrete type where I can inject other concrete data based on that data's behavior. Now all I need is one system type, because the system, we can inject concrete data inside of it. Look, so how do we take this now and make these changes? Well, let's go in here and say this. A system now says puller, and this is now storer, and we've got to use our pointer semantics because we've implemented the interfaces with pointer semantics. And now look at what we've done. We're injecting Xenia. We're injecting Pillar. Later on, we can inject Bob if we want. We can do that all through this one concrete type, which means we can still pass system through, and everything should work. Let's see if I did. There it is. Look at that. We're now able to inject data into our concrete type, and we have a full layer of decoupling. We can define a system to be almost anything as long as the other concrete data implements the right behavior. Now, it's very important to me after we get a piece of code working that we do a code readability review. Code readability reviews are critical. There's really two types of code reviews you should be doing. There is the readability review, and you should be doing this every single time you get a piece of code working. The readability review there is to make sure that we're consistent with our variables, with our API designs, with our semantics. These things must be in place, right? We want to make sure that our mental models of our code is always in place. Treat the readability review as a way of validating our mental models of every function, every method, the location of things, the namings of things. Then the next review after that is going to be more of a technical review. There we could also look at API design. We could look at algorithm efficiencies. We can look at things that maybe we want to improve. But the code readability review is critical. And when I start doing a code readability review, I realize one thing here. I'm never going to have more than one system type. The system type, thanks to the embedding of the interface, is already fully decoupled. And since I'm not going to have more than one system type, this interface is now pollution. Look, I can go back and work in the concrete because I'm never going to have a second implementation of pull store. Having it there is a waste of time. I can now go back and use our concrete type, which means that I can go ahead and remove code. Oh, it's a great day when you can do something like this. So there it is. I can remove this code. I change my higher level API back to the concrete type, passing system. This code works, and I'm still at the highest level of decoupling that I can achieve in this program because of the data injection. Now, I do another code readability review, and I realize something else. This idea of data injection is super cool. But guess what? It's clever. Because this API isn't as precise as it could be. I mean, honestly, wouldn't this be a more precise API? Look at this. Think about this for a second. Wouldn't this be a more precise API? I mean, system is really hiding the cost of initialization. We don't really know what a system is when we look at copy. We don't realize we need these two behaviors, at least somebody new to the code base. But now with this new API definition, we've reduced fraud. We're going to make this API easier to use, easier to test, because it's exactly saying, give me concrete data that implements puller, give me concrete data that implements store. We know exactly what copy needs and what it does, and much more than when we use this idea of a system. And again, I want to be as precise as we can be. So now if we replace our API design to use puller and store, now what we're going to do is pass our puller, pass our store. That will fix that problem. And even main cleans up, because if you really think about it now, we can go back and just construct the concrete type. The concept of the interface is completely gone from initialization. Let's clean this up. Let's get rid of this. I'm going to use the special go func to clean that up. And now what we're going to do is share Xenia and share pillar with copy. And even our main program here has cleaned up tremendously, because we're focused again on what's important, which is what? The concrete. Right here during initialization, we focus on the concrete data. Xenia and pillar are the problem. We pass Xenia and pillar into copy, a higher level API. Our higher API is already decoupled now. Give me anything that implements pillar, anything that implements store, and we now have decoupling throughout the entire application. And we've got an API now that really is going to limit and almost reduce all misuse and fraud for this software. Notice that this was a refactoring, and I don't want you to be afraid of refactoring. If you're not refactoring, you're not improving. If you're not refactoring, I think you're doing things wrong. Look at the approach we took here. Layering the API, validating every layer was testable, and we're thinking about tests from a data point of view, not from a decoupling point of view. I don't want to hear, oh, Bill, we got to write tests and we got to decouple code because we got to write tests. Let's throw an interface at it. No, 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 no. Layering, testing through data, building on top of each other, implementing a concrete solution first, and then asking what needs to be decoupled, and decoupling the program through more layers of refactoring, and then doing code readability reviews to tighten up these APIs, and asking ourselves, where is there potential fraud and misuse? Where can we be more precise that we know the problem a little bit better? And then putting those changes in. All right, let's go explore a little bit deeper the idea that we're passing concrete data across these program boundaries when we're using interface values. We could call this, like implicit interface conversion. But again, I really want to focus on the fact that it's the concrete data that we're moving, and I want to look at more of the mechanics behind it just to solidify this a little bit more. So look, I've got the mover interface, the locker interface. That's move, lock, and unlock. And then I've got the move locker. Remember the composition of multiple interfaces. So a move locker knows how to move, lock, and unlock. We've got the three interfaces right there. Then I've defined a concrete type named bike. Now this is implementing using or declared using the empty struct, right? This is a case where you might want a method-based API for some reason where there is no state, right? Maybe we're using bike as a namespace. Again, I want to be very careful. Remember, functions are always going to be more precise than methods. But in this particular case, since there's no state, then the API would have to be as precise as any function, right? And we've got the implementation of move, lock, and unlock. So a bike is a mover, a locker, and a move locker. OK, great. Now, this is where things get fun. On line 49 and line 50, we're declaring two interface values set to their 0 value. There they are. That's the move locker. That's the mover right there, again, set to its 0 value, a nil interface. And then we go ahead on line 54, and we construct a bike value. There it is. There's our bike, right? Set, and it's an empty struct, but there's our bike, and we assign it to the move locker interface. We can do that because we've implemented that. And if we go back and look at the implementation of the interface, it's using value semantics. So we can store copies of values and the addresses. And we're using value semantics here. So this is going to say we have a bike, and we're going to point to that bike value right there. There it is. Remember, it's the empty struct. So I could argue that really what we have is a copy of the bike. We're using value semantics, right? But since there's no construction anywhere else there's no variable, let's just look at it as there's our bike. Now, what we're able to do on line 58 is go ahead and say, let's assign ML to M, two interface values. But we're not really assigning the interface values. Remember, the only thing that's real is the bike. So what we're really saying is, let's store the concrete type bike inside of M. And the compiler knows whether or not this concrete type has all of the behaviors to satisfy M, because the interface declarations make it. And we know that any concrete type inside of move locker must be able to move, lock, and unlock. We know all three behaviors exist, move, lock, and unlock. Therefore, we can do the assignment because the only behavior we need is move. And so now we say we've got a bike in here, and boom, there we go. We can do that assignment. However, we can't go in the other direction. I can't assign a mover to a move locker, because when it comes to the mover, the only behavior that we are aware of is move. This is the only thing that we know about. We don't know if there's a lock and an unlock in here when we look at the concrete data from the mover perspective. When we look at it from the move locker perspective, we know. So we're not able to do that assignment. Now, Go has something else that's very special. It's called type assertions. And a type assertion in Go allows you to ask a question about what is stored, about the concrete data that is stored inside the interface. Allows you to ask a question. The question we're asking here, and look at the syntax, the interface value dot whatever type we want to ask the question around. What we're asking, and this happens not at compile time. Everything I've shown you so far can be checked at compile time. Type assertions happen at runtime. And what we're saying on line 76 is, I believe when this code runs, in that moment in time and space, that the concrete value that's sitting inside of M is a bike value. That's what we're asking. Now, if it's true that there's a bike value in there, since we're using value semantics, B will be a copy of that bike that was stored. It will be a copy. If it's wrong, then we panic. We have an integrity issue. You're saying absolutely there needs to be a bike in here, and there isn't. All right, but there is a second form to the type assertion, which is this OK value. And this is a Boolean flag. And we want to use this when we may not necessarily have a concrete value of that type. Now what this is saying is, I believe there's a bike value inside of M. If there is, great. OK is true. B is a copy of the bike. But if OK is false, then there isn't. Do not panic. We know that there's a chance that that might not be true. And then B isn't a copy of the bike. It's set to its 0 value or 0 value bike. Type assertions are very, very powerful. And I want to show you some examples of type assertions and how they are working pretty well in the standard library. One of the best places to look is, I'm going to do a search on Golang IO. I'm going to look at the IO package in Go, and I'm going to come in here, and I'm going to look for the copy function. Now, anytime you're looking at Go documentation, if you find something you want and you want to look at the source code, all you got to do is click on that header link. If you look again, I found it. I click on the header link. It brings me right to the code. And I really want to look at the unexported implementation of this copy buffer. Notice that copy buffer is saying, give me any concrete piece of data that implements writer, any concrete data that implements reader. But look at the very first if statement. And this is interesting. What it's saying here is the following. If the concrete data stored inside of the reader variable, right, source, also implements this other behavior. Notice we're type asserting now not to the concrete, but to another behavior, another interface type. If the concrete data also implements this other behavior, then let's bypass the default behavior of copy and use this custom one. Again, what we're able to do is override this default copy behavior by allowing the user to have their own implementation of things. Type assertions are very, very powerful as part of an API design, because that means you can design an API that has a default implementation, but then use interfaces to help override the default. In fact, I'm going to show you another example of that exactly looking at this code right here. Now, Here I've got a concrete type named user. And user implements a method called string using pointer semantics. Actually, a little more is going on here. This method named string that returns a string implements the stringer interface in the funct package. This is a way of overriding the default output behavior of the funct package. But we're using pointer semantics, which means what? Only pointers satisfy the interface. If I share pointers with funct, we get to override the default. I share values with funct, we don't. We'll get the default behavior. And let's see that happen live here. So there I am creating a value of type user, and then I use my value semantics on line 29, and I use my pointer semantics on line 30. Well, using value semantics, when we implement the interface using our pointer receiver, means that we should see the default output, which is what we do. That's the default formatting for a struct value. But because we now pass the address of u, we're able to override the default thanks to this method being implemented. Basically, the call to print is doing that same type assertion. It's saying, hey, this concrete data that we passed in, does it also implement that string method? If it doesn't, like on line 29, no big deal. We have our default implementation. But if it does, like on line 30, we get to override the default. This is a very powerful API design through type assertions because it allows you to have a standard implementation for something, but not bind the user to that. Tell the user, hey, if you got a better way to do it because maybe you're on this OS, you're on this architecture, or you just know better than I do, then I'm going to give you the opportunity to override it. Type assertions, remember, they happen at runtime, and they're very powerful parts of designing an API. So I can smell interface pollution almost from a mile away. And normally interface pollution is a result of starting with interfaces instead of your concrete implementation. And up till now, I've been trying to show you how powerful it is to start with a concrete implementation and refactor into the decoupling. Again, we're focusing on data all the way through. But I want to show you a piece of code that maybe can help you understand a little bit more about this interface pollution and where it sometimes comes from. So I had a friend who had implemented a piece of code that was supposed to implement boilerplate code for a TCP server. And he had asked me to do a small code review. And as soon as I opened up the source code file with him, I saw this interface at the top of the source code file. Server interface start, stop, and wait. Immediately, this interface smelled very, very bad for me. Remember, I told you an interface should describe behavior, right? And server is not behavior. Server is a thing. It's a server. It's something real, right? And so that immediately is a smell. Another smell is that it's got these three methods in it. And when I start thinking about what a TCP server is, start, stop, and wait, it seems like to me on the surface this is already modeling an entire API set. I mean, I can't imagine everything in the code needs all three behaviors all the time. But the first question I really ask him is, dude, are you asking the user to implement this behavior? And his answer is no. I mean, I implemented this behavior. I go, I thought so. I go, do you have multiple implementations of a TCP server in your code base? And he said, no, I got one implementation. There's another smell. I don't see anything that needs to be decoupled. I'm not asking the user for implementation details. I don't have multiple implementations. So I asked him, why is this interface here? It doesn't seem reasonable or practical. And he said, the one thing you don't want to say to me, Bill, the interface is there because we have to use interfaces. No, you do not have to use interfaces. You have to make engineering choices. Remember, interfaces add the cost of indirection and allocation. And so this interface is serving absolutely no purpose. Without even me looking at the rest of the code, I already know that there's pollution here. But when we look at the rest of the code, it just really comes home. There's our concrete implementation implemented as an unexported type. And then the factory function is returning the value, but as the interface. Again, this is no. Factory functions initialize concrete types, should return the concrete type value, and the caller will deal with the decoupling if it's needed. All of this stuff is a very, very, very bad smell. And the interface is implementing or defining a method set for the entire API. Look, a caller, a user is going to do this. new server, and then use the API. And if I switch out the interface for the concrete type, this API, this code doesn't change. If anything, this code actually gets better because we have potential of reducing allocations. So major pollution here. And it took me about a half an hour to talk my friend down to get rid of the interface. But there's some really smells here that I just want to reiterate as we looked at this code here, okay? I saw an interface that matches the entire API of the concrete type. No. Interfaces define behavior. We should only have those behaviors we need to decouple those aspects of the API that need to be decoupled. Also, we've got an interface that's exported. We have a concrete type that's unexported, and yet we're returning that unexported type back to the user. Even though we're doing it through the interface, that's a big smell. That factory function should be returning concrete values or pointers, not the interface, okay? And if I remove the interface, nothing changes from the API because the interface really wasn't decoupling anything. So what I really want to do with this code and what I talked to my friend about was get rid of the interface. It is pure pollution. Use a concrete type, exported concrete type. Implement your factory function to return the pointer to the exported value. Implement your API and let the user work in the concrete. There are not multiple implementations of this, and the user has to provide you nothing. And so here are some guidelines that we're going to be maintaining as we go forward. We want to use an interface when the user of the API needs to provide some implementation detail that we're not able to implement ourselves. Or if we have multiple implementations of something and we want a layer of decoupling in our code around that concrete data. Or if we've identified parts of our API or code that requires decoupling because of change. And always question an interface when its purpose is for writing testable APIs. I cannot say this enough. If I hear somebody say the interface is there because I have to be able to mock in order to be able to test, I'm going to scream. Mocking isn't always really the right answer. Like if you're mocking a database, you are now wasting time. Those tests are useless because mocking a database isn't going to really give you accuracy of whether that code works. And with technology like Docker today, you can literally spin up that database in a Docker container when you type go test and validate that your database stuff really works, not mocking. And there's lots of things I see people mocking when it doesn't need to be mocked, where either we can leverage data for the testing side of it, or we can leverage Docker to put those systems in place. I'm not saying that you shouldn't be mocking things all the time, right? We need to make smart engineering decisions. There are times where maybe a third-party API could absolutely be mocked. We have expected behavior from the API, and I don't necessarily have to go out and hit it. But databases, sometimes other types of systems, mocking is a waste of time. So let's not just say that I need an interface because I have to write tests. Our APIs are for users. We have to make sure that they're layered properly, that they're testable, but we don't want to do things to an API for the tests that are going to make the API less usable for the person who has to use it. Okay? So if we're not providing support for decoupling, if it's not clear how the interface is making the code better, it probably isn't, and we should probably more think about removing that interface and sticking with the concrete types. So I want to reiterate that I don't want to be using interfaces anytime we have to think about mocking. But I really want to show you some mechanics in Go about that convention over configuration too, because it's really helped us have to write less code and has taken the burden of testing, or at least worrying about users' tests from that API developer. So let's start with this piece of code here. Imagine one day that I have a client. My client loves the pub/sub type of strategy, right? We have a message bus in the middle, and what we do is all of our services connect to the message bus, and services talk to each other. We get service discovery through the message bus. It's a really nice starting pattern if you're trying to do microservices. And what I've done here is my client has come to me and they said, Bill, we have our own internal message bus. We've had it for years. We use it. We love it. We want to start writing code in Go, but we don't have a package or an API that lets Go developers connect to pub/sub, all that good stuff, to the message bus. Will you write the package? I said, absolutely. I'll implement the binary protocols. I'll do everything you need. But my question to the client is, how many message systems do I have to worry about? They said, no, Bill, just one, just this one. This is the only one that matters. So there's not a second one. No, Bill, just this. Look, I don't need interfaces. There's nothing to decouple. There's not multiple implementations, and I don't need anything from my user. So I design an API entirely in the concrete. And I come up with this type pub sub. It's got other fields like host connectivity information. I've got my factory function returns a pointer of the concrete type. And then we implement our API. Now we can pretend this is a 10 method set API. It's a method-based API because pub sub has state, connectivity issues, things like that. So we've got here publish and subscribe. We pretend that we've implemented that. Brilliant. Now, I implement this, and now it's time to write tests. I'm not going to add an interface to write tests because I need to make sure that my binary protocol works. So what I'm going to do is use Docker, and I'm going to put that message bus system that this client uses. I'm going to put it into a Docker container, and every time I call go test, I'm going to bring up the message bus, and I'm going to make sure my entire API and all the binary protocols work as expected. Nothing's mocked. When this code is now ready for a user, I know everything absolutely works. So I finish the code, and I go over to somebody on the other team, and I say, here is the pub sub package, start using it. And a couple of days later, they come over to me. Maybe Jack. Jack comes over to me, and he says, Bill, come here, I got a problem. And I say, dude, you found a bug with the pub sub? He says, oh no, man, I haven't even gotten that far yet. You know, I started realizing that I need to write tests against the pub sub, and I'm not going to have a pub sub system to hit when I write tests. I need to mock the pub sub system. And I think about it and I go, you know what, you're right. For your application and for your application's tests, you need to mock. You should assume that the pub sub API works. So you should be able to mock, if I subscribe to this and publish that, I get everything back. I go, you're right, you need to mock your test. He goes, great, Bill, I appreciate that you understand what I need to do. You didn't give me an interface, so I can't mock it. Can you go back and add an interface to your package? And I say, dude, no, I'm not adding an interface to my package because I don't need the interface. I don't have a need to mock. My tests hit against a real system, thanks to Docker. My API is one and only one. I go, you need to mock, not me, so I'm not going to provide you an interface. And he says, Bill, why are you being a jerk? You know I need the interface, just give it to me. And I say to him very quickly, I'm not being a jerk. What you're not understanding is this is Go. And Go says that I only have to worry about my tests, and I don't have to worry about your tests. Your code, your tests need this interface, not mine. So sit down, Jack, and I'm going to show you something. And what I tell Jack really clearly is to do this. Jack, there is nothing stopping you from going ahead and defining your own interface. Remember, Go is about convention over configuration. Isn't it true that if Jack implements this interface for the methods that he's using, because he might not be using all of them, then doesn't any concrete type that I've defined also satisfy this interface? Yes. Think about how convention over configuration is helping us to reduce code and cognitive load. Jack can go ahead and define the interface he needs, write his entire application using his interface. I don't have to provide it. And yet any concrete piece of data, any value or pointer that comes out of my package can satisfy this interface for Jack. So Jack now in his tests defines a concrete piece of data called mock. He implements the API that he needs, and now he's able to mock. And then when his application comes up, he either calls pub sub new, he gets the concrete data from my package, or when his tests start to run, he just creates his own concrete data. But his entire application is built not on the concrete, but on this valueless interface. And Jack doesn't need me. My code is clean, streamlined, and Jack's code that needs a decoupling defines the interfaces. This is what's beautiful about Go and this idea of convention over configuration, that we've now shifted this idea of responsibility, that if you need to worry about tests, you worry about your own tests. I don't have to do anything special in my code because you have to test. This is brilliant, brilliant stuff coming out of Go. All right, I just want to sum up everything we just did in this composition around design and just kind of here are the cliff notes of everything we did and things you should be thinking about when we start moving from the concrete into behavior. We start decoupling our concrete solutions. Now, interfaces are very, very powerful, right? I don't want pollution, but here are some really interesting things. Interfaces are going to give our program structure. They're going to encourage design by composition, and I showed you how that composition works. And they also allow us to enable and enforce these clean divisions between components, whether these, and a lot of times these components are going to be these packages. We're going to start talking about package-oriented design eventually, and we're going to really talk about decoupling. And the interface can really help with decoupling because remember, I can define an interface that satisfies your concrete values, and you can define interfaces that my concrete values, and therefore these interfaces, which are isolated and defined within the packages themselves, can create very clear divisions. And we have really nice layers of decoupling through convention, not configuration. Now, again, when we talk about decoupling, we're really trying to reduce dependencies. We're trying to decouple components and packages as much as we can. And that's always going to lead to correctness, quality, and performance. It's going to allow a code base to grow over time and not suddenly come to a halt. And we've seen that already by some big projects in the Go community. Okay? Remember, when it comes to grouping, we don't want to group by what we are. We want to group by what we do. We don't want to talk about who we are. That's configuration, right? Our parents made us who we are. But we individually decide what we want to do. And that's how we want to group things, or I want to be around people who are not necessarily like myself from a DNA perspective, but who like to do the same things that I do. We want to focus our code around that level of diversity, okay? Level of diversity. So that interface is going to help our code decouple from change. It's going to allow our code to maintain decouplings between packages or components. And we've got to really do our best to understand what is going to change in our code and try to decouple that. And it really helps if you start with that concrete implementation, that same exercise we went to, okay, the same exercise. And if it's not clear what an interface is doing for us, if the benefit's not clear, I want us to stop. I want us to learn more, and I want to question those things, okay? And the biggest thing here that we can do is really try to design code and write APIs that defend against fraud and not protect against accidents, to really focus on the idea that we want to design APIs that are hard to misuse. I mean, JBD, Anna from Google, said these two things better than I ever could. A good API is not just easy to use, but also hard to misuse. And you can always embed, but you cannot always decompose big interfaces once they're out there. Keep interfaces small, compose interfaces as you need them. And this is really going to help you design better code in Go, not only today, but for tomorrow. Welcome to Lesson 6, Error Handling. If integrity matters, and it better matter to you, then error handling is everything, because everything we do in Go is around APIs. We design APIs, and error handling is about respecting the user of your APIs, giving them enough context to make informed decisions. And Go is really special with error handling. Go knows that it's not about writing a program that works. It's about dealing with failure, right? This is what we do day in and day out. Engineering is about writing code that can handle failure gracefully without causing more problems. And the error handling mechanics and semantics in the language are tailored to that, and that's what we're going to learn in Lesson 6. All right, now the next step in learning design is error handling. We started very early in one of the very first sections when I was trying to prepare you for this class to tell you that lines of code are important, and to tell you that if we really want to maintain mental models and reduce the chances of legacy code, we've got to worry about failure. Failure is always what we're coding against, and error handling is everything. It's not about exception handling, because exception handling, I think, hides context around errors. This is about looking at an error when it's happening, right? In Go, errors are just values, and they can be anything you need them to be. But from an API design perspective, for me, error handling is about one thing. It's about showing respect to the user of your API, giving your user enough context to make an informed decision about the state of the application and giving them enough information to be able to either recover or make a decision to shut down. If your application loses integrity, you have a responsibility to shut it down. I don't want to shut down apps, but you have a responsibility because integrity, data corruption, no. And there's two ways to shut down an application in Go. You can go to OS, the OS package .exit, and even set a return code on that. That's the fastest way. Or you can call the built-in function panic. Now, you'll choose one over the other depending if you need a stack trace or not. So if you need the stack trace, you're going to call panic. If you don't, you just call OS exit. But we've got to design APIs and errors around the idea of giving the user enough context to make an informed decision. So let's start with the basic mechanics and what the language provides you in terms of error handling. Now, what you're going to see here is the error interface. Now, this error interface is provided to us built in to the language. There really is no package called built-in here. This URL, that name built-in, is there purely for documentation. But look at the error interface. It looks like it's unexported, but it really isn't because, again, it's built into the language. And it's got one active behavior, error, and it returns a string. And this interface is how we work with errors. If you think about it, error handling in Go is done from a decoupled state. And that's very, very important. Because error handling is going to be all over the place, because it's going to be widespread, we want it decoupled so we can change our error handling, improve and refactor error handling without creating a large set of cascading changes throughout a code base. So this interface is critical. But again, errors are just values in Go, and the most widely used value for error handling is what you see on line 15, and that is the error string type. And this comes from the errors package. Notice a couple things about the error string package. One, it's a struct type that is unexported. And two, it has one field in there, which is an unexported field named S of type string. This is the most commonly used error value in Go, and in many, many cases gives us enough context to give the caller enough information to make an informed decision. Now, the next thing you're going to see from the errors package, implementation of the error interface. I want you to notice a couple things here. One, it's using pointer semantics, and that's very, very important. We're going to come back and explain why pointer semantics are very important here. Unless you're working with a error value type that is going to require value semantics, maybe like a reference type or a built-in type, if we're using that struct, I most definitely want pointer semantics for the implementation of the error interface. And notice that it's really just there for one purpose. One, to make the value compliant with errors, but two, for logging. Whatever comes out of this method should be for logging and logging only. If your user has to parse the string coming out, you have failed the user. We cannot have them parsing to get context. Okay, now that we have the implementation of the interface, we now have the factory function. There it is. Again, coming from the errors package. And this is how we create errors. Remember, or more importantly, look at the return of this factory. It is the error interface. And we look on line 27, and what we see is that we are constructing a value of the unexported type error string, taking its address, because we're using pointer semantics for the implementation, which means that we can only share, and we stick that in the error. So anytime you call new, I want to show you on the whiteboard for a second what that error variable is going to look like when we call new, because what's interesting here is we've got a factory function that's not returning a concrete value directly, it's returning an interface value. And remember, I told you that factory functions really should be returning concrete values and pointers, except this is that one kind of exception. Remember, there's exceptions to everything, and that's new because we always work with errors from an interface perspective. So when I call new, what we're going to end up really getting back is the error interface value. It's going to say I have a pointer to an error string, and it's going to have a pointer to the struct error string type, which is really just a string at the end of the day. Well, it probably wouldn't say Bill, right? It would be some sort of error message, whatever that is. And this is what we're going to get back. We're going to get errors and work with errors from a decoupled state. This is now an error interface value with a concrete pointer inside of it to our error message or string. And it's very typical in Go to be looking at this kind of code here when it comes to error handling. Notice that we're in an if statement. Inside the if statement, we make a call to, say, in this case, web call. We check to see if web call has failed. We've got the error not equals nil. Now, there's a few things here that I want to talk about before we move on. One is that people liked the idea of exception handling because the idea was the try code had your happy path and your catch took care of all the negative path, and you separated this for code readability. I get it, but I can't tell you how many times when I landed in the catch, I was lost because the context of how I got there is lost. Was it this call? Was it that call? And I used to spend too much time trying to figure out how I got inside of a catch. It doesn't work. But you can still have this concept of happy path if you follow this basic design principle when writing code in Go. And when it is reasonable and practical, what I want you to do is use the if statement to handle your negative path logic and keep your positive path logic on a straight line of sight. In other words, if this call to web call succeeds, then I just move down the function to the next call. So this line of sight right here, this tab, is my happy path. I'm going to get the same benefits we were getting from exception handling. If this call was succeeded, no problem. We keep our line of sight going, and we continue to go down this line of sight for the happy path. And we use the if statement to deal with our negative path logic. My line of sight down this line right here is our negative path. And the idea is that we return out of the negative path. So we do something. If there's failure, then we're going to handle that failure, whatever that means. We'll talk about that, and then you will return. You can have, even though you have a single entry point for a function, get into your head that we can have multiple exit points. And the one thing I really want you to avoid using is an else clause. Else clauses make code an order of magnitude more complicated to read. Because what else clauses typically try to do is you're putting positive path logic inside your if. You're trying to push a function from the beginning all the way down. It just means I have to consume, read, and understand more code as I go through the function. When you use this pattern, I don't have to worry about reading as much code because I know that if I've gotten here and I've moved down to line 36, I know everything above is already done and fine, and we're good. So I really want you to follow this pattern. I also want you to stay away from else clauses because we're not looking to have a single exit point. What's really nice about Go 2 is they have this concept of a naked switch. And on the naked switch, in your case, you can do Boolean logic. You can write Boolean logic here. And if you do have a situation where you may have an if-else, then use the switch to do that. And again, leverage the idea of negative path on the return, negative path always indented. Try these lines of scope here, these lines of path. You'll see that it's going to really help you. And as we continue to work with code here, I'll show you how this code base is doing it. OK, great. So we've got the call to web call. Web call down here is returning an error. It's returning an error interface value where the string inside of our error value here says bad request, right? That's the string, bad request. So when we call web call, we take that error interface value, we store it in a local variable to the if called error. We're using our short variable declaration operator. This is a local variable only bound to the if. This is really great. And then we check error not equals nil. Now this is interesting because nil is really an interesting concept in Go. Nil is always the 0 value for the two types that can be nil. One is pointers, and one are the reference types. All right, so nil always takes on the type it needs to satisfy an expression. In this case, what is nil? Well, since ERR is an error interface value, then what nil represents is a nil error interface value. You see, it's always going to take on the type it needs so we can do the compare. But I like English. And so for me, error not equals nil, what it really means, it's asking one question. It's asking, is there a concrete value stored inside that error interface? Here's a situation where there's no concrete value stored. Here's a situation where there is. And in our case, we're going to have it. So anytime I see error not equals nil, what we're really saying is there a value, whether a piece of data, a value or a pointer, is there something stored, concrete, inside the error interface? And if there is, that means we have an error. Now in this case, the fact that we have an error is all the context we need, because this function only returns one error. And we know what that error is, and we have enough context, and we can make an informed decision about how to handle the error. All I'm doing right now is logging it and returning it. All right, so when you got a function that returns just one error, a lot of times it's just the fact that an error exists, that there's a concrete value stored inside the error interface, which is enough. But what if web call could return multiple errors? At that point now we have to deal with a different mechanism to give the user enough context to make an informed decision. So error variables are our next level of context to give that user an informed decision about what is going on. And these error variables are great when you're going to have a function that can return more than one error. Now if you notice this variable block, I've gone ahead and I've declared two error variables, still using the errors package new to create the error interface values. But I'm assigning them to basically a global variable at the package level here. And I want you to look at the naming convention, because we're using ERR in front of these variables. This is an idiomatic naming convention in Go. You'll find it in the standard library. So ERR bad request, ERR page moved. These error variables are our context. Now if I go ahead and I look at web call, you'll see that web call, if it fails, returns one error variable or the other variable. Now I want these error variables at the top of the source code file where they're used. If they're used in multiple places, then put them at the top of the source code file named for the package. You really want the user, or your user, to see that these variables exist, because it really shows how much you care about them, because you're trying to give them context. So when we call web call, either we could get back ERR bad request, or we can get back error page moved, which means now that the developer using your API makes a call to web call, stores the error interface value inside of a local variable, checks to see if there's a concrete value stored inside there, and if there is, now uses a switch to determine, is it this variable or that variable? Did we get back ERR bad request, or did we get back ERR page moved? Depending on the variable we get back, now we know how to handle the error. So variables are a critical and important part in being able to maintain the use of the default concrete type coming out of the errors package, that error string type, or unexported type with an unexported field, and yet still being allowed to leverage that type and give users enough context to make informed decisions. What we now have to think about is what happens if that error variable doesn't give the user enough context. When that happens, the next thing that we're now allowed to do is create our own custom error types. But I do not want to be polluting our applications with custom error types just for the sake of using them. We want to use the error string type and variables first until we no longer get enough context from it. So type as context now applies when we're going to need our own custom error type. I mean, think of networking issues, right? I mean, how many problems can happen on the network? Just one, right? We all wish. There's tons of things that happen on networks. So an error variable isn't going to be enough to say there was a network issue. We're going to need to know what was that network issue. And the more detailed we can get about the network issue, the more we're going to know whether we can recover from it or not. So type as context becomes very important when we start dealing with custom error types. Now what I want to show you are two custom error types from the JSON package. This one is called unmarshaled type error. Notice it's an unexported type with two exported fields, value and type. I want you to notice on line 22 as well that we've implemented, or at least the standard library has implemented, the error interface using pointer semantics. Again, pointer semantics are going to be the default. There will be exception to use value. I'm going to come back and show you that. Also look at the implementation of the error interface here. Remember that the implementation is for logging, right? It allows the concrete value to be an error value, but it also is for logging. And one of the things I want you to always look for is if every field in the custom error type is being used in the logging message. If we're missing a field from the logging message, I would question the relevance of that field. You wanted to create a custom error type. You added this field because you thought it was going to help the user, but it wasn't enough to log information about it. That could be a smell. So we're going to get an error of this type when you don't pass a pointer into an unmarshal call, because unmarshaling and decoding requires, pointer semantics, shared access. This custom error type is used when we have an unmarshaling error in the JSON package. That's when you have a document that says this field is a string, but you defined it as an integer in your concrete type. Then we're going to get the unmarshaled type error. That's what this error is for, right? That's why we have value and type. But here's the second custom error type that we have in the JSON package. It's called invalid unmarshal error. We'll get this when you don't pass the address of something into the unmarshal call. Again, I want you to notice that we're using pointer semantics here for the implementation, and I want you to notice that the message coming out is a little bit more complex. Okay, we've got these two user-defined, custom error types, part of the standard library's JSON package. And I want to show you this function called unmarshal. I've taken a snippet of code from the JSON package for the unmarshal call. The one thing I want to show you here is the second parameter. The second parameter is based on the empty interface. The empty interface tells us nothing because any piece of data, any value or pointer satisfies it because it doesn't have to have any behavior. I want to be very careful when we're using the empty interface. Don't use it to write generic APIs. We should be using the empty interface when we have to pass data around where that data can be hidden without problems, or in this case where we're going to use the reflect package, because what we want to do is at runtime or dynamically inspect the concrete data. This is great if you want to do model validation. Reflect packages are fantastic for model validation, or like what we're doing here with some unmarshaling. Now, if you notice, we're using the reflect package value of function call. This is how we always start a reflection. And we're basically saying, is the concrete data inside of V? Is it a pointer? And is it nil? Really, we're saying if it's not a pointer or it's nil, then we're going to return this error value right here. Again, we've implemented the interface with pointer semantics. We always have to share. So we're going to either store an invalid unmarshal error pointer in the error interface value, or we're going to share this unmarshal type error inside the error interface value. Again, we're going to be processing from a decoupled state the error interface, but now the question is, what we want to know is what type of value is stored. What type? Type is context. Was it a pointer to this type or a pointer to this type? Now Go gives us a special mechanism to do this type as context, and it happens on the switch. So look at what we do. We call unmarshal, we get back the error interface value. We ask, is there a concrete type stored inside the error interface value? Oh, there is. Then we do a type assertion on the switch. Notice that the type assertion is using the keyword type. It is the only place where we could do a type assertion on the keyword type inside of a switch. And what this is letting us do is type as context. What it's saying is, okay, type assert what is inside of the error interface value. And if it happens to be a pointer of this concrete type, then let's execute this code, and E will be a copy of that, right? It's always going to be a copy on the type assertion, a copy of the pointer. Or if E is a pointer of this type, then that's what we have. Let's execute this case, and E will be that. Type is context. It's really cool, right? The conditional logic is based on what type of value is stored, and thanks to the type assertion, we get a copy of what was stored, and now we can process our error handling from that concrete place. But for me, that is also a problem. We want to maintain, to the extent we can, error handling from a decoupled state, because once we switch from the decoupled state to the concrete, then any improvements we make to error handling against those concrete types could cause a cascading effect of change throughout our program. So even though this is super cool, right, this idea of type as context for error handling, it's kind of dangerous because we're setting ourselves up for some potential cascading changes throughout the code base. But type type as context can be very powerful when you need to move concrete data across program boundaries where both sides need to work with the concrete data itself. Then this idea of type as context can come in really, really handy to move data across program boundaries, maintaining levels of decoupling. I'm just afraid when we're using it here with error handling, because I really rather be processing the error interface value directly, or at least maintain levels of decoupling. So then how can we maintain this idea of custom error types without moving into the concrete? This is where we're going to start talking about this idea of behavior as context. Behavior as context allows us now to use these custom error types, but to stay decoupled. Let me show you that. Let's start again with our type as context example. Here in this function right here, this method, I am making a call to read string based on this interface value called reader. We can imagine that we've abstracted a network call. Now when we make this call over the network, we should get a line of data back, or we might get an error. So we check to see if there's a concrete value stored inside the error interface. And if there is, notice what I'm doing here. I'm doing a type as context, and I'm checking the different types of concrete error values that we have in the net package. Pointers to op error, pointer to address error, pointer to DNS config error. There's types, lots of types of errors that can occur in the network, and the net package tries to cover them all. And so this type of context looks pretty cool because I can now filter down based on what was stored inside of the error interface on that call, which error we got. And you can see that I'm calling temporary on every one of these concrete values because you're told that if there's a temporary method like this, you should call it. Remember, errors are just values in Go. They can be anything. We need them to be both in state and behavior. This temporary method is beautiful because if it's temporary, then we know that we're still in a state of integrity. Just keep going. If it's not temporary, we've lost integrity. Maybe that listener has gone down, that socket has dropped, and now we have to make sure that we can recover. Okay, this is great, but again, we're moving from a decoupled to a coupled state. If we make any changes to these concrete types, this code's going to break, especially something from a net package where lots of applications are dealing with networking today. This could create cascading changes across large different code bases that we don't even own. Okay, so what we prefer to do is try to maintain this level of decoupling. But let me switch over to the net package for a second. I'm going to do a search Golang net. And I'm going to see the net package come up here. And what I'm going to do is search for op error. I want to look at op error. Op error is the most common type of concrete type we might be using for error handling in the net package here. It's our most common error type. I do want you to notice something that I didn't mention before. There is a naming convention for a custom error type. And that's that it ends in the word error. And we would have and you'll see that in custom error types. Op error. You know, and we saw that also as well over here with address error, DNS config error. So that's a naming convention I want you to follow when you're defining a custom error type. Now I hate all this orange on that search. So we're on line 414. So let me just get rid of that, and we'll go over to 414 so we can see it a little bit better. Now, here we go. Here is the op error type. I'm going to try to bring it all into view. And you can see that this is a type that is exported with 5 exported fields. You're able to inspect all of the details you want from the networking error. The net package has exported everything. But if I scroll down, you're going to notice that this is the implementation of the error interface. Look at that. It's using pointer semantics for the implementation. Not a surprise. You can also see how complex it is. The string is going to be very complex. Again, we don't want to have to parse the string to figure out what's going on. Now, all of those types will have this op error or this error implementation using the pointer semantics. But what I want to focus on next is the temporary method. Let's see if we can find the temporary method for op error. Oh, look, there it is. Look how complex this method is. Thank God they implemented this, because look at all of the type assertions. I mean, I wouldn't have been able to figure this out. So this temporary method returning true or false is brilliant, and it's really, really important because it's going to allow us to simplify whether or not there is or is not an integrity issue with something as complex as a networking issue. But I want us to go back to this code for a second, because if we go back here, you should see this pattern where we're type asserting to the concrete to call temporary, type asserting to the concrete to call temporary, to call temporary. Really, the common behavior here is temporary. This is all I care about. Technically, I almost don't even care what the concrete type is if there's a temporary method. So let's apply the ideas of behavior as context and clean up this code. I mean, we can start off with the idea of this. Let's take a look at this. Look at this code here. This becomes very interesting to me. Look how the net package has an interface called temporary. They have inside this code base defined a level of decoupling through this temporary behavior. But also notice that it's unexported. What does that mean? It means that we don't have access to this interface type from our code. But it would have been nice to have access to it because we could have leveraged it for our own decoupling. But guess what? It would have been a mistake to have this exported because the only piece of code that needs to implement temporary is inside the net package. They own the different custom error types. They have the need to decouple. We're not implementing temporary on behalf of the net package. It's for internal use. So remember that goes about convention over configuration. There's nothing stopping us from defining our own temporary interface, is there? No. And isn't it true that any concrete type that has the temporary method inside the net package also implements or satisfies our temporary interface? It absolutely does. Again, the beauty of Go with static code analysis, right? The beauty of Go to convention over configuration is we've now implemented our own interface that the concrete values inside the net package also implement, right? That data, the values and the pointers. So look at what I do. We're going to go from these three cases, right? The three cases on the error where we're going from decoupling to that concrete. And I'm going to move it all down into one case. There it is. This time when we do the type assertion, I'm not going to ask it what the concrete data is inside of E. What I'm going to ask is, does that concrete data also implement my temporary interface? I am now staying within a decoupled state. And when I do that now, I go to just one case. That's it. I don't care what the concrete data is. All I care about is that it implements temporary. And temporary will tell me whether or not I have an integrity issue. This is beautiful, right? The fact that an error value can have not just state, but behavior can allow your caller, your user, to maintain decoupling in error handling, even when we're using these custom error types. So here's a general rule that I want you to follow. If your custom error type can have any one of these four methods, it doesn't have to have all of them, just one, then I want the custom error type to be defined as unexported with unexported fields, because if it's unexported with unexported fields, you're forcing that your user can never, ever go from a decoupled state to that concrete, right? We can't type assert to the concrete. You're really helping them, even though they might feel like they're being restricted. Here are the four methods, okay? Temporary, timeout, not found, and not authorized. That's it. There isn't really another one. If you can add any one of these four, we can maintain decoupling with custom error types by making the custom error type unexported. Remember, temporary covers a tremendous amount. Temporary is really kind of this blanket statement that you have an integrity issue or you don't. And if people complain that you've made the custom error type unexported, and you have a valid temporary method, just tell them, look, we're not going to export the type, even if you feel like you need to inspect it directly yourself. Let's fix temporary to be more accurate. And what's brilliant is we can fix temporary to be more accurate without creating a cascading code change, because this code doesn't change if we change the implementation of temporary. If anything, this code gets better because it's more accurate. Now, if you have a custom error type like the JSON package did. Remember those custom error types that we talked about before for the JSON package? Timeout, temporary, not found, not authorized. They don't work for those types. Those types have to be exported. The user may need to move from decoupling back to the concrete. It's a scary situation, but that is what it is. Most of the time, that temporary method is going to work for you. So I don't have a problem with the custom error types as soon as the error variables don't work, but I'd love to make sure that those custom error types are unexported with unexported fields, and that we apply method sets of behavior that the user can bind to maintain that their error handling is done from a decoupling state. I want to show you some more of the interface mechanics here through this code. This is a really interesting code because our mechanics and our semantics might trick us, or if we have very strong understandings of mechanics and semantics, then we can really understand the behavior of this. This is a piece of code that was, I've retrofitted it from a bug that a friend of mine, who is a very experienced Go developer, a couple of years ago produced. And I told him right after I saw it, we're putting this in the training. So take a look at this code. Let's see if you can find the bug here. On line 10, I define my custom error type. Look at the naming convention again. It ends in error. We're using the empty struct as our base because we're not going to have any state. And I implement the error interface using a pointer semantics like we should be with these struct types. Find the bug. Now, I wrote a function called fail, and I want you to notice that fail does not fail. Fail is returning nil for the error in that second parameter position. Okay? So what do we do here? We go ahead on line 23. I declare an error interface variable set to its 0 value, a nil interface. We call fail, which does not fail, returning the result back to our local error variable we've already declared. Fail does not fail, but we check to see if failed failed. And guess what? As far as this code is concerned, fail failed. How is it possible that fail is failing when we are returning nil, the 0 value for the failure? I want you to think about this for a few seconds. Okay, enough time. We just don't have time to sit here all day. I want you to think about this just for a few seconds, okay? Why is fail failing? Because there is a fundamental bug in this code that everybody at some point makes. I did it myself too, early on in Go. But let's walk through the code to show it to you. On line 23, we create an error interface value. There it is. It's error, and it's set to its 0 value. There is no concrete data stored inside of error. Now, when we call fail, fail returns a value of nil. So guess what? The value we're now sticking in here absolutely is nil. That really hasn't changed. But the question you have to ask yourself is, what type of nil? Remember, nil takes on the type it needs. And if you look at the return, what we're saying is a pointer to a custom error. We've actually stored a concrete piece of data inside the error interface value. The value happens to be nil, but it's of the custom error type. As far as this is concerned, we do have a concrete piece of data stored inside the error interface. This is the bug. The bug is that the developer didn't use the error interface on the return. They used the custom error type. Remember, the custom error type is an artifact. It is the custom or the concrete value we're using. Error handling happens in the decoupled state. So we've got to fix this code by always returning the error interface value. Now, what are we returning out of fail? We're not returning a nil custom error. We're returning the nil interface value, which now means that there is nothing stored inside the interface. Now, I want to share one more thing with you here. I kept telling you that we want to be using the pointer semantics, pointer semantics for our implementation of the error interface, unless the value that we're implementing here happens to be like a slice, a value semantic type of piece of data. If we're using struct types, I really do not want to be using value semantics here. Let me show you, because this is going to teach us this last part of the interface mechanics, just like this one showed us some mechanics. This is going to show us our last one. Now, let's go back to the original code where we have this web call that could return this error bad request. Let's say I decide to get fancy or clever. And I decide in this code, I'm going to create my own error variable called error bill. There it is. And I'm going to mimic what's coming out of web call with bad request. Great. Now I decide that I'm going to change the way I do error handling by not asking if we're not nil, but if we are that particular variable. Now the question I'm going to ask you is, should ERR equal error build, right? That's a new, so that's creating a new value. That's creating a new value. Should this be the same? Well, when I run it, as probably expected, it's not. ERR is not the same as ERR bill. This really does make sense in the sense that we're calling new. But remember, we're using pointer semantics. So let's do something here. Let's change the implementation to use value semantics. The one thing I'm telling you not to do with these struct types. Don't use value semantics, but I'm going to do it. I'm going to use value semantics now for the implementation of the error string. I'm going to store value inside of the interface. And now when I run this code, what happens? Whoa, 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 whoa. ERR now equals ERR bill. Suddenly I have equality. The question is why? I'm going to say this for the very last time. Remember, interface values are not real. Interface values are valueless. There is an implementation detail, but from our programming model, they are not real. The only thing that's real is the concrete data stored inside of them. Therefore, when I am comparing two interface values, I'm not comparing the interface values because that's impossible, they're not real. I'm comparing the concrete data stored inside of it. That's the only thing I can compare. That's the only thing that's real. So now that I'm using my value semantics, think about what's happening. Now what we have is an ERR variable that says this. Oh, you've got a custom error value, and that custom error value has this string. Let's say it's bad. And then when we look at ERR bill, what are we saying? What we're saying now is I've got, remember this is ERR right here. This is ERR bill. And this one is saying I've got a custom error value. And this also has the word bad. Guess what? Since both ERR and ERR bill are storing values of that custom error, we're going to compare the values. And isn't it true that the values stored inside of both of these interfaces are the same? They are. It's the same string. We're basically doing a string compare, which is very, very dangerous. This is why we don't want to do that. Then why, when we're using pointer semantics, don't we have the same problem? When we're using our pointer semantics, what these interfaces are saying is we're storing not values, but pointers, addresses. The address of this value and the address of this value is being stored. Now what are we comparing? Not the values, but the addresses. And isn't it true that the address of this value can never be the same as the address of that value? That's right. So the mechanic here is that interface values are not real. They're valueless. The only thing real is the concrete data. And when we're doing these comparisons between interface values, we're not comparing the interface values. We're comparing the data that was stored inside of it. Remember, we can be using our value semantics and our pointer semantics. If we're using value semantics on the storage, then we're talking about comparing the value itself. If we're using pointer semantics in storage, then we're going to be comparing the address. It's the same thing that when we're passing interface values across program boundaries, we're not really passing the interface value around that's valueless. That's not real. We're passing the concrete data that's stored inside of it, and how we stored it in there is going to determine everything. These are really important mechanics that are going to help you look and read code and understand the behavior. Again, what we're trying to do is look at a piece of code. When we understand the semantics, we understand the behavior. When we understand the behavior, we understand the impact. We're going to be using interfaces quite a bit in Go, and we don't want to be doing interface pollution, but decoupling is going to be a big part of what you do every day, and having a strong understanding of these mechanics and the semantics are really going to help you. Let's get into a little bit now of design, because one of the things I find that is lacking in a lot of Go code is logging consistency. I spent 30 years trying to figure out how to combine error handling with logging. And I finally came to the realization that actually I tried to, for 30 years, not try to combine it, but separate it. I always wanted to try to get the error handling kind of separated in terms of frameworks and logic around how we log things, this separation. And I really came to the realization that you can't separate these two things, that error handling and logging are this one thing. We've got to bring them together if we want any consistency. And I'm always worried about consistency. And so I always love asking this question to everybody in the trainings that we do live. And that is, if, let's say it's 3 o'clock in the morning, and an error occurs in your software, right? An error occurs, but the error is handled by the software, right? And the program just continues to run. There's no real hiccup. Maybe there was for, a second or two, but it recovered. We keep going. My first question is, do you want to wake up, or do you want to be woken up at 3 in the morning because that just happened? Remember, nobody needs you. The software just kept running. The reality is I don't want to wake up. I mean, the software did what it's supposed to do. It identified failure, it recovered, it keeps moving. So I don't want to don't wake me up, let me sleep. Now, when I wake up in the morning and I get to work, I want to see some indication that there was a problem, right? I don't want to be blind to it, but I do want to see it. But the real question now becomes, am I going to spend time looking at the logs when I get in? Because right now, again, it's not needed. It was recovered. Maybe on my dashboard for metrics, I see that there was an error. I don't know much more, but the program kept going. Here's the reality. The reality is probably I'm so busy with meetings and other priorities, I never go back to look at the logs because it's no longer an issue. It's not that I don't want to. It's not that I'm not necessarily curious, but it's just human nature to say I've got other priorities. What I'm trying to stress here is that we write applications that log a lot of things, and most of the time we're logging as an insurance policy to be able to find bugs when errors occur. And I did that for a long time. But the reality is that there's too much activity on our systems today. Our user bases can grow to 1 million people almost overnight. And so logging that much has a huge significant cost. A lot of times logging is going to create a large amount of allocations, which is going to put a lot of pressure on your heap. Now that's not unique to Go, but we are talking about Go. So I want you to consider that logging is important, but we've got to constantly balance signal to noise in the log, because if you're writing logs, writing data to your logs that you end up never, ever reading or using, you're wasting CPU cycles on something that you could have been doing actual real work. And it goes beyond just the CPU cycles of your process. You're eating network bandwidth, disk I/O bandwidth, other complexities that go through the entire system. So during development, I really want to make sure that we always have a good level of signal in our logs, and we're logging from a trace perspective the bare minimum we need, but then we're logging the errors in a way that there's always enough context if we want to take the time or need to take the time to look at it. And that's also been a big problem for me for 30 years. How do you make sure there's enough context in the log, both from a tracing perspective, bare minimal, and then an error perspective, and not duplicate errors throughout a log, and at the same time minimize those log writes, and then, let's add more to it, have a consistent pattern that we all can follow and review during code reviews where we're doing logging the same way and it's not random. Oh my God, my head wants to hurt, right? All of these things. So you might find it hard to believe that I don't believe in logging levels. I've never been able to turn a logging level up in time to get more detailed information. So I'm not a believer in logging levels. I tend to use the standard library log package quite a bit. I will create my own logger and pass that around the application, but either I need this information or I don't. And I make sure throughout my unit testing and any other integration testing that I do that my logs have signal. Now, I want to show you a pattern using Dave Cheney's errors package. Dave Cheney's error package is really nice, and it gives us a consistent way to apply error handling, apply logging, and have code consistency throughout, minimizing, again, a lot of pain. But remember when I talked about handling an error? That's a big thing. Now that I can't separate logging from error handling, what do I mean when I talk about handling an error? I mean really a couple of things. When we talk about error handling, what we're going to mean is that when a piece of code decides to handle the error, it means that that code is responsible for logging it and logging the full context of it. It also means that code has to make a decision. Can we recover or not? If the answer is no, then error handling means we shut down the app, either with the stack trace on the panic call or OS exit. If we can recover, then that code has to recover the application back to its correct state and keep it going. At the end of the day, when that piece of code returns, it never ever returns another error back up. The error stops there. Either the app is recovered or it shuts down. But we've also logged the error. That is error handling to me. And this is what this pattern is going to be perfect for with Dave Cheney's errors package. So imagine this piece of code right here. We're at the bottom of a call chain, and we make this call to third call. Some function above us makes a call to third call. And you can see here that third call always fails. It's failing with this custom error type called app error. We're using pointer semantics. We're going to store the address of app error in there, and we've set the error code to 99. This is very similar to maybe like a standard library function that is going to return these raw or these true error values. Now, second call was the one that called third call. And you see our traditional mechanics in Go, where we're going to use the if statement to do the error handling, right? We're staying away from the else clauses, happy path in the first tab. And so here we go. We call third call. We get back an error interface value. We ask, is there a concrete value stored inside the error interface? The answer is yes. And when the answer is yes, now the developer writing this code has to make a choice. It's really Boolean. Am I going to handle the error here or not? If the answer is handling the error here, we deal with it like I said before. But if the answer is no, I'm not going to handle the error, then there's only one thing you're allowed to do, and that is wrap the error with context. All right? We would prefer to handle the error. The lower in the call stack we handle the error, the better opportunity you're going to have for recovery. But in this case, the developers decided, no, we're not going to handle the error. Think about this. I don't have to worry about logging anymore. I don't have to worry about recovery anymore. All I worry about is the wrap call. Now, the wrap call is interesting because it does two things. At this point, remember that we've gotten an app error. Here it is. This is our app error. And our app error is already wrapped against this error interface value. Now, this is error, right? Wrapping the app error. But what wrap is going to do now is wrap context around what we have. And there's two types of context. There's going to be call stack context, and there's going to be user context. The call stack context is going to take where we are in the code, at that line of code that we're doing the wrap. We now know exactly where we are when this error occurred. And we're also now going to be able to add some user context. In this case, I'm just indicating that second call was calling third call. So we're going to get call stack and user context built in there. Now we take this error, we wrap it, and we send it back up the call stack. And when we do, first call now is involved. Remember, first call is calling second call with the parameter of I. Now, an error occurred. We know that, right? We know that second call returned this error. Well, guess what? First call now has to decide, am I going to handle the error? If the answer is no, then you only have one choice. We wrap the error again with that context, our user context and our call context. Notice this time our user context is showing the parameters or the values we passed into second call. This is brilliant stuff. You can share any context you need, and if you get bugs and the context isn't enough, this is what you're going to be improving, the context. If I'm writing a database type of app and I don't have a security issue writing queries to the logs, that would be a query, so I can copy and paste it out of the log and run it directly. Here I love showing what the input was, because I'm not going to get that in the call stack context, but at least I can see what values were passed. That could really help. Okay, so I've got, this is the original error right here. This is one wrap right here. This is another wrapping right there. and we go to main. Now, main made a call to first call. It gets back the error. It says, is there a concrete value stored inside the error interface? There absolutely is. Therefore, we now come into this. Now, the mechanics that I showed you on the case, doing the generic type assertions, guess what? We get to continue to do that because of the cause function. What's brilliant about the cause function is it knows how to unwind this down and get us back to the root error value. And now we're going to type assert against the root error value. And when we do that, we can do the case on line 30. But I think what's even more powerful is this. If you're using the standard library fumped or log packages like I do, if you put a %+v in the formatting, guess what? The full stack trace and context of this whole thing gets logged to, in this case, standard out or standard error, wherever you're logging. And if you just do %v, then you're just going to get your user context. %v just gives you the user context. %+v gives you both. Now I want to show you this running so you can see it visualizing it right here. Let me copy the path and get us over into our terminal. And what I'm going to do is build this program, and then I'm going to run it. And I want you to notice the output. Now, the first output you're seeing is when we did the %v. Okay, we're doing the %+v. And what you see here is a full stack trace. Here's the app error context, state 99. And we can see stack traces from the different levels of calls that we were making in the app. Here's first call, right? So that's runtime, main, all the way to first call. There it is. And then we've got our context of what we passed in. And here what we're seeing is the full context from main to first call to second call, and then the context to third call. So we could see individually how these different layers that we got from our wrapping came in. And then I can use just the v without the plus. And what you see now is just the context, the user context. So I can look at a stack trace from any point in the call chain. And then I can also look at just the user context, right? So we see here, first call, line 51. Let's go to line 51. Look at that. We know that there was failure on that call to second call. That's where we were, right? Inside of there. Again, if we look at first call 52, we know that that's where the wrap call happened. We've got a tremendous amount of context here about where we were, and we don't have to worry about logging all the way up, right? We're not going to separate logging from error handling. It's just one thing. So from a user perspective, remember, this is all we're going to have to now remember. And from a developer perspective, what we're going to just say is, oh my goodness, an error called. Are we going to handle it or not? If we're not going to handle it, we wrap it. If we are going to handle it, then we deal with it. We log it, and then we make decisions about whether we can recover or not. This is a fantastic pattern. And I really, again, want you to not feel like you've got to log everything as an insurance policy. Signal is everything in logging because logging costs you a lot. It's going to cost you lots of allocations. So the logs that you're writing better be worth the cost. They better be truly information you need if there is a problem, and information from a tracing perspective to allow you to know that the system is healthy. Don't forget that we have dashboards. We have metrics. I don't like writing data into the logs. I'm not a big fan of structured logging because for me, logs serve the purpose of being able to find and fix bugs, but that's me, you know, and I'd rather use my metric systems and my dashboards for those data points and try to tie that stuff together. So I really want you to look at Dave Cheney's package. You'll find it in GitHub under PKG errors, and this pattern is something that we use at Arden, and a lot of people that my clients that I teach use, and it's been very, very effective for us. Welcome to Lesson 7, Packaging. Again, maybe one of the most important important lessons when it comes for you to sit down and start writing that production code. How do you structure projects? How do you think about packaging APIs? What are the relationships between packages? What are the costs of coupling? What is the cost of not decoupling? All of this stuff is going to be taught here. I'm going to give you mechanics and design philosophies, and I'm going to share with you how I'm doing this on a day in and day out basis with our projects for our clients and the success we're having around package-oriented design. So this is our place where we start to really learn how do we sit down, structure these Go projects, think about packaging API, and how do we work as a team moving forward and doing that. When you are ready to really sit down and build a production level project, package-oriented design is going to be your friend. I really want you to spend some time reading those links that I have on this page because they go into a lot of detail about what I'm going to cover. But package-oriented design is really important because what it's going to do is give you an engineering decision about where packages go, and it's going to help you identify how your Go project should be structured, and it's going to really improve communication between you and your team members. The whole idea here is that we want clean package design and project architecture that is not random, but very predictable. The whole idea around mental models is knowing where everything is. If you don't have a package-oriented design around your project structure and your packages, you're really going to have lots of problems. Maybe not today, maybe not a month from now, but you will definitely years, and also depending on how kind of turnover you have. Now, what's interesting to me is the history behind packaging. There was an interview given to Brian Kernighan in the year 2000, and Brian was asked this question: can you tell us about the worst features of C, the C programming language, from your point of view? Remember, this was 18 years ago. And this was Brian's response, and when I read it for the first time, I almost fell out of my seat. I think the real problem with C is that it doesn't give you enough mechanisms for structuring really big programs, for creating firewalls in that program to keep the pieces apart. And it's not you can't do this, and it's not you can't simulate it. You know, you can simulate OOP all you want. You can do that, but here's the key. You can simulate it, but the compiler in the language is not giving you any help. When I read this for the first time, I almost fell out of my seat. I mean, here is Brian saying that we have this language that we're using, but when programs get too large, we have big problems around encapsulation and mental models. And here it is. Go is saying, you know what, Brian, you're right, and we're going to fix this with the concept of packaging. Packaging is our basic unit of compilation in Go, and it's how we really structure and think about applications. And the problem is this is very, very different from object-oriented design. Very different. And so all of us, me too for a long time, struggled with this idea of package-oriented design. So I want to try to give you some guidelines and some philosophies so you can hopefully start thinking from an engineering standpoint how to do this better. And there isn't just one way to do this. I want you to understand this is the way that I've developed over the last 5 years. This is how I'm doing it. I am doing it successfully, but every project's different. Every team is different. Dynamics are different. So I don't want you to feel that you're locked in. What I want to make sure is that you've got project structures and philosophies that are in line, and you've got policies and procedures that are in line with this, okay? So I don't want you to say that this is a end-all, be-all. And what I'm also going to share with you, some of it is agreed upon by the Go community today. When we start talking about project structures, this is all me. These are my opinions, my ways of doing it. You don't have to agree with it at all, but I think that you want to at least find something you can agree with so you can have consistency and make sure you're maintaining mental models of your code base. So here are the language mechanics behind packaging as it relates to Go. Now, the big problem here that you're going to find is packaging directly conflicts with how we've been taught to organize source code. You've been taught just create a folder somewhere in your project source tree, throw some code in there, and encapsulate, different parts of your code. And that is because projects like your C++, your C#, your Java languages, you're really building a monolithic application as it relates to your source code. In Go, we don't really have a monolithic application. In Go, every folder in your source tree represents a static library. I want you to think about this for a second. If we switch over to a project that I want to share, which is my service project, this service project can be found on GitHub under Arden Labs Go Training Service. So I want you to understand that github.com, Arden Labs, service. We're going to use this for some package-oriented design. This is a service project that we're developing and building training around to teach people how to write services in Go. And this is what I want people to be learning next after this class. So what I want you to understand is this is a project. It has a source tree. We'll talk about these folders. But every folder here, like this one called Mint, is really going into being a static library. This is really interesting because what Go is saying is that we build software based on the idea that we build these packages, which are APIs, which are really static libraries. And the idea of building an application through the use of static libraries is not necessarily unique. Languages allow us to do this, right? C allows us to create those A files, those SO files. C# lets us do the DLLs. Java has jar files. This isn't new, right? And Ruby has gems, right? This isn't new, but you have a choice whether or not you want to build this monolithic app or build it in terms of these components. In Go, this is not a choice. You have no choice. Every folder ends up being a static library, whether you like it or not. This really puts a constraint on us. So you can't just create a folder randomly and put some stuff in it because you're really going to hurt yourself. You have to think about packaging or component level API design from the very beginning. Okay? What's kind of interesting to me, though, is that this idea of packaging at the source code level here, our source tree, really makes me think about almost microservices at our source code, where every folder represents its own unique API, its own kind of program boundary, just like we would have with microservices. And so we've got to find ways of decoupling these program boundaries and contracts these program boundaries so they can interact, again, dealing with what? Change. So it's a really interesting, brand new way to think about software development, design, and architecture. Now, understand something, that there is no real concept of subpackages. Just because a folder is sitting inside of another folder doesn't mean that this package is a subpackage. All packages are built and compiled and then laid out. From the linker's point of view, all packages are at the same level. So we want to leverage the hierarchy to give us some indications about relationships. But from the compiler's point of view, there are no subpackages, there are no relationships. All packages are at the same level. And we talked already about exporting and unexporting, exporting being a way of opening up a package's API to be public. And another interesting thing is that two packages cannot cross-import each other. And this is a really important decision. It's done to kind of simplify things, and it helps also to make sure that initialization is consistent. If you have two packages importing each other, which one gets to be initialized first? That's a very complicated problem, especially consistency over time. So it also makes you slow down and start to think about the relationships or the import or coupling relationships you have between packages. So the language mechanics are kind of few, but they do put some interesting constraints on how we define projects, lay out projects, how we code and architect and design our source code. It's no more a monolithic application with folders. It is a project with lots of individual static libraries that we call packages that eventually are going to import and be bound together. And the more decoupling we can think about in this case, the better and healthier our projects are going to be. All right, before we get into project structure, I think it's really important to have a philosophy behind what we're doing, because a philosophy allows you to validate what you're doing. I was on the airplane on my way in to record this, and I was writing some code, and in my head I kept thinking, this API design is violating one of my philosophies. I kept thinking this over and over again, and the guy sitting next to me turned around and he says, "Did you say something?" And I looked at him and I said, "What?" He says, "Did you say something?" And I said, did you hear me say that I'm violating a philosophy? And he said, yeah, and I started laughing. I mean, it was so ingrained in my head, I actually spoke it out loud on the plane. And so I think guidelines and philosophies are very important because they allow you to make sure you're making the right engineering choices and you're not going off the deep end. So when it comes to packaging design philosophy, these three things are very important: purpose, usability, and portability. And I do believe that the Go community is behind these philosophies. Now, how we implement them, we all have different ways to do it. Now, the first one here is purpose. And for me, a package must have purpose. And for a package to be purposeful, it must provide and not contain. And what do I mean by this? Look, packages cannot be a dumping ground of just kind of generic code. Every package must have an API, a clear API on what it provides the user. And if it's not clear, I want you to question that package's existence. And the name of the package should describe the intent of what it provides. And if you're struggling to name a package, you probably have a code smell there. Now, packages like net, fumped, HTTP, OS, that's clear. We know what they provide. Packages like util, helper, common, these are packages that contain code, and these are going to cause you a lot of problems because they're going to be a dumping ground of code, they're going to be a single point of dependency, and eventually you're going to crumble on top. And I promise you this, if you have a package today called models, if you have a package today that is just a common set of types, your project has already failed. Please, in monolithic applications, you can have that type of encapsulation from a type perspective, not here in Go. Types are an artifact to move data across program boundaries. They cannot be an API in and of themselves. Avoid packages like models. Every package that has a real purpose has its own type system. Even if you have to duplicate types across multiple packages, that is going to be much better. Remember, the concrete data solves the problem. We can leverage interfaces later on to decouple our APIs and to accept everybody's concrete data. You're not just bound to your concrete data through an interface. You can leverage anybody's concrete data. So I want to really avoid packages like models because now that's a very large thing of containing, and all of a sudden you change one model, one concrete, and you've got cascading changes throughout your code base. Very, very dangerous. So a package must provide and not contain. There are very few exceptions to this rule. Now, I don't have to get deep into usability. You can read these things, okay? We've talked about these things since we got here. Intuitive, simple to use. You must respect the impact on resources and performance. You've got to minimize users' cascading changes. Asserting to the concrete is dangerous. We always want to reduce, minimize, and simplify our code base. So usability is more of an art. And remember also that usability means that we're designing APIs and packages to reduce or minimize fraud and misuse, right? This is what we want. Precision is everything. Remember, we don't want packages and APIs that are vague. New semantics that create a level of precision to reduce misuse and fraud. But portable is usually what most developers think about when we start talking about packaging. The more decoupled, the more reusable a package is, the better it's going to be in your ecosystem. We want to be able to pick up packages and move them. We want to minimize coupling because coupling creates constraints. And policy is a big part of this too. When I talk about policy, what I mean is if a package is making decisions about how we log, how we do configuration, how we do things, then only other applications that want to do those things the same can use that package. The more policy a package has, the less reusable it is. We've got to be very clear about when we're setting policy, and the purpose of that package will help determine whether we're making the right decisions around policy. And again, the single point of dependency is going to be death over time. That's why those packages that contain things can be so dangerous, especially that package called models, because everything is going to bind itself to it, and eventually everything will collapse upon itself. So we want to leverage these design philosophies as we begin to talk about a different project structures. I'm going to share a project structure with you that is my own, that is working, that follows within these design philosophies, and allows us to make some very clear engineering choices across our team, which again gives us levels of consistency that we need. All right, so let's talk about a project structure that I use on all of my projects. Arden Labs uses it on these projects as well, and I try to get my clients to do it as well. This isn't the only project structure you can use. I've seen some very nice project structures that are different than this, but anytime I see a project structure that's working, trust me that it's applying these design philosophies and the things that we're going to be able to do to validate where code goes and how code should behave and be designed. And that's the big key here. Now, I really do believe that every company, or at least every team, should have a Kit project. And I also believe that a project is bound to a single repo, let's say in your GitHub or whatever source control system you're using. So I really do want you to have a Kit project. And a Kit project to me is the set of foundational packages or APIs that every application you're building should use. So I would want to see things like log packages if you're not using the standard library, config packages if you're not using some third-party stuff, web frameworks you're building, whatever it is. And I also like to see that laid out in the root of that source tree, right? I want to see that laid out kind of right there on the edge. Probably don't want to see packages inside of packages here. I also want these packages to be as decoupled as possible. In other words, I don't want log importing config or config importing log. Really, these packages shouldn't even be logging at all, because if you choose to do some sort of logging, then you're setting policy. I'm also not a big fan of the logging interface. I think that is a big mistake. I mean, the standard library doesn't log. These foundational packages shouldn't log either. Now, if these foundational packages have go routines or paths of execution where events are happening that you want to log, then I think you should ask for a handler function, and the user can implement whatever they want in the handler function, and you just call it during those events. See, we don't need interfaces all the time. Asking for a function like a handler function really can help streamline everything and then get you to that logging that you need. Okay, that's Kit. Should be in its own repo, hopefully something called Kit, foundational stuff. Now, every project that you work on is what I call an application project. Now, the application project can have multiple binaries in it. This isn't a one-to-one. In fact, less is always more. And a large team of people can work in an application project if package-oriented design is being implemented properly. I've worked on teams of 3 to 5 people in this structure, and we've been very successful without stepping on each other. Now, I want you to notice there are 4 folders in an application project, at least my application project: command, internal platform, and vendor. And this gives us indications of where packages should go, because each one has a very specific purpose. Now, when we talk about the vendor folder, we're going to be using DEP, D-E-P. Today, that is the recommended tool for dealing with reproducibility and vendoring. And the DEP tool, basically on a new project, you'll say DEP init, and then it's just DEP ensure. And a DEP is going to go and look at all of the third-party packages, including Kit. Kit will be third-party packages, and you will maintain a copy of all of the source code and the versions of that. You need this, please. Own all the source code. Unless you've got projects as big as Kubernetes, you should be able to own all of the source code and the dependencies that you're working with. Use DEP. As of today, the language team is playing with something called Vigo. It's an experiment of a new front-end Go tool that will be also helping with vendoring and version decisions and these types of things. We're not there yet. Maybe in a year from now when you're watching this video, we're all using the Go front end and not DEP. I don't know where that's going to end up. So at least for today, you should be using the DEP tool if you're doing vendoring. And please own these dependencies if you really want to maintain high levels of reproducibility on your builds. Now that leaves us command, internal, and platform, and each one has a special purpose. Let's start with command. Command is where the binaries, or the applications themselves that this project owns and is building. I'm going to go back and look at our service project here so you can get a sense of how I'm dealing with this same tree. Notice service is using my package-oriented design project structure. Command, internal, vendor, and we're going to see the platform folder in here as well. Okay, great. Let's talk about command. Command is where the applications are, where the binaries that we're building. It can be one to many. On this service project, which is implementing a CRUD-based web service, you can see a folder called CRUD, and you can see a main.go. Main.go is that entry point, and it's where we're building. And that means that CRUD will be the name of the binary. This is important. If we have multiple binaries we're building, they could be under command, or in this case, since I'm using a sidecar architecture, you can see that we have two other binaries, one called metrics, one called tracer. These are microservices that help dealing with tracing and metrics for this service. And these are three different binaries that we build, three different main.go. Now, packages that are defined inside of, let's say, CRUD are very application specific, and they're there to help support startup, shutdown, maybe some small routing like in a web service, but not a lot of business logic, more presentational logic like in a web service, taking a request, doing a response. Now, what's nice is at the application layer, right, at the command layer, these packages can contain things if you really need to. You can get away with packages that contain at this level because they have really no level of reusability. They're specific for this app and nothing else. You also could have test folders here or packages for integration tests that can help and work with you as well. So at the application layer, this is where you have a lot of ability to set policy. You could do some containment like we're doing with handlers, and you're going to have multiple binaries that you're building. Now, the internal folder is where we put our business logic. This is going to be business packages, service level packages, packages that need to be reusable across multiple binaries, but really business service layer logic. You can see here that I've got a package called user that implements all of my user CRUD. You can see that we're going to use files to organize source code, not folders. So I do have a file called models, which is the models for user. You can see I've got my tests. My tests stay within here. And I've got my API for user. You can also see that I've got a package here called mid, which is my middleware stuff. And that package is providing business layer middleware. Okay, so any other business logic is going to go here. And then platform is for foundational packages that are not inside of Kit. So I've got special database support, Docker support, flag support, special testing, tracing, web framework support, foundational packages. So what do we have? Internal platform, foundational, internal, business logic, command, application logic. See how we have these three layers separated? I don't care how you do it, but you really want to separate application from business to foundational logic, and this is how we're doing it. Now, because I know where packages belong, we can do a lot of validation against our project during a code review to validate that what we're doing is sane. And I want to share some of that with you. I've already told you that we now understand where a package goes. If you tell me, Bill, I need a package to do this, the first question I'm going to ask is, well, what does this package provide? Is it clear and reasonable that the package provides this and just this? We want packages to try to provide one thing and one thing really well. Remember when we were talking about API design in layers? Primitive layers, lower level layers. I'd like our packages to be as primitive as they can, though. Eventually you can have some lower level packages and some higher level packages. So we've got to learn, what does this package provide? If you tell me it's going to provide some business layer, we're going to put it under internal. If you tell me it provides some foundational support, we're going to put it under platform. If you could tell me it's very specific to the application, maybe some sort of presentational kind of stuff, request response, hey, it's going to go under command for that binary. You see, now we're not guessing. We're not going, where does this package go today on Monday? Monday we're going to put it here, but on Tuesday we're going to go there. No. And we use the internal name, by the way, because we get an extra level of compiler protection. The compiler will make sure that if any project tries to import another project's internal packages, the compiler will say, no, you can't do that. We get an extra level of protection. So that's great. I can now validate where a package belongs based on its purpose, and there's no mistake where it goes. We're not going to argue about where packages go. Its purpose dictates platform, internal, or command. But there's other things that we can validate too, not just the location of a package inside the project. We can also look at dependency choices, right? Anytime a package imports another package outside of the standard library, something from vendor or something from inside the project, things get very interesting. Now, regardless of where the package is, we always want to understand the cost and the benefit of the coupling, because there's a real cost to the dependency, right? You better not import a package because you need its types. If I see you importing models, I'm going to start crying. Why can't your package have its own models, its own types? Why do we have to create that binding? Okay? I also want to try to minimize packages that import each other from the same level. Right, the same level. The more we can decouple that, the better. In other words, if I come back here, it would be really great if database didn't import anything else here, or web didn't. Now, you can't always do that, and it's nice to just have one level inside a platform and inside of user. I think it helps keep things clear and organized. But there are times where you can really make a strong engineering case that if we just do this one little change in the API, we can reduce the decoupling of packages at the same level inside a platform and internal. Platform is a little harder to try to maintain decoupling at the same level, but I work very hard to do this at the internal level. I really want to make sure at the internal level I try to keep packages at the same level from importing each other. And if I do have a relationship of an import, this is where I want to try to use the hierarchy and maybe try to define that package inside the package that needs to import it. You can't always do it, but I want you to spend some time here really working hard to minimize dependencies inside of internal at the same level, inside of platform at the same level. Now, the other thing I want us to do is understand the import tree. I have made sure that this project's structure is in such a way where we should always be able to validate the following. Here, any package that we have inside of command has the ability to import inside of internal and platform. You can always import down, you can't import up. If you decide to create a different project structure, try to maintain this idea that down is good and up is bad. What this means is if I have a package like user never, ever should be importing packages inside of command. That is a violation of law. Import down, import up, bad. So that means that internal packages can definitely import inside of platform and vendor down, but never up. Platform packages, guess what? They can import from vendor or inside platform, but they cannot import up. They can't import into internal. They can't import into command. Look at what we've done here with this project structure. We're able to validate that the imports that we're making are always down. Command or application packages can take in business packages, can take in platform packages, but platform packages can't import into application. Oh my God, think about how bad that would be. So we're able to do that type of validation too. Policy, I told you policy creates coupling. So what we're going to try to say is Kit packages and platform packages, they're not allowed to set policy. It means they're not allowed to log. They're not allowed to trace. Those things, if they're needed, have to be decoupled. Configuration, too, decoupled. Metrics, telemetry, decoupled. Okay, we don't want any dependencies that we have to avoid from Kit and platform. But guess what? Command or application packages and internal business packages, they can set policy. They are the application. There is much more freedom with the command or application packages having the highest level of freedom to set policy because they are unique to the application. We've talked already as well today about how data is accepted and returned. We want to make sure that we have consistent use of value and pointer semantics. We only want to use an interface to accept concrete data when we need that behavior, when we need decoupling. We want to validate that. If we don't need the decoupling, we don't take the interface cost. We ask for the concrete data directly. We always want to be reasonable about creating a new type if one already exists, except we don't want to import a package for a type. I'd rather declare a new type to keep a package's API as decoupled as possible. We can look at now parameters for an API and validate how decoupled that API is from other packages. And error handling too we can validate. What we said is, we talked about before, error handling means that an error is logged, that the application validates its integrity. If it can't, it shuts down. If not, it does. We can keep going, and that error is no longer reported. So look at this. If I've got a Kit package that's calling panic or wrapping errors, now I've got to stop the code review, right? Because wrapping errors is a policy, and you're not allowed to panic an application here. Only the application is allowed to panic, right? That's an application concern. But at command, which is our application packages, they are allowed to panic. They are allowed to do that. They are allowed to wrap. This is, again, a policy that can be set. And in fact, a majority of the error handling is going to happen at the application or command level. Internal packages, remember this is our business logic. Guess what? It's not allowed to panic applications either. It doesn't have the right to do that. Though it will be able to wrap, that level of policy is fine, and it will hopefully be able to handle errors as well. But your platform packages are like your Kit. Therefore, no panicking, no wrapping, root cause only. You see now how I can look at a package and knowing where the package is and what its purpose is, what is allowed and not allowed to do. And when it comes to testing, it's also very important. Your test files should always be in the same folder as your code when it comes to Kit, internal, and platform. But at the command level, this is where we probably will do more integration testing. There I don't mind having a folder called tests. Remember, this code really isn't reusable anyway. And recovering from panics is another big one. You have to be very careful when you recover from panics. Losing stack trace information can be costly. So application level packages in command absolutely can recover from a panic. Has to make sure that we're back at 100%. But I get worried when Kit, internal, and platform packages recover from panics. Now there is one exception. If those packages are creating and own their own Go routines, then they are responsible for stopping panics on those Go routines if they can guarantee that we're going to have integrity. So look at how important project structures are, because the project structure now stops things from being random. If you tell me you need a package, I'm going to ask you for its purpose. Once you tell me your purpose, I know whether it goes under command, internal, platform, or if it's Kit, then vendor. I know that. And once I know where it's located in the project, I know all of the ways of validating its imports, its policy decisions, and everything else that's going around it. And we can validate again that we have these strong engineering decisions all the way through, and we're not arguing about things, right? Remember, package-oriented design allows a developer to identify where a package belongs inside your project, and then the design guidelines it must respect, the things that we've been talking about. It defines what a project is and how it's structured. I've given you one structure that works incredibly well for me, our developers at Arden, and our clients. It's not the only one that would work, because the whole end game here is two things. One, to be able to develop mental models of our code base so we know where everything is, and two, to improve communication on our team so we can always promote clean package design, clean project architecture, and we can always have real valuable discussions and not arguments. And if I go back to that service code, this is a great example of package-oriented design in the wild. This is code that I call starter kit code. If you want to build a service in Go after this training material, go find the Arden Labs/service repo right here. You're going to see package-oriented design in full action, in full display, and you're also going to see how to build web services with all of the mechanics and the semantics and the things I've been teaching since we started this video.